Good morning! Thank you guys for getting up to listen to the Fast Science Summit. And we've got a really phenomenal lineup for you guys today, so I think it's going to be an amazing day with a lot of information, and we'll just see how it goes. So what I'm going to do first is give a small introduction, and I'm calling it Genetics and Therapeutics 101, and this is just to refresh everybody on the genetics and how we're looking for therapeutics in a general sense. And then you're going to hear from the people who are actually doing this, who are doing the work and doing the research. For those of you that are out on the live feed, if you want to send questions, you can do it either through our Facebook page, look for Foundation for Angelman Syndrome Therapeutics, or you could tweet it to us either at Cure Angelman or at fast_science, and we will try to get your questions to the people in the room. So hi to all of our live feed watchers. All right, okay. So a little bit of history of Angelman syndrome. So Dr. Harry Angelman, who's here, actually 50 years ago this month published a paper on puppet children. He had 3 cases, 3 children who came into his clinic, and they all had very similar characteristics, and they were very unique characteristics. And if you think about Angelman syndrome, it's incredible that 3 people in the Liverpool area all came to his clinic, and he noticed that they were all so similar. And as the legend goes, he named them puppet children because he had seen this picture of a boy with a drawing of a puppet, and the boy was very happy, and he thought, I'll use this as my term. Now, we don't use this term anymore, and we really ask people not to use this term. And what we do now is call it Angelman syndrome after Dr. Harry Angelman, who first described it. I think some of you also know that this painting was recently stolen just last week, I think. Hunt for it right now because we'd like that part of our legacy back. So it was a while later, 1987, when it was determined that children who had Angelman syndrome had small deletions. And we think of them as big deletions because they're big things in our lives, but they're actually really tiny. But that led the way to figuring out what it is in that region of chromosome 15 that is so important for Angelman syndrome. And in 1997, it was determined that the gene UBE3A was the causative gene in Angelman syndrome. So to think about how Angelman syndrome ends up manifesting, you have to think about genetics a little bit. And so I want to remind you that we all have 23 pairs of chromosomes in our cells. And today we're really only focusing on this pair, and this is chromosome 15. And we get one set of that pair from our mom and one set of that pair from our dad. And so in the one cell stage, you've got one set from your mom and one set from your dad, and that one cell is then going to divide many billions of times to make the person that's all sitting here in this room. And I'm a developmental biologist at Princeton University, and that's what I actually study, is how do you go from one cell to all of us in this room who have your arms and legs in the right places. And if you think about it, it's pretty miraculous. But in this case, we're talking about one set from mom and one set from dad. And the thing that's really cool about this is your cells know which set of your genes came from your mother and which set of your genes came from your father. And the way they know that is through something called methylation. And so we talk about methylation a lot when we're talking about our diagnoses. And so what I'm showing you here is a neuron, and this diagram is showing you what the genetics looks like on chromosome 15 right next to UBE3A. So in these diagrams that we always have in our science papers, this box represents UBE3A. So this is where that gene is on the chromosome. And on the maternal chromosome, the box is red because this box is actually making UBE3A RNA, which is going to make UBE3A protein. On the father's chromosome, this box is black because it's not expressed, it's silent. And the way your cells know the difference between mom and dad is this methylation. So this is a modification of DNA that the cells recognize. And the methylation modifications from mom are different than the methylation modifications from dad. And so when we've asked you, when we're talking about diagnoses, have you had the methylation test? What we're asking you is, has someone checked the DNA to see if both mom and dad's methylation patterns for this region are present? If they aren't, that tells us something about the type of Angelman syndrome that the individual has. Now, in an Angelman syndrome neuron, the maternal copy is gone. This is the deletion case. So that maternal copy is gone, so there's no expression of this gene. And then on the father's side, because of the methylation pattern, there's a different transcript that's expressed. And we talk about this transcript. It's called the antisense transcript, or the ATS. And we don't understand the mechanism completely, but because the ATS is expressed, it prevents UBE3A from being expressed. Now, I do want parents to realize that in all the other cells in your body, both copies of UBE3A express. So even if you have Angelman syndrome and you're lacking UBE3A in your neurons, all of your non-neuronal cells still have UBE3A. So this is a really interesting facet of Angelman syndrome, is that it's neuronal specific. So we know the gene that's involved, and we know the cells that we actually need to go and target, and those are the neurons. All right, so with that background, these are the known mechanisms for Angelman syndrome. So in this diagram, I'm showing you the female chromosome is in red and the male chromosome is in blue, very clever. And so on the red chromosome is the UBE3A that's expressed, so it's in bold type. And just remember, on the paternal chromosome, there's UBE3A, but it's not expressed, so it's gray because it's silent. The vast majority of us have children with deletions, and what happens in the deletion then is the UBE3A gene is just missing. It's not there in the mom's chromosome. The cells don't recognize it as being something to express in dad's chromosome, and you miss UBE3A. With a UBE3A mutation, you'll have a normal methylation pattern because it will see that both mom and dad's chromosomes are there. But UBE3A itself has had change in it that has prevented it from being functional. And if you want to know more about point mutations and how they work and how they disrupt function of UBE3A, I'm happy to talk to anyone at any of the breaks. There's also uniparental disomy, or UPD. And in this case, this is another thing that's almost like a miracle. So what happens is when you make that first cell, something happens and mom's chromosome gets kicked out. And it can't survive with only one chromosome 15. And life is a powerful selection tool, so what it does is it copies the chromosome it has from dad, and now you have two chromosome 15s. So this is what we call rescue, and the cell knows how to do it, and it does it very well. The only problem is that now you have two methylation patterns from dad, and so the gene is not expressed from either chromosome. So it does cause Angelman syndrome, but the miracle here is that you have a living person. And finally, there's imprinting center defects. And so in this case, methylation doesn't look normal, but it's not UPD. And what it is instead is it's other parts of the chromosome that are important for putting those methylations in the correct places. And that process goes awry, and you end up with a chromosome that is not recognized as being from mom, and so UBE3A is not expressed. So these are all the major ways that we have Angelman syndrome. And the thing that's important to keep in mind is that in all of these cases, there's a perfectly good copy of UBE3A sitting there. It's just not being utilized. So what is UBE3A? So UBE3A, you can think of this as part of a protein complex, which is essentially a machine. It's a little machine in your cells that has a function, and UBE3A is part of that machine. And the function of this machine, which involves UBE3A and some other proteins, E2 and E1, is to take a modification called ubiquitin and put it onto other proteins. So UBE3A in its little machine complex goes around and finds the proteins it's supposed to add this ubiquitin to, and it does that. And then what happens most of the time is proteins that have been tagged by UBE3A in this machine get taken to another machine called the proteasome. And this you can think of as a recycling center. It's another protein machine in the cell, and what it does is it takes those proteins that have been labeled and disintegrates them. It basically recycles them, breaks them up into little pieces, and those pieces get recycled by the cells for something else. And so if UBE3A is not present, proteins that should be labeled aren't labeled, and the idea is there's probably a buildup of proteins in neurons that shouldn't be there, and that somehow is interfering with optimal neuron functioning. That's how we mainly think about UBE3A function. I just want parents to understand that ubiquitin is a modification that typically targets other proteins to go be recycled by the proteasome. But there are also cases where you can add ubiquitin to other proteins in the cell and cause them to have different activities. So UBE3A is involved with recycling proteins, but it may also be involved with modifying other proteins to do their jobs effectively. But the take-home message is without UBE3A, whatever this ubiquitin labeling is doing is not happening, and it's causing neurons not to function correctly. So before I tell you about in general, how we're approaching looking for therapeutics, I just want to stop and say, this is a reasonable question. Is it reasonable to think we can even make a targeted therapeutic for Angelman syndrome? And this is something we debate a lot on Facebook. And personally, I think there are a lot of reasons to think that this is possible. And I'm just going to share 3 of them with you that are, I think, particularly compelling. The first is this paper in 2007 that came from Ipe Elgersma and Ed Weber. And what they found was that they could rescue the phenotypes of the Angelman syndrome mouse by making modifications in other proteins. And the reason that this is so compelling is the protein that they modified is a protein called CAMK2, and it's important in neurons, it's important for learning and memory. But the thing that I want you to know is that this protein is predominantly expressed in neurons after the mouse is born. So what that says to us is that the brain's developed fine, the neurons developed fine, there's nothing necessarily wrong with how the neurons were made. What really seems to be wrong in Angelman syndrome is how they function. Now, as a developmental biologist, I can tell you that if your heart doesn't form, I'm not going to be able to rescue that very easily in you if you're born without a heart. I mean, we could do a heart transplant, but it's not an easy thing to do. So if Angelman syndrome caused strong defects in the way that the brain was formed, there wouldn't be much we could do about that. But it looks like that's not the case. It looks like the brain is fine, and what we really need to do is think about trying to fix the functioning of those neurons. And this was the first paper that said it was possible, and it was also one of the first papers that came out that said you could do this for any neurological disorder, and has really set off a wave of change in the neurological community, or the neuroscience community, who used to think that there were windows where things could happen and windows where things can't, and that has all been upturned and things are really changing. The second, and this is another paper from Ed Weber's lab, if you restore UBE3A into the adult brain, an adult mouse brain, so we take a virus, go into an adult mouse and put some UBE3A coding sequence back in the brain, you can rescue some of the phenotypes. An important thing to keep in mind here is that this is an adult mouse. So this is a mouse that's had Angelman syndrome its whole life. We go back in and add some UBE3A, and now these mice have some recovery of their functions. That tells us that there's going to be a lot that's possible. And there was a recent study that suggests that there are some phenotypes that might require more early intervention than later intervention. And that absolutely may be true, but the really important thing about this paper that I want you to take away is that neuroplasticity, the functioning of those neurons, could be rescued at any age that they tried. So we think the mouse model is telling us that we have a lot of potential for therapeutics. We can also say that if you're a mouse with Angelman syndrome, we have some very good news for you because we can take care of you. But the bottom line is there is a reason to believe this is possible, and we're not going to know until we know. So we have to keep moving forward. We have to keep looking for therapeutics, and once we have them, we'll know what we can rescue and what we can't, and what we can make better and what we can't. But there's plenty of hope. All right, so general ways to find therapeutics. This is the easiest, or I would say the most upstream approach to this, and that would be trying to just reactivate that silent copy that's sitting there in all your neurons and ready to go. And there are a lot of people who are working on these types of strategies. There's reactivation of the paternal gene, and that would involve chemicals, antisense oligos, different engineered proteins, and you'll hear about some of that today. Or you could add an additional copy of UBE3A from using the viruses, for example, that I told you about with the mouse study. So we have those two approaches to turning back on UBE3A. Now the benefit to that approach is that that would be the upstream thing that's wrong, and everything that's downstream of UBE3A we hope would take care of itself. But the other thing we can do is we can try to look for things that UBE3A does or proteins that it modifies and go after those as our targets. And so, for example, we could try to find all the target proteins that UBE3A interacts with and see if any of those are proteins that already maybe have drugs available to modify their abilities and their activities. You'll hear some about that today. It turns out, we talk about how there's no UBE3A function in Angelman syndrome, but it turns out the researchers have seen that there's actually a very small amount of UBE3A that's expressed in the neurons in Angelman syndrome. The paternal copy may leak a little bit. So what if we could figure out a way to stabilize that little bit and keep it around longer, and we could put some more UBE3A into the neurons? And I just want to mention that one of the first postdoctoral fellows that we funded, and this was the Christina Castellana postdoctoral fellow, Jason Yee, just published a paper this year in Cell, which is one of our top journals in the science field, and he had found a modification of UBE3A that's important for its stability. So the money that you guys have raised and helped us with has already started some important work towards trying to figure out how to stabilize UBE3A. So here's another way that we can do this. All right, so a little bit of a preview for what you're going to hear today. And some of these people should be in more than one column, but I wanted to simplify it a little bit. We're going to talk about restoring UBE3A, and you're going to hear from the FIRE team, David Siegel and Kevin Nash specifically, but also Ed. Jody Cook is going to talk to us from Agilis Pharmaceuticals. Art Bodette and Ben Philpott aren't here, but I just want you to know that they fall in this group. So ISIS Pharmaceuticals is talking about the antisense technology to stop that antisense transcript and let UBE3A be expressed. And then Ben Philpott had published a paper with some chemicals that turn on UBE3A. Those chemicals are really harsh, but it gives us the proof of principle that there may be other drugs out there that could modify expression of UBE3A and be therapeutic for us. Thinking about modifying what's happening in Angelman syndrome and making those neurons function better, you're going to hear from a lot of people here. Jeremy Levin and Matthew Durian are coming up next from Ovid Therapeutics. You'll hear from Scott, Ann, and Ed from the FIRE team about some of the work they're doing that sort of falls in this realm. But I also want parents to know this, because we talk about our therapeutics possible. We already have therapeutics. And you're like, what? We have them already. We use them every day. We're talking about finding better therapeutics. So what do I mean by that? We have anti-epileptic medicine. We have the ketogenic diet. We have the low glycemic index treatment. Those are therapeutic interventions for Angelman syndrome. They're targeting the epilepsy. And we're going to hear from Donna Herber. I think this is disruptive nutrition, not skivation, so I apologize. Today about a potential dietary approach. We know there are some behavioral therapies and medicine that can help with sleep issues. I'm happy to talk to anybody about this if you want to talk about the trial that was done that modifies behaviors in sleep. We can treat reflux with Prevacid. We can treat behaviors with therapies. We can treat motor issues as best we can with physical and occupational therapy. And then communication has really exploded recently with the advent of the more affordable iPad for those of us who can't prove that our children are smart, even though we know it's true. And I want to point out to you that tomorrow the educational symposium starts at 9 o'clock, and we have some of the leaders in those fields who are going to be here to talk about communication and some of the things that are possible with literacy for our kids. So I strongly recommend that you don't miss that. Okay, and with that, I just want to finish up by showing you how fast some of this has gone. So I told you that from 1965 until 1997, it took us that long to figure out that it was UBE3A. In 1998, so just 1 year after we figured out that this was the gene, the mouse model was created. Because once you know the gene, then you can go into the mouse and remove it and say, okay, now I have a mouse with Angelman syndrome. In 2007, this is the paper from Ed Weber's lab that showed that you could rescue that mouse model. This was the motivation for founding FAST. So this was why we came together and put this foundation together, because we said if that rescue happened, then there should be more money put into this because we need to be looking for things right now. 2011 is the paper published from Ed's lab showing that you could virally replace UBE3A. That same year, paternal UBE3A expression was turned on in neurons by Ben Philpott's lab with topotecan. 2015, Art Bodette's lab has published the paternal UBE3A expression activity by these antisense oligos. And now we're here to hear all the great science today. But just look how fast things have gone since the rescue of that mouse model. So it's been 8 years, and that might seem like a long time, but if you think about how long it took to figure out that this was the gene, we are now moving at a very rapid pace. And that's thanks to a lot of you sitting in this room who have done everything from bake sales to Ruby Tuesday dinners to things like that. The more money we have to put into the research, the faster this timeline is going to speed up. And so that's the end of what I wanted to do for the introduction. Thank you. And that's going to put us right on time. But we're happy to take a question or two while we mic up our next speakers if anyone has anything. So what we have, oh, I should mention this. What we have mics in the aisle. We'd ask you to come up to the mic if you have a question. And There was another thing I wanted to say. Oh, yes, I want to say there's no internet access in this room in general. We're sorry about that, but we have to keep the feed open so that we can do the live feed, and if we start to jam it up, it's going to be a problem. So we're sorry that there's no internet access, but we're hoping you're paying attention up here anyway, so that shouldn't be an issue. Sharon. Can you bring me the program?
Oh, I was just curious. My daughter got our diagnosis early. She was born in '89 and had our diagnosis in like '92, and then the internet, happened, and it's not really all that important. But there was talk about when the mutation occurred. Either like right at conception or during or in utero, or was the egg mutation already in the egg? And I was just curious. Does anybody really know?
So our best guess with this, so is your daughter a deletion?
Deletion positive.
So deletions happen when the eggs are forming, and it happens during the process of copying chromosome 15 over and over again. So there happen to be regions on chromosome 15 that are absolutely identical to one another. So if you think about the chromosome as a zipper, what happens is it comes apart, you copy it, so now you have two copies, but those two copies have to sort of zip back together. What happens in Angelman syndrome is those identical regions mispair, and there's a little piece that's kind of looped out, and that just gets tossed. So the big point here is that it is something that happens in our cells pretty regularly. It is not something that anyone in this room did or looked at or ate or walked across. And in fact, it's possible that that deletion occurred while you were in utero.
Oh, okay.
So because you start to make the eggs, your own eggs, while you're still a baby developing. So some of that could have happened before you were even born. Okay. So there's no one in this room that should listen to anyone who tells them that they did something that caused that deletion. It doesn't happen. Similarly, point mutations that occur that affect UBE3A or change imprinting center defects, things like that, those things happen in our cells all the time. They just do. What's great for us in some ways, if you think about it, is that these things are not incompatible with life. We have our kids, and we love them. And we know that the life expectancy for Angelman syndrome is good if we can get them through some of the conditions they have, like the seizures, and we can protect them from danger. So, the cells do everything they can to survive and make sure that these individuals make it. Okay, so give me just a second, and we'll bring up our next team from Ovid Therapeutics.
I would urge Matthew to come up.
There we go. All right, so on to the people you really want to hear from today. Our first set of speakers, we are very privileged to have Dr. Jeremy Levin and Dr. Matthew Deering here from Ovid Therapeutics. So you're going to get a program tonight at the gala, or tomorrow night at the gala, that has all the information about everyone who's speaking today. But I just wanted to mention a couple of things because Dr. Levin's going to get up and talk first. So Dr. Levin is the chairman and CEO of Ovid Therapeutics. And in 2012, Fierce Biotech voted him as one of the 25 most influential people in the pharmaceutical industry. So the fact that he and Matthew are here and they're going to focus on Angelman syndrome, this is a big deal for us. I also want to mention that before he came to Ovid, he was the president and CEO of Teva Pharmaceutical Industries. It's one of the world's largest pharmaceutical companies. He was also a member of the executive committee at Bristol Myers Squibb, where he put in place some strategies that really turned around Bristol Myers Squibb and made them a much more viable company. So this is the person we need to help us look for therapeutics and to run this. Dr. During was here last year and spoke with us, and he's here again today. And he's a Harvard and Yale trained neuroscientist, spent many years on the faculty at Yale. He pioneered the use of viral vectors for neurological disorders. So if you have some questions about that, you might want to talk to him about that as well, because it's really fascinating. He is the founder of Ovid Therapeutics, and he is also serving as the chief scientific officer at the moment. So I'm going to have Jeremy come up and start to address, and then afterwards we will take questions from the audience for both Jeremy and Matthew. So let's thank Jeremy again for being here.
Thank you, Becky. This is obviously something very important, and if somebody has lost it, Becky, is this yours? Yeah. There you go. I learned to my cost, I put my name behind it just in case. So thank you so much, Becky. Ladies and gentlemen, colleagues, friends, and family, it's a true honor to be here with you today. I want to thank a number of you. If you don't mind, just give me a bare minute, and I'm going to refer to my notes as I go through this, because sometimes I forget names. It's not that anything's wrong with me, but I am getting older. So I want to thank Paula Evans, Becky Burdine, Alison Barrett, and the rest of the FAST team for the invitation to speak, and for the terrific event. I've just seen some wonderful things. I'm really excited what we were doing. So that group of people, they really helped me understand a lot more about how I could engage with and help find therapies. So, but much more important, if I can ask you a question, if I may, it's just to help me again, and perhaps to set the grounding for what I really believe in, and that is the patient. May I ask those of you who are parents who've had their child diagnosed this last year to hold up your hand? And then may I ask those who, just keep your hands up for a moment, those of you who have had their child diagnosed in the last 5 years, and in the last 10 years, and in the last 20 years. I think that to me speaks so much, and even further. I think you all know each other, and for all of us, we will have different levels of knowledge. But one thing that I'm absolutely certain of, you know more about your children than anybody else. And we're going to learn from you as we go through developing the therapies. And it's my goal that we can help you make a difference to your lives and theirs. Some of you asked me why I chose to devote myself to building a company such as Ovid. Actually, Matthew started Ovid. I was given the chance to go and run another 150,000 person company, and Matthew approached me and showed me what the true problem was. Something that was very real, for which I'm incredibly grateful, Matthew. And I want to take you through a little bit of my thinking then, and then in addition to that, move on afterwards and tell you a little bit about what we're doing, if that's okay with you. So prior to Ovid, indeed, I did lead one of the largest pharmaceutical companies in the world. I had the privilege of bringing medicines to millions of people. In fact, 1 in 6 medicines in the United States, 1 in 6 pills in the United States came from the company that I ran. But throughout the last 25 years, as I focused on building and growing companies, I've always focused on the patient. To me, nothing else matters. Nothing else matters. I admired and learned this from some of the leaders in the industry. Not everybody, but some very specific people. For us here today, there's much to learn from the bravery of some of those people in jumping in to areas that nobody else wanted to jump in on. 20 years ago, I witnessed the birth of one of the first rare disease companies, Genzyme, which brought a unique medicine to a very rare disorder, Gaucher's. Fast forward 20 years, a patient that would have died took me out for lunch a week ago. Under the leadership of one man, Henry Tremere, who was brave enough to go into this, and in doing so changed the lives of many, and actually began to instill into those of us in the big companies different ways of thinking. and how we look at rare disorders. 15 years ago, the then new CEO of Novartis, Dr. Daniel Vasella, actually a psychiatrist by training, went against conventional wisdom and was led by science to build a program to find a cure for what was then described as a very rare cancer, not to be ignored, to be forgotten. And he asked only one question: will the program that we have help patients? And when the answer from the scientists was yes, he ignored all the marketing people who said you can never, ever, ever get this to patients because we're only interested in big drugs. Novartis found that drug, and in doing so has brought tens of thousands of years of life to thousands and thousands of patients who would otherwise have died. 10 years ago, the same occurred in Bristol Myers Squibb, where under the leadership of a very remarkable man, not a doctor, but a man who lives out west, a little further west than here, a man called Jim Cornelius, with the support of amazing scientists, went against the entire prevailing scientific wisdom to enter into an area to find another form of cure for another rare sort of cancer, which he did through an untested field called immuno-oncology. Remarkable. And in doing so, I saved many, many lives. So I was privileged to be in all three of those companies at the time those decisions were taken. We were able to make a real difference to patients, their families, and the medical providers. And frankly, for those of you sitting in the audience, you know, it's something that we should expect and demand of the biotechnology and pharmaceutical companies, that they focus on the patient and that they do exactly that. And that's why I'm here. The patient was and is central. But actually, it's not just a professional philosophy of mine to devote myself to patients. It's actually very personal, very personal. From my funny accent, you know I'm South African originally. I experienced something in South Africa as a child quite remarkable, and that has influenced me very substantially. And it's some very little of what you are experiencing with your children. My uncle was born unable to hear, talk, walk properly, and in his early years he was epileptic. We never had a diagnosis. He threw tantrums, he got angry, but we understood his frustrations when nobody else did. We cared for him. And when others thought he was intellectually impaired, we knew otherwise. He was kind, he was funny, and he smiled a heck of a lot. But the odd thing was he definitely knew how to press our buttons. The schools at that time, unlike here, rejected him. The neighbors and our childhood friends, to me as a little boy, was sympathetic but a little bit nervous and really didn't understand. But we did. He lived with us, and when my father died, his last spoken word was that we would have to look after him for the rest of his life. And we did. As the family has done, so I've understood. But it's a small comparison to what you are dealing with. I know that, but it has influenced me. My uncle was a wonderful man and has influenced me profoundly in the way I think about this company and the way we develop our drugs. So, over all those years and into my medical career, that kind of an experience has helped me understand just how central the family is to the care and well-being of all patients. In Ovid, I now have the opportunity where I can devote my career, my life, my time to finding medicines that can help your children. And hopefully, in doing so, Ovid can set an example to the industry. One which will catalyze many new research efforts, new thinking, new ideas, new approaches, new medicines. I think Becky, you said it well. The level to which the acceleration has happened is remarkable, catalyzed by the help of so many people in this room and others who've devoted themselves and their resources to making it happen, and I know it's going to accelerate. So, today as we think and consider the developments in Angelman's, which are remarkable, the message is quite clear to me. There's real hope to develop treatments that can and will help your children. There is no doubt of this in my mind whatsoever. We'll be a partner with you as we walk down this complex pathway, and believe you me, it is complex, to find medicines that can positively affect your lives. So I want you to understand, I have absolutely no illusions about what it takes to discover and develop medicines. I've been involved in literally hundreds of projects. Actually, I've spent billions of dollars, or directed billions of dollars to be spent on developing drugs and bringing medicines to patients. Done correctly, however, I know it can bring huge benefit, and we're going to do it correctly. But I want you, because you are who you are, and you know your children, and there's nothing to be hidden from you, that this is not an easy thing to do. It's complex. Just give you an example. For every 5,000 to 10,000 chemicals tested in animals as potential drugs, only 5 to 10 ever enter into human clinical trials. And of those, only 1 becomes an approved drug. And the process from the laboratory through the clinical trials and eventually approval by the FDA and EMEA, the European agency that regulates drugs, takes a considerable period of time. No shortcuts can be taken. At every stage, the safety of the patient must be taken into consideration, and I can assure you, we will do. On the road to approval of a medicine, in addition, there are partnerships that have to be made, and in particular here in Angelman's, with clinicians, patients, families, patient advocacy groups, and much work and collaboration with the FDA, who honestly try their very best to help and will try their very best to help. They're a remarkable agency when it comes to working with them about medicines of this kind. This is a complex and process and requires tremendous planning, thought, and at the end of it, impeccable execution. But it brings results, and it will bring results. Today, as you've heard, for Angelman, behavioral and cognitive approaches, physical, speech, and language therapy, diet and nutrition are a mainstay. So you're right, Becky, there are approaches, definitely. No therapies yet treat the underlying disease causes. Symptomatic therapy with anti-epileptic drugs for seizure, melatonin, for example, and hypnotics for difficulty in sleeping, laxatives for constipation. But just to be very clear, there have been no major clinical trials of new therapies. And this is important. This is unlike other areas where there's a good roadmap for us to follow. The good news is, though, and thanks to the exceptional scientific work Ed and others have pioneered, it's terrific. Over the last decade, the focus and the evidence around the pivotal role of UB3A is very important. I know that you've seen a lot of science, but I want you to understand that without a roadmap, without a sign, without an understanding of the critical pathways, it means nothing, because you're just then trying out drugs on phenomenology, trying out drugs on things that you think will work, without knowing that you have in your hand a clear molecular pathway that you can go after. This is what new science is all about. This is what new drug discovery is all about. And with that, there's real opportunity. Broadly, you've heard this morning, but I think it's important to reiterate it, that there are 2 general approaches. The first is to try and restore the UB3A expression, the way it works, its function, and to impact it directly. That's a very important role, and I think we're going to see a lot more developing in that area. And frankly, I'm very excited to see it, and I'm to learn about it. And as we get closer to it, to really involve ourselves in it potentially. Importantly, is to intervene equally downstream. This is the second approach, downstream of the UB3A gene. And it's here that we, Ovid, have chosen to focus our initial efforts. It's because we believe we can bring results much more quickly that way. Our drug, OV101, acts in that region. It's at the level of cellular function where we think at this time, there is the maximal opportunity to impact many of the important effects of the syndrome. Now, just to put you on a level playing field, and many of you have heard this, but others, if you haven't, I'd like to just take a moment to tell you this. OV101 has been given to over 3,000 adults in clinical trials to test its role in helping patients with sleep disorders. It reached phase 3A. That's the last stage before approval. But it was never approved for use. It's very important to understand, it was never approved for use. It was only after these initial trials were stopped that it was fully appreciated that the drug actually impacted downstream of UB3A in a manner that was strongly suggestive that it could help patients with Angelman, and then demonstrated in animal models of Angelman's. The drug has shown minimal side effects. That's good, very important for us as we consider our children that could be taking this. It's been used, as I say, for 3,000 patients, and it's really very important that we understand how that drug works, and we do today. But it's never been given to children. And because it's a drug that's never been approved by the FDA, we need to think through very carefully, and we will think through very carefully, how we construct the appropriate clinical trial. I am completely confident that we will do this correctly. And if the trials are successful, OV101 holds immense potential to help the Angelman community overall. Now, as we planned our clinical approach, we studied prior attempts to test other drugs. Many of you are familiar, obviously, with the minocycline trial, and you'll probably ask, well, how come that trial went very fast? How come that was tested so quickly? Remember, I said to you, OV101 has never been approved. Minocycline, unlike OV101, is an approved drug, allowing clinicians to use it and design their own trials rapidly. In addition, unfortunately, unlike other disease areas like cancer, cardiovascular disease, etc., there is no major history of trials to understand how best to construct these trials. The approach with OV101, with your help, and those of the clinicians and others who support us, is an exciting opportunity to use rigorous and modern approaches to design a trial to ensure the best possible clinical and scientific outcome. So what are we doing? Over the last year, we've secured and qualified our drug. We're preparing for our initial submissions for the FDA, and it's our intent that we begin clinical trials for this drug in the second half of 2016. But most importantly, and this is critical, over the last several months, we've sought to understand what are the most difficult problems and biggest challenges that each family faces on a day-to-day basis. This has helped inform our design and where best we should be testing in the clinical trial OV101. We've interviewed a lot of people. Some of you are in the audience today, and I'm very grateful for the time that you spent with us. We know, as I said, where OV101 works. It works on the extrasynaptic GABA receptor. It impacts a technical function of the brain called tonic inhibition. Very important, and we know it works on animal models. And we've now asked the question, where should we be spending time to test it with the greatest impact clinically? And particularly, how should we run a clinical trial to ensure that Angelman syndrome patients show maximal benefits and have the potential to improve to a point where there's a major impact on that individual and his or her family. To do this correctly and in the best possible manner, we had to get a real appreciation of the needs, as I said. For example, understanding the impacts of seizures, sleep disorders, aspiration, constipation, dental care, vision, obesity, scoliosis, bone density, mobility, communication, behavior, and anxiety. This is not trivial. You all live it. But to refine it to a point where the FDA will approve a trial is something which is not an art form, it's a science. And we need to treat it like that, and with your help and your involvement, your engagement, we will do. And honestly, remembering my uncle, I asked a different question. What do the children truly understand? And what is their true potential? And how can we help in that? Because I think often people misunderstand the behaviors that they see for the understanding that's actually there. And how many of you probably believe the same? As I said, with the help of many of you in the audience today, we believe we now have a good understanding of these matters. And because of this, and although it's taken time, we're in the final stage of the designing our proposed trial. This proposal will need to be discussed with the FDA, and we're looking forward to that dialogue. As I mentioned before, the FDA is a tremendous partner, one that I respect and we respect and look forward to engaging with. And as we prepare for the next stage, which is dialoguing with the FDA, then setting in place all of the requirements of operating an appropriately designed and managed clinical trial, first in young adults and then hopefully after in younger children, will start in the USA first, but our intent is also to work in the EMA with the EMEA and to extend our trials globally. And we'll do that in a manner that I've done many times before. I know exactly how this is done. Ovid has the team to do it, and we will do it in a completely appropriate way. So I want you to understand, if I can convey this to you, we at Ovid are focused on you and your children, and we intend to devote ourselves to their well-being. Hopefully we'll be able to bring an important medicine to them. And frankly, I'm not just excited by this prospect. I and my team are utterly committed, but I'm also very, very optimistic. So thank you for your time, and I'd be happy to answer any questions you may have. And if I'm not able to answer them, I promise you I will ask Matthew to answer them. Thank you.
Okay, we have time for some really fantastic discussions, so we would ask you to come up to the microphones if you have questions. Please don't be shy. This is for us as the parents to understand what we want to understand. So, as we always say well, what I say to my students, there are no questions that aren't worth asking if you want that answer. So, let's go. Go for it.
Good morning. Son? My name is Dave Rosenblatt. My son is Nico. He's 4 years old. There's been a lot of discussion in the press recently about pricing in the pharmaceutical industry for treatments of rare conditions, with some therapeutics costing upwards of several $100,000 per year. And I was curious, as you all are approaching investors and talking about the prospects of this research, which are tremendously exciting, how are you all thinking about approaching the pricing question?
David, I think this is probably one of the central issues that you should be asking. And, well, first of all, let's get the cure, and then we'll ask the question. I have decided, what would I like to do with a company? I am not interested in a company that exploits patients and exploits families and exploits the system. I'm interested in a company that can demonstrate that its drugs have a direct impact on the patient and can help them. So, the discussion in the press today that you see is completely justified. For the last 20 to 30 years, unfortunately for me, and I'm probably one of a growing voice, thank heavens, in the industry of executives who are not interested in the consistent raising of prices. I believe you need affordable medicines. I believe that you need medicines that have a result. And I believe that you need to construct the company, and I am going to construct the company to address exactly that. And so that's... I would add one thing. It doesn't necessarily make me very popular with all my colleagues. But every single person in this audience should understand this is front and center in our thinking. We will not be doing these exceptionally expensive drugs that you've seen. It will not be the case with Ovid.
Great. Thank you.
Is this trial going to be a double-blind? Will there be placebos involved in it?
Matthew, would you like to answer that?
Yeah, thank you. Thank you for the question. Absolutely. I feel, having had significant experience with what we call open label design, where you have an interest, the moment you give a drug to an individual, there is so many changes that occur with that trial design that give belief and hope that unless you have a control and you have a blind, any benefit, you're never really convinced how much of that impact is from the drug. And I think the main reason not to do a blinded study initially in most drug development is simply one of safety. In other words, the FDA requires us typically to do phase 1 trials when that drug has not been proven, and you do what we call an open label. In fact, everyone knows what the drug is, simply because of safety. If we feel confident, and we do feel confident about the safety of our compound, of OV101, then I think what we want to do is we want to make sure that every person who is involved in our trial, that at the end of the day we have a result that we can speak with some confidence that this drug truly worked, not simply that you believed it worked or that there was a change that could have been simply related to belief in the drug as opposed to a functional effect. And you can only do that rigorously with a double-blind study. So yes, we are doing a double-blind study.
How long do you think the trial will last?
So it's a very good question. At this stage, and this, as Jeremy had mentioned, we're working in partnership with the FDA, but we expect the trial design to be approximately 3 months. So we would look for a 3-month duration. We feel that the drug's effects and benefits should be seen much quicker than that. Certain change at this drug, unlike drugs which primarily relate or only work through what we'd call plasticity or changing the modeling of synapses or dendrites, that may take sometimes some considerable time for maximal impact. Here we believe we will get those type of effects possibly as well, but we'll see initial effects that occur within the matters of hours to days. However, we believe that you have to remember the moment you have some freedom, say for example you have a drug that, and we believe our drug should, improve motor skills, there will be subsequent gain just by improving motor. There'll be a learning component to that, and we may not see the maximal benefit that it comes after. It'll require 2 to 3 months to see that. So at this stage, we're looking at a 3-month trial.
May I ask your name? Sorry.
Oh, Donna Manhart, thank you.
Donna, just a point. And everything we say, everything, must be qualified that we will do nothing until the FDA and Ovid have finished the dialogue. So whatever we state here are aspirational,
Right.
but actually, let us come back to you with the full design once we've had a full dialogue with them. Because I think, for me, my experience is they're great partners. They give you good insight. And whether we say 1 month, 3 months, 6 months, my intent is to have the right trial, not the fastest trial, and not the longest trial, and not looking for every result that we possibly could have. So I think we're right on the right track now. So I think it's a great question.
Thank you. Yeah, I understand. Thank you very much. And I think I'm speak for everybody here. We really do appreciate the time and the effort and the interest in our children.
Hi, my daughter is 31 years old, and I've been waiting a long time for this, and I want to thank you for the hope you've given me today. And my question is, for the clinical trial, is my daughter too old for it?
My answer to that is very simple. Matthew will design the trial for the best possible result, but your child will have the opportunity, if we're successful, of getting that drug, that is for sure, and in a relatively short period of time.
Okay, thank you.
Sorry, what is your name?
Connie.
Connie, you know what, it's a weird thing. I actually like hearing people's names because we've been talking about it.
Yeah, just to expand on that, as Jeremy said, we have a lot of safety data in adult patients, and this first trial, we believe at this stage, and this will, as Jeremy had mentioned, it's depending on the FDA, but we're not going to have an artificial cutoff at age 30 or 31 or 35. So I think it's going to be, if there are any restrictions or exclusion criteria, they'll probably relate to function. Simply, we need to be able to assess that individual based on the FDA feedback of certain endpoints. So it's more going to be a functional, but I would say you have every reason to hope that your child will be able to be involved in the trial.
Thank you.
I don't think this is on.
Okay, I'm just going to say it really loud. We have a question from our live feed. What do you think the outcome measures will be for your trial? This is from Terry Jo Michelle.
Hello, Terry Jo. We don't yet want to answer that, not because we don't know. We have several opportunities to dialogue with the FDA, and I'd like to hold fire on that until we've had a full discussion with them, if that's okay with you.
Hi, I'm Bridget. My son has UPD. Is he going to be available to take this drug, or is it only for deletion children?
So it's a very good question. From a trial perspective, ideally we'd like the most consistent group, and we will require a genetic diagnosis. I think Becky didn't discuss that there are individuals with Angelman who don't meet those 4 criteria. I think they have pathognomic features. In other words, they have the EEG pattern, they have everything suggesting they have Angelman, yet we don't have a genetic diagnosis. That group, unfortunately, we will not include, but UPD, mutations, imprinting defects, and deletions will all be available, we believe, in this trial. So long as we have a genetic diagnosis, I think we can move forward.
Thank you.
Did you have another one, Becky? Oh.
I don't have it online, but I just wanted to make a mention with that. I know there are a lot of people in the audience that have children. We call them children, but they now have young adults or adults. And many of you don't have official diagnosis paperwork because when your kids were being diagnosed, they didn't really do some of the testing. Given that this trial is thinking it's going to be targeted towards young adults or adults, this might be the ammunition you need to go back to your insurance companies and say, I need that molecular diagnosis now because there is something that my child might qualify for. You can talk to me about that afterwards if you need some help with that. So, now yours.
Okay, actually, Becky, can I just expand on that? We would need some sort of screening process, but we'd be happy as a company if you meet criteria that suggests clinically you have Angelman. I believe, Jeremy, you can expand on this, but I think we'd be happy to actually pay for that testing if it was necessary. So,
yep. Absolutely.
Actually, this is Mary Ann. My husband and I drove to Florida, which was about a 3-day trip to get a methylation test done in 1992 by Dr. Driscoll. So yeah, we did have that. But I was wondering where the testing was going to take place, and how much travel would be involved. I know you can't answer that definitively. And then I was wondering, just by an answer to another question, when you talked about functionality, were you thinking high end or low end?
Matthew, I think it would be best to say we have yet to enter into negotiations with the clinical centers that we would like to have. We have had contact with pretty much all of the top tier investigators that we would like to work with. So I'm afraid I can't answer that question until we actually know that the institutions will permit us to run the trial there, but we will be picking. I'm so sorry about the 3-day trip. You know, for somebody who was born in South Africa,
I would go anywhere, trust me.
But
I would go to South Africa if I had to.
You won't have to, trust me. It'll be here in the United States.
Would it be multiple locations,
Yes.
you think? Oh.
Yes. We'll try and make it as convenient as possible as we possibly can. And we understand, again, some of the burdens that's going to be put on people, and we'll try and help there as well.
What about the functionality? Can you answer that?
Yeah, based on the mechanism of action of OV101, we would expect to see potential benefit on both those maximally impacted and the most severe functional deficits and those who have the least. So we're not going to use the question really is in part, even on mobility, we're trying to think creatively, how can we have endpoints that can actually address individuals who may have very, very mobility, even those who may be in a wheelchair. So, our goal ultimately is to have the drug, assuming that we can prove efficacy, and with all the caveats that Jeremy just mentioned, is to be able to get this out to the broadest group. And so from a trial perspective, we can't say too much about that until we have this dialogue with the FDA, but we're trying to include endpoints that we believe can capture the greatest range of individuals.
And it will be easy to find out how to apply, I'm assuming?
We will be making very clear notices about that, and particularly in association with those centers that are involved with us, we will make very clear notices. This is a process. I know it's a little different for you. For me, it's kind of bread and butter, and I can assure you the team that's working within Ovid will make absolutely sure not only is the contact, the association with the physician, and if there's not a physician close by, we'll make sure that you are well aware of how to get in touch with us. By the way, you're an extraordinarily linked community, so it's going to make it an enormous benefit to us as we consider this trial.
And I'll just remind everybody that Ovid is working with the advocacy groups. So as long as you're tuned into FAST on our Facebook page, our Twitters, our email accounts, and things like that, we will make sure that you get the information.
Yep, it's a very important association.
Hi, my name is Kathy. My son's 7 and he has UPD also. Thank you for being here. And my understanding from last year is that OV101 helps a lot of aspects of Angelman syndrome. And I understand that you want to target the trial in a way that it shows effect. And I'm curious, what are you specifically targeting? And if you can even share that, is it mobility or is it something else?
So one of the important things for us in this discovering how best to use the drug was to ask patients, to ask physicians, what are the most important things that affected them. And as we understood more and more about this, it became clear that the array was quite significant, ranging from, as many of you know, sleep being a critical item, in addition to mobility. I think my understanding was that epileptic seizures were ones that could be relatively well controlled under certain circumstances. So that was, although were important, we hope it'll have an impact there. The question for us on the trial is, what should we seek as our primary endpoints? I think we need to dialogue clearly with evidence in front of the FDA about what that would be. But there's nothing that is unusual to you. You know these symptoms. What we have to do now is to convince the FDA that we have ways of measuring impact on them. Now, scientifically, there is an extremely good reason to believe that we'll have an impact across the board. That's different from going to the FDA and say, we have clear measures that will allow you to approve this drug. And it's not like minocycline, which is an antibiotic. We are approving an antibiotic, then it's an approved antibiotic, and then you can use it for other things. In this case, here we have a complex set of symptoms, but we also now, which is really wonderful, have a deep understanding of the pathway and the impact that it has on the cells. So I think we have a chance of explaining to them which are the different symptoms we should be focusing on. But I think we should wait until that's done. It's not going to delay the trial. That is going to be something that, unless something remarkable happens, will again, as I said to you, second half of 2016, and we'll announce what we're looking for, and the principal investigators will be very clear. They'll be part of the decision making here.
Thank you very much.
Hi, my name's Kim. You said young adults. My hypothetical question, and I have two questions, is if you reach your endpoints and safety and efficacy endpoints in the trial of young adults, what is the plan for our younger children? Is there a clinical trial coming next? Is it a reduced dosage? What would the plan be for those who have younger children? My son is 6. That's my first question. I have one more then.
Okay. Kim, you're exactly right. The reason that we're taking this approach, and we're optimistic that we can perhaps have a good dialogue with the FDA to explain why we believe the drug is so safe and could be used more broadly. But we don't want to assume that. It's our assumption, first of all, that we need, as we go into the young adults where the drug has been used before and the dosages are well understood, that we can have the opportunity either to, with the FDA's support, either to extend this into younger children in the same way, or indeed to do the types of safety testing that they may want us to do or not do. I don't know yet. I think that's a dialogue they have to have, but it is something that we should be conscious of, whether it be a gene therapy, whether it be an antibody, whether it be a small molecule, whether it be, no matter what the disorder is, you must be conscious of the dosages that you use. You can't simply reduce it and give it to a child. That's not appropriately. That, to my mind, that's not good medicine, it's not good science. And what we want to do is to build for a 20-year, 30-year process, not a 2-minute result. So forgive me again for not answering you, but I can assure you I'm sitting on this and thinking it through, and we are right on top of the idea. How do we get it to a child of 6? How do we get it to a baby? How do we get it to the child as soon as it's born? Things like that. Matthew, do you want to add anything to that?
There is what we call a regulatory process with the FDA and the EMA, the European, to present to them what we call a pediatric development plan. And in that plan, as Jeremy just hinted, there's 2 ways. Some drugs you can actually look at children as mini adults and it's just dosing. And there are many drugs that, because of the difference in way various foreign molecules are handled by a child versus an adult, you have to think very differently, not just dose them based on kilogram body weight, for example. We have every reason to believe that this particular drug, OV101, is a very clean drug. What I mean by that is that it isn't extensively metabolized in the body. 70% of it gets excreted unchanged through the kidneys. And that one metabolic step is a very trivial step. So typically, unless you have very severe renal failure, you don't handle this drug any differently. So we would expect, and this is as Jeremy had mentioned, everything is a caveat, but we would expect that we can move towards children a little bit quicker than you would with a drug which has got a very complex metabolism. That being said, we're going to present very early on to the FDA what we believe and how we'd like to move into children, and we'd like to accelerate that process if possible. It will follow the adult trial, but in the time, duration, and the delay in moving to children, we can't speak to right now. But it is first most in our mind is to get this into, as Jeremy mentioned, to the broadest group and build this drug in the way we can for the long term.
Thank you. My second question was, in your original trial with 3,000 adults for sleep disorder, was it submitted for approval, or why was it stopped during stage 3?
This is one of those very strange, actually I'd be more than happy to take the drug myself based on what I learned about it. But Matthew, why don't you explain?
It's an amazing drug, and I think, and the people who discovered it, invented it, carry around in their suitcases and take it every day because they're such huge believers. And any of you in the audience who want to read more about the experience, there's a beautiful article in Harper's Magazine by a Soph entitled Psychonaut, I referred to this last year, who talks about his own experience. The reason the drug ultimately didn't get approved was a commercial decision. There was no, as a sleeping pill, it was being developed by a company where the primary drug that was used was Ambien. And the issue that they were trying to push to was to say, can this replace Ambien? Can it be? They were looking at this drug to be a $2 billion drug, to be the sleeping pill of all time, because unlike Ambien, has no interaction with alcohol, has no next day tiredness, does not have abuse potential, improves the sleep architecture and the quality of sleep. So at every level, it looked like a better drug. The bottom line was, when it came to the end of the day in sleep studies at phase 3, its efficacy as a sleep drug is not as potent as Ambien. When you look at when the FDA is not so concerned about sleep quality, they just look at what's the duration of sleep, what is the sleep latency, not the total sleep. They don't look to say how much slow wave sleep, how do you feel refreshed the next day. So it could never stand up directly, it was not superior to Ambien, and so therefore that didn't provide it. And then because of the lack of abuse potential, the FDA subs told the developers, that was Merck at the time, to say, look, if you really want to promote it as a drug that has no abuse potential, you have to study patients who have a history who had active drug abuse. So that required them to actually go out and recruit cocaine addicts, people who are using drugs of abuse, and not just take those patients but also use doses 3 times greater than you'd ever use sleeping. And in that particular trial, they did a side-by-side comparison of the Ambien. They showed a small number of those patients who had a history of drug abuse had euphoria. So the moment you have a signal and a drug causes some degree of euphoria, and remember, this is only in patients who have a history of drug abuse, not normal patients. That meant that signal would mean it would have to be a scheduled drug. You could not actually just prescribe it openly. And so the commercial model to develop it, when it was no superior to Ambien as a sleep drug, plus had potential of abuse because of the euphoria and be scheduled, there was no commercial model to market it, and that's why they dropped the program. They were that close to filing at the time.
Kim, I want to just go back to the story I told you about Novartis.
Yeah, I'm actually a pharmaceutical rep, so I know Novartis well.
Okay, well, there you go. See, the story with Novartis was about a drug called Gleevec. Gleevec, Dan sat at the table, and the scientist was saying to him, I know you've got this cancer, CML, and this cancer is dreadful, but there's only 20,000 of these patients, and they die after a short period of time, so there's not a market, a commercial decision. Not the scientists, sorry, the marketing guys were saying this.
Right.
And the scientists were saying, well, hang on a second. Just give us a moment. This drug actually can prolong their lives. It's genetically targeted. And Vasella asked the question, will it help the patient? Rather, how big the market is. And that resulted in what you saw, changes of many people's lives. The decisions that go through large companies are often predicated not by the science that's there, but by what is the market. And this is unfortunate, but hopefully over time that will evolve and change. Certainly we're going to drive a change. So I hate to be taking, you as a pharmaceutical rep know that well.
Unfortunately, yes. Thank you. I do.
So I just want to mention we only have about 8 minutes left, and I know there are at least
I
4
just wanted
people
to say
still standing
thank
here.
you. Thank you very much for what you're doing for our kids. Thank you.
Thank you.
Hi, my name is Anurag. My daughter, she's a deletion, about 2 years age. I have 2 questions. The first one is for my wife who couldn't be here. Based on what you understand about the mechanism of OV101, how permanent do you think the impact is? In the sense, if you stop taking the drug, will you see a regression back to what it was? You have to keep taking it, and if you start learning how to walk, will you regress back if you stop doing it? And the second question was, we heard that Agilis recently got the orphan drug status. Is there something along those lines you guys are thinking? Is it a possibility which will help accelerate the timeline and other things?
So let me answer why don't you answer the first and I'll answer the second. How's that?
Sure. So the drug will be required to be taken because it doesn't alter we don't believe at this stage we have any data suggesting, a little bit of animal data suggesting you can create increased neurogenesis and increased cognition in chronic dosing in rats, but we believe you need to continuously take the drug to gain benefit. So I don't want to expand too much beyond that, but yes, this is a drug that you will see improvements we hope to see, and then when you see those improvements, they may gain in time because with use, with engagement with the environment, with additional therapies. So we're a huge believer that the drug is just one aspect to managing the condition. You will still need physiotherapy, you'll still need active treatment, you'll still need environmental engagement, you may need nutritional aspects as well. This is not going to be a panacea. It just fits in as one component, and like every complex disease, we believe it's just one aspect where you need to continue to take the drug. So we believe it'll be chronically administered, so that's one. Unlike gene therapy, you put the gene in, it gets into the brain, and it's a one-time shot. So this will be a chronic drug. I'll let Jeremy discuss the orphan status.
So in all drug development, there are different ways of approaching it. The number one item to me, it doesn't matter how you go through the regulatories, whether you be orphan, non-orphan, or otherwise, is to determine what is the clinical outcome that you want. Thereafter is decisions on whether you want to go into being an orphan designation, not orphan designation, what route you want to go through the FDA is appropriate. Different companies take different approaches. We will probably apply for that, but it was less important to us to seek that, and almost I would be very surprised if we didn't get it. It's not that difficult to get with a rare disorder. For us, the critical focus is to ask the question, how will the drug impact the disease? That's the critical. Our drug is one that has been given to thousands of patients. It's not at the starting point, it's in the middle of the development. This is not a drug that's going to 1 in 10 fail because there's some bizarre, most unlikely to fail because of some bizarre anomaly. This is a drug that we need to prove efficacy with. And so I'm confident that as we go into the FDA, we'll find the right paths, and all companies take their own route.
Thank you.
Thank you so much for this, appreciate it. And as you can tell from my accent, I'm from Australia. So I guess basically this question is related not just to this trial, but to any other trial. How can we get it approved by the TGA in Australia so that, are you going to bring this trial, any other trials that any of the other guys are going to be doing out our way so that my child is 2.5?
So great question. First of all, we have to discuss rugby. There's a New Zealander here and a South African here and all the rest. So this is a global disorder. This is not a disorder of the United States, France, Germany, England, South Africa. It's not that. So we are definitely going to do that. And although I've been to New Zealand many times, I've never been to Australia, but I can assure you we're coming.
You're not missing much.
So the answer is we haven't started, but we will do. And we need to have the dialogue in Australia. The medical system there is beautiful. It's well organized, despite my New Zealand colleague. But just to give you very clear, we're both American, and very grateful for it. So yes, we'll be coming there, but we haven't yet started.
Okay, so it'll take a bit longer.
Not that much longer. I think the second we get rolling here in the United States and the EMEA, once you do that, everything starts falling into place. It's not trivial, but you will certainly do it.
Thank you very much.
Okay, let's get our last 2 questions.
My name's Suzanne. My son Drew is 16 in deletion. And first I want to say thank you, because when we were given a diagnosis 15 and a half years ago, we were given no hope. So thank you guys for giving us some hope. Second, you said there were some side effects, and Drew has really bad side effects with every medicine we try, it seems like. So what are the side effects to the medicine?
So it's a good question. Everything we take has potentially got side effects, but I think this is one of the safer drugs that we've ever explored. When you talk about a drug, we talk about effects that are on target, in other words, that you expect knowing the mechanism of the action. When you act on the target receptor in the brain, the GABA receptor, if you give too much of any drug that acts in that pathway, you'll cause sedation. That's why it became a sleep drug. So if you give very high levels, you will get sedated. So we know that. That comes at so when you feel sedated, some patients will have dizziness. Any drug that gets into the brain essentially has the potential of causing headaches as well. That we haven't seen that in many of the trials. We don't believe beyond those effects, and as I said, in people whose brains are primed, in other words, if you have a history of drug abuse and you're prone to have, and people take drug abuse because they want to have psychotic events. That's why you take cocaine, in fact, to get the high to change the world's perception. Those individuals at high doses have a predilection to having psychotic events, having hallucinations. We do not expect that at all. It was not seen in normal patients, even at doses 10 times what we're planning in this trial. So we don't expect that. This is a very, very safe drug. As I mentioned, the sort of doses that we're discussing are about 1/10 of trials that were previously done in conditions like Alzheimer's disease and Huntington's disease. So we feel we have what we call a very big therapeutic index. The functional effects compared to toxic effects are very, very distant. In other words, we believe we can go up the dose, double it, triple it, you'll still not see major adverse events.
Okay, and before your last question, if we could have the folks from Agilis come up here so we could be ready for our next session, and then we'll take our last question. Okay.
Hi, my name's Tom, and I'm from the UK, and I was just wondering, if your drug gets approved by the FDA and trials start here, what's the time frame for the drug being approved in the UK and Europe and globally?
Well, Tom, it does depend on our dialogue with the EMEA and with the UK, but we are already talking to physicians in the UK and several other countries actually, with the intent to explore how best to get it there as soon as possible. After all, this is the center of where Angelman was first diagnosed, and we'd like to get it there as soon as possible. In addition to which, I was trained in the UK, and I know that system extremely well, and know many. I'm a little older than I was a little while back. And many of the colleagues who graduated with me from Cambridge are now situated in roles within the UK that could definitely help accelerate this. And a lot of them have reached out to me and asked what we are doing. So I expect us to get it there as soon as possible. But first we must get it nailed down here in the US, and then we will go there. But Matthew's already talking to you.
I have a visiting appointment at the University of Oxford, and have already been discussion with the sort of rare disease network in the UK to work with the MHRA. So we're certainly looking at England as a place to really, a point of entry in Europe. I can tell you that.
Okay. Thanks.
We're out of time, but can I just say one last thing, if I may?
Yes, of course.
Thank you very much for all of you thanking us. I'm very grateful for that. I think I'd like to flip it the other way. Expect a lot from us. Don't let us engage with us. We're going to be there with you, and we're incredibly privileged to have the opportunity to work with you. So I have to thank you, not the other way around.
All right, was that a good enough start for everybody for the FAST Summit today? I think we can all say it's going to be a great day. All right, so the next group that's coming up to talk is Agilis Biotherapeutics. And I want to mention while they're getting mic'd up, when we started FAST back in 2008, one of the things we said, the board members would say to each other, is we're like, if we could just get a really good pharmaceutical or biotherapeutics company to look at us and see the promise in Angelman syndrome, we'd be set. So, there's a culmination of a dream here today, having Ovid talk about a trial that's coming up and having some other companies that are going to come up and tell you about their approaches too. This is what we've always wanted. So, be happy you're sitting in the room today. This is a banner day. All right, so our next speakers are going to be Gregory Robinson and Jody Cook from Agilis Biotherapeutics. Greg is the Chief Science Officer for Agilis. He brings more than 20 years of pharmaceutical and biotech experience in research, clinical development, and R&D management. He spent the last 7 years at Shire and then made the jump to Agilis. And he is a biochemist with degrees from Boston University and is here to tell us a little bit about how Agilis is doing what they're doing. Jody is the Vice President of Operations and Strategic Alliances. She has over 20 years of senior executive experience in the life sciences. And she earned her PhD in auditory science at Arizona State University, and that sounds really interesting, so I'm going to get her to tell me about that later. So we're going to turn it over to Agilis. Again, they're going to give an introduction about what they're doing, and then we're going to open it to questions from the audience, both from the live feed on Twitter and our Facebook page, and also in the audience walking up to the microphones. So please help me welcoming Agilis Biotherapeutics.
Great, thanks, Becky. And I'm really thrilled to be here to tell you about, Agilis's efforts to find a therapeutic for Angelman syndrome. I want to thank the organizers, Paula Evans, Allison, and everyone from FAST for inviting us here, and we're thrilled to be involved with this organization. I'd also like to put a special thanks out to Dr. Ed Weber and Dr. Kevin Nash for the efforts they put into Angelman and the work we're doing with them. It's working out very well, and I want to thank you guys for all the efforts. So I want to tell you a little about what's happening and what Agilis Therapeutics is all about. As Becky said, I've worked the last 7 to 8 years in the rare disease space for Shire Pharmaceutical, dealing with patient groups such as this, et cetera, and have really come to appreciate what it needs to go into the rare disease space to find a therapeutic. And because of the efforts in the growing momentum I'll talk about in gene therapy, I decided to make the jump and use the gene therapy to find therapeutics for genetic diseases such as Angelman and other ones that we're looking at in our pipeline. So on the next slide, do I? Thanks. Here we go. Is Agilis Therapeutics, we're really dedicated to advancing DNA therapeutics, innovative DNA therapeutics designed to provide efficacy in rare genetic disorders of the CNS. So we're concentrating on CNS, rare disorders, and how we can use DNA therapeutics, primarily gene therapy, to move forward and develop a viable therapeutic. We're doing this through one of the more comprehensive scientific analysis of the gene construct, of the vector. I'll get into AAV, adeno-associated virus vectors that we're using. But we're looking at synergistic platforms, looking at not only optimizing the DNA that we're using, the regulatory elements to drive that DNA and drive expression of the protein, but also the delivery platform using the very safe AAV, adeno-associated virus vectors. And then using different forms of delivery. We feel that direct delivery to the brain, direct delivery where you need to see the activity, is right now the best way to move forward. So we're using direct delivery for the treatment of our therapeutics and our indications. So why gene therapy? And this was one of the reasons I made the jump to Agilis, is I didn't think gene therapy was moving fast enough at other pharmaceutical companies, and there's a lot of talk, but I wanted to see some action. And really, in gene therapy, there's been a dramatic increase. You've seen it in the news, but there have been clinical successes at Unicure, Bluebird, Spark, to name a few, as well as the environment around the regulatory environment with the Orphan Drug Acts, the benefits you get from orphan drug for gene therapy, as well as the approval of Glybera in Europe for the first gene therapy approval. So there's been a lot of talk, but now a lot of action. Now there is a lot of action in the gene therapy space. Also, manufacturing was always a problem, but now that they've sort of solved a lot of the manufacturing issues and they've been able to deliver enough to make a therapeutic, that's also being dealt with and has really improved the chances of a gene therapy therapeutic being a viable option. And finally, you see significant value creation. And by this, I mean there's investment going into companies who are doing gene therapy. The Wall Street, the investors are realizing that this is a place that they can create a therapeutic, and because of that are putting money into it and allowing companies to form therapeutics. And as Becky stated earlier on, that the research going on in AS is going at a dramatic pace, a very increased pace, and we wanted to use the momentum of gene therapy to be there as well, and use gene therapy to the momentum that's been shown to create a DNA therapeutic for Angelman syndrome. So Agilis is really at the intersection of a lot of enabling capabilities. We have the scientific expertise. We're specializing in gene therapy. We have the expertise of scientists like Dr. Weber and Dr. Nash, as well as others, experience in the rare disease space. We have tremendous partners and advisors on our staff, who have experience in the rare disease space, have experience in synthetic biology, have experience with DNA vectors, with gene therapy. So we're able to move it forward efficiently and appropriately. We also, work with organizations such as yourself to move this forward. It's invaluable, the information you bring, the questions you ask, the passion that you have for getting a therapeutic, and that is very helpful for us. And also the progress in gene therapy. With all the things that have happened, it's not talk anymore, it can be action. And that's why we want to be involved and move our therapeutic forward. This is a quick snapshot of our pipeline where we have a number of different areas that we're working on. Angelman is one of the main areas that we're working on, along with Friedreich ataxia and another clinical stage that we're not announcing right now. But Angelman and the CNS disorders are ones that we're concentrating on and are prioritizing right now in our pipeline. So let me give a little tutorial on what is gene therapy. Everybody knows, it sounds very, sci-fi and all this, but really there's a defective gene. You need to replace that defective gene. So we find the gene. How do you get that gene into the cell that's needed? Right now there are viruses that everybody has in their body. They're safe, that you can use to deliver that to cells. And either you deliver it to the cell and then provide the cell to the body, or you provide it to the site of action, in this case, the CNS, and allow the virus to transduce or move into the cell and then have expression of the normal protein, not the defective protein, or the missing protein in the case of Angelman syndrome. So really, it's just a matter of getting protein expression through a DNA construct into the cell that's needed. We use a vector called adeno-associated virus, which is a very safe and well-known virus. It infects or transduces dividing and non-dividing cells and doesn't get integrated into the genome. It stays as an extra chromosomal piece of DNA that then expresses the protein of interest. So you don't worry about the integration into the genome and what might happen with that. The nice thing about this is there are multiple variants, serotypes of the adeno-associated virus that can target different cells. So we've been doing a lot of evaluation on the different viruses, different serotypes that can target the cells that we need for Angelman syndrome. Up to date, there have been no significant adverse events with any of the therapies that are using adeno-associated virus. So it's very safe, it's well tolerated, and it offers good cell targeting. So let's move into Angelman syndrome. This is somewhat of a rehash because Becky gave a great overview of Angelman and the causes of the disease. But essentially, through imprinting, you essentially don't have the paternal allele. You have the maternal allele in the brain. In the body, you have both alleles being transcribed. But in the brain, you only have the maternal allele. And when that becomes deleted or mutated, you end up with a lack of UBE3A gene expression or E6AP protein being produced, and you get Angelman syndrome. So the molecular pathology of Angelman syndrome is well known. You lose through deletion or mutation the UBE3A maternal allele, and therefore you lose the expression of the ubiquitin E6AP protein. And with the reduced expression of the UBE3A gene expression and E6AP protein expression, you end up with a decrease in neuroplasticity, a decrease in AMPA receptors, a decrease in the synapse efficiency and activity, and therefore impaired cognitive function that you see in the disease of Angelman syndrome. What's nice is that there's no morphologic pathology. In other words, as Becky was saying, in the adults, it's not that you don't have a heart or something like that. The cellular machinery is all there. You're just missing the protein that's needed. And the phenotype appears to be biochemical only. So if you can replace the protein, the E6AP protein, you should be able to restore function. So for gene therapy at Agilis Biotherapeutics, we've licensed with the University of South Florida, Drs. Weber and Nash, the worldwide exclusive rights to the Angelman syndrome gene therapy. The pioneering work that Ed Weber was able to do in the mouse model convinced us that and we felt gene therapy, but that showed the proof of concept that it would work in not only developing, but also in the adult animal, proving that there was no morphological insult, and you just had to replace the protein. And the work that he did was published in the daily paper in the PLOS ONE journal, and it showed that you could rescue the cognitive defects in a mouse model of Angelman syndrome. So gene therapy for Angelman syndrome, essentially, on the left-hand side of the slide, I show the UBE3A gene, which I've described, and an AAV capsid, a safe adenovirus. I should say that most everyone here has some serotype of adenovirus in their body already, so it's not something foreign to the body. Essentially, we'll be delivering it. This would be delivering to the CNS, looking at delivery through different mechanisms that you can get into the CNS tissues, either through the CSF or other mechanisms. And then those will be using the transduction or targeting ability of the adenovirus, be able to get to the cells that are needed for cognition, movement, seizures, things like this. So it's been in the work that Dr. Weber showed, he showed that the E6AP protein expression, the expression from the UBE3A gene, was normalized in the hippocampus. The hippocampus is needed for learning and memory. He was concentrating on the cognitive effects. He showed that synaptic plasticity was improved, that you could see the synapses were working, the neurons were working and functioning much better, and that he saw associative learning in the memory phenotype was recovered in these mice, showing that the E6AP protein was functional, had the ability to work in this model. So at Agilis, what we've been doing is working with Drs. Weber and Nash as collaborators, and have moved to the human UBE3A rather than the mouse UBE3A. So making a therapeutic with the human UBE3A gene construct. And we've created the human UBE3A construct. We're working to optimize different portions regulatory to get the optimal expression of the E6AP protein. And I show the construct here with the different elements that we're using. And right now, we're actively working with both labs and looking at testing different AAV capsids to find out which ones deliver. We're looking at evaluations. We'll be using the AS mouse model, the similar model, but expanding on it. Using the human gene, but expanding on looking at how you can more broadly affect the different parts, such as seizures, such as movement disorders. But looking at learning, memory, neuroplasticity, right now in the lab we're doing all these experiments, and they are ongoing as we speak. So we've started the work. And hopefully, we plan to have a lead candidate selection of a gene therapeutic that can go into clinical development in 2016. So I'd like to end the science part of the talk now and turn it over to Jody Cook, my colleague, who will talk more about the development of this lead candidate into a therapeutic. So thank you.
Okay, great, thank you. Thanks, Greg. Thank you very much. As Greg said, he runs the science portion of the company. We're a small company, so we're all very actively involved in everything. And he said he'll have a lead candidate by 2016. Remember, we just licensed this and kicked off the work in July with Dr. Weaver and Dr. Nash. And I told him, I was like, 2016, that's not fast enough. Can't we have it by Christmas? So I'm with you. We have to do it right. We have to be really focused and make sure we make everything correctly. But it's never fast enough for all of us. I understand that. Let me tell you a little bit about the drug development process. This is probably relatively new to what's new to all of you. It's certainly newer to people that have never done drug development. You've heard before that maybe 1 out of 10 out of 10,000 actually get through into the process. So we're a little bit ahead of the game in that by licensing the technology and the great work that had been done by Dr. Weber. Agilis came into this process beyond the discovery phase. So we came into this at the preclinical phase. July of this year, we started in the preclinical phase. And two things you have to do together. You're doing the preclinical phase of the work. What does that mean? That means he proved it in mice. Now we need to make it for a human. So they made the human version of it. And now we need to retest that version a bunch of different ways. Is it safe? Is there a mistake? We look at it in cells. We look at it in animals. We look at it in various ways. So that's all the preclinical work that's going on. The other thing we have to start working on right now is something called process development. When you actually have a pharmaceutical that's approved for use, you have to show that you can make the same thing over and over and over again. You can make it in a laboratory, but then you have to be able to produce it so patients all over the world get the same product. That takes several years of development. So we've already started on the process development. So what comes out of the laboratory then needs to have a lot of controls put around it so that we can make the same thing over and over again. So that goes on behind the scenes while we're moving things forward. Once we get to the point where we believe that the scientists have come up with the right candidate, we believe we understand how to make this, then we'll engage with the regulators and talk about essentially what's called a pre-IND meeting, where we say, okay, we believe this is going to work. Now we discuss with them, what do we have to do? We have to do a series of safety studies and a whole series of other things to make sure that what we're going to put into a human is safe and can be effective. So we have those conversations. Once we have those conversations, agree to the plan, you execute on the plan, and at that point you're able to start your phase 1 clinical trial. Phase 1 clinical trials are safety studies. Generally, they work with some dose escalation, so you do a little bit of dosing in that, but they're really designed to make sure that what you've developed is safe. Everybody looks for efficacy signs, but it truly is a safety study. So once you get into phase 1 and have demonstrated it's safe, then you go back to the agency and discuss with them how to take it to the next level, how to broaden the population, how to show that it is effective and how it can work. So it really is typically a 7 to 10 year process to get from an idea through into a phase 3 and proof that it's available on the market. And honestly, probably 7 to 10 years in general is optimistic or pushing it a little bit, but it takes a while to get beyond just the idea phase. So that's the process that companies go through. Where we are, like I said, in Agilis, we're at the preclinical stage. We're working aggressively, committed with Dr. Weber to get us moving to the next round of studies and the process development. We hope to have the lead identified this year, this year coming up in 2016. At that point, we will launch into those pre-IND, IND-enabling studies. Many of you have, we announced that we had received orphan drug status, and many of you have been reaching out to us and sending us emails trying to understand what that means. The Orphan Drug Act was something that was passed in 1983 that was designed to promote development of orphan drugs, orphan indications. So for diseases that have fewer than 200,000 in the United States, that act put into place economic incentives to try to get companies or biotech companies to develop these products. There are a number of economic incentives there to help us do this at a lower cost. Since that has been put up, and the other thing that, that goes along with this is an ability to have the companies interact with the agency more often or at a faster pace. So for a company like Agilis, that's really important. We don't want to launch a year's worth of studies, go talk to the agency and find out, oh gee, they really wish you had done this. So we want to interact with them as much as we can early on, design the studies together so that we don't make a mistake along the way, so we don't waste any time. So we're very focused and committed to making sure that before we take the step, before we do the study or spend the money, that it really is the best path forward. And that is what the Orphan Drug Act for us has been a big benefit, will be a big benefit. Excuse me. In general, since the Orphan Drug Act has been passed, there have been over 3,000 approvals, and nearly 500 orphan drugs have been approved for sale. That's an enormous increase from before the act was passed. There were 10, and now there are over 500. So this has really opened the eyes to the agencies, organizations like NORD or your organization. Plenty of organizations, rare disease groups are combining and really making an impact into the legislatures, as well as bringing awareness to the public. There are thousands of orphan diseases, and together that's a very large number. So there's a lot of companies working on this. So, did it switch? So for Agilis, we announced this. We were granted this designation in October of this year. It'll provide financial incentives to develop our treatment for Angelman syndrome. And really important for us, it'll provide more frequent interactions with the regulators and potentially speed our development and our entry into clinical trials. And that's a really important thing for our company. So our next steps for Agilis, as Greg had mentioned, we are working in the laboratory to optimize our DNA and delivery. Dr. Weber showed how to do it in a mouse. We're looking at, are there other ways, this piece of DNA, can we put different things around it to target more specific cells? Your scientists have done a great job identifying what's the problem. So now if we can just tweak what we have already to maximize the potential benefit, that's what we're doing in the laboratory right now. That should be completed in 2016. And then we'll move into what's called safety studies, where we will dose at higher and higher levels in an animal model and determine what we believe will be a safe dose for the human. And obviously the goal is to give the safest dose that will give the most benefit. A safety study could take 5 months, it could take a year. Again, it depends on what the results show up until that point and how we have that conversation with the regulators. And then we are going on with the manufacturing development. There are a number of different places that have, over the last decade, worked out how to manufacture gene therapies. These are biologics. It's not quite as simple as just making a pill over and over. There's a lot of reaction going on in making these products. So it's taken a while, but now many companies have worked out how to do that. So now we need to modify that process for this specific one for the treatment of Angelman syndrome. We are also concurrently in the areas of trying to understand what's the best route of administration for the gene therapy product. The disorder that we understand is mostly in the central nervous system in the brain. So we're looking at different routes of administration. We're talking with neurosurgeons, neurologists, the scientists in this room to help us understand what is going to be the best way to deliver this to your children and family members. Is it going to be maybe like an epidural, a lumbar puncture into the CSF, cerebral spinal fluid? Is there other ways that we can deliver this that will provide the most efficacy? We are also looking at what should the phase 1 clinical protocol look like. And I know that's not coming right away, but we need to understand what to do and what's the best thing to do. There needs to be outcome measures to evaluate improvement. And you heard about that in the previous talk as well. What are the right things to measure? A lot of clinical trials end up failing because they didn't measure the right outcome, or they didn't know what the right outcome was to measure. We want to make sure that we start today to figure that out so that we at least de-risk that as much as possible. And I'm going to talk about that a little bit more in just a minute. We have going to engage regulatory discussions, and then you open something called an IND, which then allows us to move into human trials, and then obviously then into a phase 1 human clinical trial. So let me just tell you a little bit about something that I'm very excited about and have really been diving into the last few months. I'm calling it the Outcome Consortium Mission. For the Angelman groups, the Angelman syndrome, we need to establish reliable markers, clinical measures of Angelman syndrome that can be used for therapeutic development, evaluation, and registration. That's different really from a test that you would go to your doctor and get, or an educational evaluation to put your child into special services or get extra help. This is really something that needs to be measurable and repeatable, and you can put statistics around so that when companies, whether it's Agilis or any company, goes in to say, we have a treatment, we believe it works, it can't just be because the parents say it, the kids are better, or we think it's better. We have to show scientific evidence that it works. So we need very clear outcome measures, biomarkers to do that. So Angelman syndrome as a group needs to have those for whether it's us or any other company down the road over time, you're gonna need to have those measures. And we've already heard about it in the first talk that they're looking at what are the exact measures that we need to use to find an outcome that can get a therapeutic registered. So the goal of this consortium mission would be to invite all stakeholders to participate in the project development. I've already been to, thanks to Terry Jo at Vanderbilt, we've been to Vanderbilt. We've had a group of scientists together. We've been to South Florida. We've seen Ron Thiebaert in Boston. We're going to see Ben Philpott and the UNC team next week. So I'm starting by traveling the country, and I've been talking to the folks in Australia. Megan, I've talked to her several times as well. So we're really trying to get all the various stakeholders, the clinicians, the scientists, to at least open their eyes to, and they've all thought about it individually as I go around and talk to them, that these are really important things. So we want to get everybody excited about it, and then pull them all together and convene a planning meeting. So hopefully early next year, we're going to convene a planning meeting to discuss this short-term and long-term outcome measures. So we need some that maybe for those of us that are entering clinical trials in the next few years, and then maybe there's a global Angelman syndrome outcome measure that gets developed for something that enters clinical trials in 10 years. But we need to raise awareness, get participation, get funding around this, and then execute this plan and continually update on what those measures are. Those are the things that can happen right now, today, so that when any of our therapeutics enter into registration process or talk to any of the regulators, they've already been validated. They've been validated by the community, by the scientists, by the clinicians, and so it's much easier. It will speed the process for any of us to get therapeutics. Some of this has already been started, but certainly we'll want to rank order symptoms that are important to families and caretakers and clinicians, and I know you've already been started on doing some of that, but really to develop effective therapeutics, it requires the families and the patients' interactions, because you know your disease better than anybody. Even the clinicians and scientists, we may say, this is what we think is highly important, but then we have to hear from you. And so if we do drug development work that's inclusive of the family and patients, you end up with a therapeutic that is much more targeted to the big needs of the community. So all stakeholders need to be involved. We need to find those sensitive objective measures. If they're not there, we need to identify them, plan and budget, and then we can raise funding and execute the plan. And you've done a fantastic job of already moving things forward, but this is something else I think that we can work on. I've already had conversations with people at the NIH that are very interested in funding and helping to make these programs move forward, and they're very excited because I tell them that there are very active patient family groups that are part of that, and those are the kinds of things that they enjoy moving forward and helping to fund. So I just wanted to have a few, I put in a slide here called Common Questions. Many of you have emailed me, and I look forward to actually meeting you, and thank you very much for sharing your stories and your photos of your beautiful children. And probably the top 3 questions I'm getting right now are, will your child qualify for clinical trials? We don't know yet at this point what the inclusion-exclusion criteria are, but like all clinical trials, you start with something. You try to make it as tight as possible because you're looking for getting the first group through that gives you a good result. But that means that very quickly behind that, you follow up with broadening those inclusion-exclusion criteria. So we are not planning to ever exclude anybody. The therapeutic idea is to treat the entire population with AS. When will it be available? Again, I really can't answer that question. I wish I could. I can give you the near-term timeline, which we've talked about. We hope that our science will develop the lead candidate next year, and then we will begin the conversations with the regulators to get to what are the right set of studies that we need to execute. And then is there anything I can do right now? And really, I think you're already doing all great stuff. If you can, I was talking with Megan in Australia, and I don't know when that's going to happen, but in the very near term, they're launching a registry, a patient registry, which I think will be fantastic. So join that when that happens. Keep very good medical records if you can. If you haven't had the confirming test, the diagnosis, you can maintain or get that. And participate in anything that you can to keep things moving along. Any therapeutic that comes on the market is not going to immediately, nothing is going to snap your fingers and be everything's perfect. So if you're in therapy now, keep that going. Very likely, even with a gene therapy, you'll have improved function, but you're still going to need therapy to teach and make progress from that. So nothing is going to be a snap and it's all done. So I would say keep going. You're doing phenomenal right now. Keep up what you're doing, and we will keep you posted along the way as things move forward. My last slide here is just a picture of our team. Like I said, we are a small team at Agilis. We are 3 full-time employees, and the way that our model was set up is to be very collaborative. We have an excellent group of scientific advisors, and we use them regularly. We have Dr. Weber, the group at South Florida. We have the FAST organization, and one way that the Agilis investors decide when they're going to take on a new disease or have something for us to work on is there enough support in the community to make this happen? And you should be very proud of yourselves, because the answer is absolutely yes in Angelman. And that was a big reason. Dr. Weber's science is outstanding, but if this group didn't exist, it's likely we would not have moved into this space. So you guys are phenomenal for doing that and for being active. When we were investigating whether or not to take on Angelman syndrome, I sent an email to Paula, and I happened to be in Chicago for personal reasons. And she's like, okay, I'll meet you. Where are you? I'll come talk to you. And now that I know Paula, as everyone else does, once she's got you in, there's no going back. So thank you, Paula, for meeting you and for getting us all excited and interested. But I can promise you that we're a small team, but we're a very committed team. And we're committed to rare diseases. Friedreich's ataxia was our first indication. We joined them for many of the same reasons as this. And you guys actually were our second indication we picked up. And quite honestly, this one has moved quite fast. And I promise you that we will keep it going as fast as humanly possible. And that is because of all your input. So thank you for having us here. Thank you for welcoming us into your group. Sorry, I have a... okay, so we can open it up to questions.
Okay, again, we were going to ask you
You
to
wanna
come
come
to
up
the
here?
microphones.
Why don't you just stand up?
And
Yeah.
also, we had said if you're on the live feed, you can tweet us or you can go to the Facebook page. There's also a conversation going on the live feed page. You can ask questions there as well. So we'll start over here.
Hi, good morning. My name's Colin. And really, I've got a funding question for you and for Dr. Levin, really, just to give us an idea of the amount of money that you actually think you're going to need over the next 7 to 10 years to get to the point where you can actually deliver a drug. So just, I mean, have you got it? I assume not, because you were talking about funding becoming available during the process. And then for Dr. Levin, I mean, I assume you're on a shorter track, therefore need less money. But again, it would be helpful if we could hear from you the sort of rough quantum of funding that you're going to need.
Yeah, have him go. No, yeah, have him go because he's shorter track. And he's brought more drugs to market than I have.
Well, so I have a principle: don't ask other people to put your money into a company unless you put your own money in.
Fair enough.
That's number one. So we did. Me and my family put in $5 million last year at the beginning in August, and friends and others. And then in August of this year, and Matthew as well, the management of Ovid invests in its own company. That's number one. Number two, that was just the beginning. That was to prove that we could actually collect and be ready to help people. And in August of this year, we raised about $75 million. So we have more than adequate money to bring this drug to the marketplace.
Okay.
And hopefully we'll do that successfully. But again, in the August fundraising, again, the same principle. Put your own money up. Don't ask anybody to put other money in. Now, the money we have is not venture capital. It's not quick money. It's not money that wants in and out. I picked it very carefully. These are people who really believe in medicines. They must meet the philosophy that we at Ovid have. And if those of you care to visit us in New York, and I think, Alison, you have, and I know that you have, you'll know that we don't live in fancy offices. Yes, I have a tie and a jacket and a suit on today, but that's out of respect for you. I am, without a doubt, the oldest person in our building. We live in a WeWorks. WeWorks, for those who don't know it, is we have everybody crammed together, 6 in a room. My desk is that size, and most of the people in there are entrepreneurs. So we're investing our money in this, nothing but this.
Okay,
so
that's helpful. Thank you.
Yeah. The Agilis team was started, actually it was a purposely formed company in synthetic biology, in particular gene therapy, by a group of family investors, mostly, that had a mission of using synthetic biology to do something very meaningful. And they worked with a company called Intrexon Corporation, and R.J. Kirk has done a number of very successful biotechs, and put something together in the very beginning with some key investors and who are on our board of directors right now that are committed to doing this. Financially, where we are is that we have enough money to get us to major milestones. And in all biotech drug development companies, you don't necessarily pull it all in the very beginning. And as you make progress, you bring more money in. The current investors are highly committed to this, personally committed to this, and will continue to put their money into moving things forward. So I'm honestly, we were talking about this the other day, I'm not really worried at all about making the next round of funding when that becomes necessary. But we are, and like you mentioned, ultimately it takes a lot of money to bring a drug to market, particularly from the very beginning. But as we make progress and as we see positive signs, the money is very much there and available.
So
Okay, thank you.
I just want to say from the community standpoint too that Jody took you very nicely through the process of getting a drug to trial. What we're doing when we're asking you guys to continue helping us raise money and things like that for FAST and other organizations is we're trying to fund the basic research that's going to provide those preclinical data, that's going to provide those targets that then the pharmaceutical companies can take through their pipelines. So I don't think anyone in this room needs to worry about raising money for The companies, they can do that on their own. They have their own ways to do that, and they have a lot of places to go for that we don't even have access to. So we're not going to rest until we have multiple therapeutics for Angelman syndrome so that every single kid has something that works for them. The last thing we want is to have something that works really well and 10% of our kids are allergic to it or can't take it or whatever. So we're going with the basic research. We're still looking for all the things we can do so the pharmaceutical companies have something to do with it. So that's just my point for this.
And can I just make one more comment on that? This is in my view, in our view, this is a pre-competitive space. We're not in competition with Ovid at all and other companies. It's not, there are no indications where one company gets one treatment and that's it. It will take a number of different, maybe a cocktail of treatments or various varieties of treatments from multiple companies to cure this problem. So this is not, there's not, oh, I like that company or not that company. We're not in competition. At this point, we're looking for the first therapeutic and then the second, and it's going to be a lot of therapeutics before we get to where we need to be. Go ahead, thanks.
Hi, my name is Sharon, and I want to thank you for investing in the hope we have for our children. My question is this: you mentioned that you've achieved long-term expression in non-dividing cells and wanting to optimize the levels, and obviously the initial part is trying to get enough expression in all the areas that it needs to occur. But I'm wondering if you're also looking at regulation for overexpression.
Right now that we're looking for optimal expression, so as you said, in the different cell types. For overexpression, in vivo, a lot of times, you have to see, do you really get enough expression? And that's the key. We are looking at different ways, though, and have discussed, what are called mammalian switches and things like this if you need to lower the level or remove the gene or whatever, a safety switch of some sort. We are discussing that. Right now, our primary goal is to get something that expresses enough.
Thank you.
Hi, my name is Kathy, and my question's kind of elementary. You, in your presentation, you referenced E6AP or something like that, and all the stuff that I've read talks about UBE3A creating a UBE3A protein, so I kind of wanted to understand the difference between that and the one you talked about.
There's no difference. E6AP is the UBE3A.
Oh, okay.
The protein that's produced from the UBE3A gene.
It's just a different name?
It just has another name because of how it was discovered.
Okay, thank you.
Anna?
Hi, my name is Anna. My son Aiden is 10. My question has to do with, when I listen to these two talks, I have a hard time kind of integrating what's going on. So I understand your work is further upstream and the OV101 work is further downstream, but there are words in terms of learning and potential, and then there are words in terms of tonic inhibition. So how do these two efforts kind of come together?
We're trying to fix the broken gene, essentially, and it would be we're replacing what was broken so that the expression of the protein occurs and all the natural functions come back. So we're at the level of the gene. Let's fix the gene, and then all the natural functions should come back. Versus or in a different, yeah. I don't know what to say. Sorry, I won't speak for you.
So yeah, it's a great question. We believe that if your child had been born with a healthy copy, without the deletion, without mutation, it would be a child without Angelman. I think that's the understanding we all have. And so the hope ultimately would be if that you go in and intervene and put the healthy copy in at the time of conception. Remember, it's important. We don't know from certain animal studies, we may not be able to actually get 100% recovery. So as a physician, as a practicing physician, we never use the word cure in medicine. In fact, that's something that we're all dying, medicine advances through incremental mechanisms, right? We make small leaps and those ultimately add up to something that's really revolutionary. But there's very few changes in medicine that are paradigm shifting, that are totally disruptive, that cure. So we're looking for incremental steps. ultimately, the approach that Agilis is taking, they would ideally like to be able to intervene in utero, right at the time or early on conception. We now have tests that, in fact, we can isolate fetal DNA from the blood, and we can screen for Angelman, of certain, the microdeletions at least, during pregnancy. So that suggests that you have the opportunity, as science advances, to intervene at that earliest stage, even in utero. And that's the hope in the future of gene therapy and other genetic approaches, gene editing, other approaches that can create recovery. Our approach right now is to say, every one of you has a child, or those of you in the Angelman community, has a child who could be helped. If we have a medicine that we believe can help you at some level, we want to get that to you safely and effectively, and we want to make a difference in your lives. And small gains in many symptoms can translate to enormous difference in terms of quality of life. So that's our strategy now. We're very interested in the biology of this disease. We would like to make revolutionary changes. We'd like to be able to talk about, use words like cure paradigm. But right now, I think the goal for us to say, we want to be able to help you, we want to do it well, and we believe we have a drug that can do it downstream of the gene. In other words, as you mutate that gene, multiple things downstream change. We have seizures, not simply because of that. And so the goal here is to say, we have a drug that we think can help you, would like to get it to the clinic and do it fast.
So just
if I may make just a broader comment. So having seen many, many therapeutic areas develop, one of the most important things is to take note of what you said earlier on, is that many drugs are complementary to begin with. And the voyage that you take here is a voyage of understanding the biology, understanding truly, we think we know the answer, we may not. Sometimes even in the most extraordinary areas, we thought that we knew how to cure infectious diseases. In fact, the pharmaceutical industry was so arrogant that it decided in approximately 1980 to stop research in antibiotics. We've cured it, it's all done. Nonsense. Bugs are really smart, and in fact they've now come back. So as we look at Angelman's, I think what I can truly say is that every single approach that we adopt gives us more knowledge, number one. Number two, yes, there's a period of time. I don't know how long the trials are that take for gene therapy, and I don't know truly at this stage. I will come back to you next year and tell you exactly how long our trial are, because yes, we are much further ahead. However, it's my firm belief that these therapies will be complementary. It's my firm belief that as we go into it and we learn from your children, that there will be lots more to be learned downstream. And during that period of time, we also hold the hope, and this is what I really believe is important, is that somewhere along the line, we'll catalyze just a tremendous amount of new thinking about what are the basic disorder, what are the ways of approaching this. There were many proteins that Becky showed on that pathway. I'm not looking for a magic bullet, I'm looking for a medicine. And we need to be open to the fact that there are different approaches to that. And I can assure you, I'm certain that I know we are, and I'm certain that all other companies entering into this are doing, and if they aren't, beware.
Thank you.
And definitely, I want to second that, Jeremy, that absolutely, this is to cure Angelman will take more than one therapeutic. There's going to be differences. We don't know all the biology. So we want to make sure that we have enough therapeutics to move the therapeutic benefit forward.
Laurie?
Good morning. My name is Lori, and I have an 11-year-old son named Josh with Angelman syndrome deletion positive. I never thought I would try to immerse myself in my leisure time in science before him. So, so if this sounds, on December 1st, I was reading an article from BBC News on the difference between gene editing and gene therapy. And one of the things that they said is that there's no way for scientists to know where the gene will end up in gene therapy when they send it in with the vector. So does that potentially mean that if you sent in the vector with the gene therapy, that it could be different in every patient? Or is it kind of like the majority of the patients, it would go to the right place, and some of the patients, it wouldn't? I mean, I guess I don't understand how that works if there's no way to know where that gene is going to end up.
That's a good question. That's one of the reasons, I mean, when I talked about integrating and non-integrating, when you integrate into the genome, there are specific sites, but you're not really sure where, and that was an issue. With the adeno-associated virus, you're looking at getting it to the correct cell. It will stay in that cell and produce protein, but it won't integrate. It's been engineered so it's safer and won't integrate. Okay. What you have to worry about is the cell that it gets to, and that's where we're looking at the what's called tropism or cell targeting to make sure you can get the piece of DNA into the cell so it'll use the machinery to produce the protein but not integrate into the genome.
And a lot of that depends on how you deliver your therapeutic as well. And like Greg said, these are non-integrating. And a lot of work that we've done even before we joined into this community was what type of viruses target what cells in what part of the body. There are some viruses that are really good for the liver. We don't want to be in the liver. There are some viruses that are better for different parts of the brain. So the scientists over the last 20 years really have been working out which viruses target which cells. So as we select that, then we do in a very, and Kevin Nash is doing a lot of it, a very exhaustive evaluation of once we've given the therapeutic, where are we sure it hasn't gone to the wrong places. So before we get to a human, we will feel very confident in animal studies that it absolutely targets the right place, but not the wrong place.
So is it typical then that if you've tested it and in the testing you've done, it's going to a specific cell per se, that it would generally most likely do that in everybody once you're realizing where it's going, that it's most typical that that would happen that way?
Yes, that's what we believe, yes. Yeah.
Thank you.
Okay, we're quickly running out of time, so these are going to be the last two in the room, and I have one from online from our live feed. With your streamlined approach, is there any estimated time frame on when phase 1 trials could possibly start? Give us your worst case scenario.
It is live streaming, so I'm sure that our board might be online, so I can't throw a date out there that I'll be held to. So, like I said, it's 2016. If we have the candidate targeted 2016, if we say safety studies will take another year, then it's developing the work, and then we could move into humans. So a couple years would be a reasonable estimation without putting a firm stake in the ground. But every time we talk to you, every time we interact, every time we will give you our next best guess. So our next best guess right now is that the lead candidate will be next year.
You've been standing longer, so why don't you go first?
My name is Stephanie, and I was just, I don't know exactly how to ask this question, but my son is Leo, he's 8, he has a loss, and he also has a gain. Now, is this gonna affect him being a part of any trial because he has that gain in his genes as well?
You know where the gain is?
Yes, extra X chromosome.
Yeah, we have quite a few. Her son is not the only child that we have in our community that has been doubly genetically blessed with Angelman syndrome and something else. Do you have some thoughts on whether that becomes an exclusion criteria for a trial?
As far as Angelman, I wouldn't think so, but we need to be, fairly stringent on what the initial inclusion criteria will be. But in general, I wouldn't think it would have any effect on a treatment.
Okay, thank you.
It'll probably be dependent on the trial and the drug, but I'm in the same boat with you.
But in the end, I don't think it'll make any difference.
And Stephanie.
Hi, my name is Stephanie. I also have a child with Angelman who's 11. But the first thing I have is a comment. 10 years ago, we thought, we've got kids with Angelman. What are we going to do? How are we going to survive? And never would we thought we would be here 10 years later, let alone here with 2 companies that not only honor 3 companies that honored the science and the human aspect of all of this. I remember talking with Dr. Weaver almost 5 years ago about all of this, about how we wanted our kids to be treated as human beings and not, unfortunately, the mice that we're studying. And I just want to thank you for respecting that, because it's very important to us that our kids remain our children and that innocence remains and they don't become a science experiment. So thank you for taking that under consideration. Having said that, researching the data, are you planning on utilizing data that's already been measured in other trials or in other research mechanisms, or are you looking at trying to find new metrics that are specific to Angelman syndrome so we can better evaluate the therapeutic that is being put to clinical trial, something that's a little bit better than the Bailey scales, for example?
Yes and yes. Yes, we are absolutely going to look at all the data that's been out there. In fact, we have just engaged with Dr. Bird and Dr. Hahn to accelerate pulling all the natural history data into a usable, queryable database that will be available to any company that needs to do research. So yes, you should never throw away old data. Always use it as much as you can. As we get smarter and understand better questions to ask, we can go back to that data that will be in a database and query it again. So absolutely, we're going to use that. Any studies that have been published with the data, we want to use that as well. The Baileys and the things that have been used over time, for sure, we will use that data. And then, yes, on the side of, should we develop more? When we were at Vanderbilt, we were interacting with circadian rhythm scientists. We were actually interacting with scientists in the auditory side, which is my background, for various evoked potentials for hearing and background noise. And so we're trying to borrow from other areas, other scientific areas that also Angelman kids have disorders or have symptoms of. So we don't have to recreate a new test. And then finally, I know Dr. Weaver's going to talk about it later today, I think. We've been talking with him as well about what is the right scale that really identifies the Angelman syndrome as a whole. And maybe that's a brand new development effort. And I think that's really important as well. So yes, yes, and yes. We're going to use old data, medium term. So as therapeutics progress through this, there will be needs for all those different scales in all the different areas. So we're trying to lead that effort to get it organized, to make it move faster. But certainly, you guys are going to pick that up, and the scientists and clinicians will pick it up and run with it, so that when any of us end up in front of the agency, we have not only the idea that everyone says, yeah, we have this problem, but here are a number of different scales to prove it. Thank you very much. Thank you for your comment as well.
All right, let's thank
you,
the
everyone.
people from Agilis. And we are miraculously on time. So we have a 15-minute break, so get up, stretch your legs, walk around a little bit, but then come back because we have another company that wants to tell us about something that they have in the works. That will be at 11:45. Get everyone back in the room so we can get started for our next session. So if we could ask people in the room to take your seats.
It was like this. It was like this double. Oh, okay. Sure. Well, you build it in your head. Okay. Okay, we're actually way past time, and I want you guys to hear this talk. So we're going to ask you to sit down, and let's get started with our next group that is working on something that we hope is going to benefit all of our individuals with Angelman syndrome. So Donna Herber, Mike McCandless, and Angela Poff are all here from Disruptive Nutrition, which I just love that name. And Donna's going to start us off, and I think she'll do the introductions for the people that she's going to introduce. But I just want to say that she's bringing 23 years of experience in medical science research and product development to Disruptive Nutrition, and she's going to talk to you about what they're doing in terms of getting this product together. Angela's going to tell you about the science behind the product that they're going to tell you about. And then Mike has, it says here, 17 years of experience in development and manufacturing of nutritional supplements for improving athletic performance. So I think you have a little bit of a key of what we're going to be hearing about and how exciting this is going to be. And I will turn it over to Donna.
Thank you. So as she said, I'm Donna Herber. And we've been working with the University of South Florida in collaboration on this project. So in the labs of the people that we're working with, we have as a lead Dr. Eb Weber and his student Stephanie Charlone. We are also working with Dominic D'Agostino and Also here with us today is Angela Poff, and Angela is going to go over the basic science, the preclinical work that is leading up to the product development that we're doing.
Thank you, Donna. Okay, so what is a ketone? So ketones are natural compounds that are made in our bodies during certain situations when our bodies are burning fat. So that would be any time that you're calorie restricting or during fasting or starvation, our body will start to break down those fats, and parts of that is turned into ketones. Or it could also be when you're consuming a diet that is very high in fat. Now, ketones are actually a very efficient energy substrate, and they can serve as an energy source for pretty much all the tissues in the body. And importantly, they can actually replace glucose as the brain's primary fuel. So you may have heard of glucose before, and we know this is a really important energy for the body, but ketones are an alternate substrate that our bodies and our brains can use. And they're actually extremely efficient energy molecules. They actually kind of give you more bang for your buck in terms of how much energy they make compared to the other energy metabolites like glucose. And so we can kind of consider when the brain is running on ketones, we're enhancing the energy reserve capacity of the brain. And that's really important, even in a healthy individual, but especially in an individual with some kind of neurological deficit. Because the brain is a very energetically active organ. It requires a lot of energy. But ketones are more than an energy source, so they actually have very important roles in signaling and communication in the body, and they're very protective, especially to the brain. So they're anti-inflammatory, they inhibit inflammation in the brain, and they also will decrease the amount of oxidative stress in the brain and enhance the body's own protection or antioxidant defense systems against that kind of damage. And they also improve motor performance, and we think this has to do with that efficiency of the energy molecule. So ketone supplementation, I've just told you about some of these really nice beneficial qualities of metabolizing ketones, but I told you our body only makes it in those kind of nasty situations like starvation or fasting. So what people are doing is trying to find a way where we can orally supplement ketones so we don't have to rely on those dietary restrictions to get ketones in the body and get those beneficial effects. And so people are developing these ketone supplements. They are a source of calories, so they're a calorically dense molecule. And again, I want to emphasize this is something our body makes naturally, but we're just supplying it from an exogenous dietary source. This can give us a dose-dependent elevation in our blood ketones. So you take a certain amount of the ketone supplement and you pretty much instantly within 30 minutes are going to see an elevation in these molecules in your blood. And it can provide pretty sustained duration of this elevated ketones. And we can get the elevation of all three of the ketone bodies, beta-hydroxybutyrate, acetoacetate, and acetone. And this is just some human data, a single administration showing that you can get this elevation in ketones. So I'm just going to show you some data that has come out of Dr. Ed Weber's lab at USF in using the mouse model of Angelman syndrome that you've probably heard about before. This is a UBE3A maternally deficient mouse model, and we know it recapitulates a lot of the symptoms that we see in human AS patients in terms of they have motor deficits like ataxia and balance and coordination difficulties, as well as some other abnormal motor behaviors. They also exhibit some cognitive deficits. They're prone to seizures, and they have impaired learning and memory. So in this study, the animals were given a diet where 10% of the diet was replaced by a ketone supplement, so it was orally administered. And first things first, yes, we do see an elevation in those ketones in the blood of these animals, both beta-hydroxybutyrate here, and then also acetoacetate. And this is particularly important because acetoacetate, that ketone, and its derivative, acetone, one of the other ketones, are the ones that have been pretty extensively studied and shown to have pretty potent anti-seizure and anticonvulsant effects. So we do see an elevation in these molecules in the blood. Now, here we did a few studies looking at how these ketone supplements would affect motor performance in the animals. This is a study that's called an accelerating rotarod. Basically, you put a mouse on a rod that's slowly rotating, and then over a course of a couple minutes, it's speeding up. You see how long that animal can walk on that rod. And of course, it's going to be indicative of its balance and its motor coordination and function. And so what we see, animals that don't have the disease, they can stay on this rod and walk on it for a long time. Untreated Angelman syndrome mice are impaired in their capacity to do that. But when we give the ketone supplement, we see an improvement in this behavior. The animals are able to walk on that rod longer, meaning that they have better motor performance. Two other techniques looking at motor performance that were performed on these mice. Here we have the hanging wire test. This is essentially we allow a mouse to grasp a little wire with their forepaws. We see how long they can hang on. So this can be indicative of muscle strength or muscle fatigue. And so what we see is that the Angelman syndrome mice, of course, they're not able to hang on to that wire as long as their undiseased litter mates. But then when we treat with the ketone supplement, we can rescue some of that deficit, and they're able to hang on to that wire longer than those untreated Angelman syndrome mice. And on the right here, we have the hind limb clasping severity score. So in mice that have neurological disorders, when you hold them up by their tail, they retract their hind limbs, and we call that hind limb clasping. So it correlates with the severity of their neurological deficit. So what we see is that in the undiseased animals, they don't exhibit this behavior because they don't have any neurological deficit. When you look at the Angelman syndrome animals that are not treated, they of course exhibit this behavior. And when we administer the ketone supplement, that is rescued to a certain degree. They don't have as severe hind limb clasping, indicating less of a neurological deficit. Here, we're looking at a few tests of learning and memory that were performed on these animals. On the left is a fear conditioning test. It's essentially a test where you teach a mouse that when they hear a certain sound, they're going to get a mild shock on their feet. They're standing on a grid that delivers a shock. You come back at a later time point and see if when they hear that sound again, they freeze. That freezing behavior means they remember what's coming, that shock is coming. And so it's a way to tell if the mouse had learned what that sound meant and then remembered it. And so what we see is that the Angelman syndrome untreated animals have an impairment in that ability to remember that sound. But when we're treated with the ketone supplement, they actually responded similar to the undiseased animals. And then on the right, we have the novel object recognition test. And this is just where, so mice will naturally want to explore a novel object over a familiar object. And so if you introduce some objects to mice, come back later, replace one of them with something that's new, and you measure how much time they spend exploring those things and see, were they able to remember that this one object was familiar, or did they not learn that? And so what we see again is that in this study, the animals that were treated with the ketone supplement performed similarly to those that didn't have the disease. Here we also looked at the effects of the ketone supplements on seizures, and we did two types of seizure induction. On the left, canic acid, it's a chemical that's used in studies to induce seizure. You can see that the animals that were treated with the ketone supplement at various time points following the administration of this chemical, they exhibited less seizure activity compared to their untreated litter mates. On the right, we're looking at audiogenic induced seizures. This is just a seizure that is induced by a certain sound. And so what we saw was that in the untreated Angelman syndrome animals, about 84% of those animals exhibited a seizure when they were exposed to this sound. But that was reduced by about 50% in the animals that had been treated with the ketone supplement. And not only did we prevent seizure in such a large portion of those animals, we dramatically increased how long it took for those animals to cease. So we delayed the onset to seizure. They had to be hearing that sound for a lot longer before they actually ceased. Okay, so So these were some of the studies and the findings that we came up with. We were able to elevate the blood ketones with this exogenous ketone supplementation. We reduced seizures, we improved motor function, learning, and memory in this model. We have a few ideas of why we think this might be occurring. We know that it probably has something to do specifically with elevating acetoacetate and acetone. These are those ketones that have been shown to possess intrinsic anticonvulsant properties. We also saw that this administration of the ketone supplement can increase the amount of GABA in certain areas of the brain. So as you probably know, that it's thought that there is an abnormal decrease in the inhibition in the brain of AS patients, and that leads to some of their deficits. And so if you are able to increase the amount of GABA, you're increasing that inhibitory signaling and possibly is responsible for rescuing some of that deficit. We also think it probably has something to do with improving metabolic efficiency. Providing energy to run all of the things that our neurons have to do is very important and is now being studied across a wide range of neurological disorders and deficits. We're seeing that this seems to be extremely important. So enhancing that metabolic efficiency and energy production in the brain is probably also responsible. And then they have a lot of other functions that I haven't gone into today, but could also possibly be playing a role.
All right, so I'd like to go into kind of what our product development pathway is and where we are now. So again, I'm Donna Herber. Angela is with the University of South Florida. I'm with this new startup company, Disruptive Nutrition. Okay, so the ketogenic diet, Angela mentioned it briefly, and one of the things that I needed to learn about when I first started this as well, being a carbaholic myself, was about the ketogenic diet and really what all the metabolic effects were. Keto meaning blood ketones, right? So when you're on a ketogenic diet, you're naturally raising the level of these ketones in your blood and also in the brain. And that's the reason for why it's called the ketogenic diet. And when we're talking about this in a patient population, it's been used for a very long time in the epilepsy population. Very strict version of this is a 4 parts fat to 1 part other. That other can be a mixture of protein and carbohydrates. A very strict version of the diet is the 4-to-1 or maybe a 3-to-1 ratio in the diet. A more modified version that has been used as well is a 2-to-1 ratio or a 1-to-1. But in all these cases, this is a very restrictive diet. No pasta, no rice, definitely no cupcakes on birthdays. And so there's a lot of difficulties, even when you see a benefit, say in reductions in seizures on the ketogenic diet, when you have a slip, or when the patients with Angelman syndrome or patients with epilepsy have a high intake of sugar for, say, a cupcake on a birthday or pancakes with syrup on Sunday morning, that it can trigger seizures. So the restrictions on this diet can be very difficult to make it, to stay with it, to adhere to it. So what we're trying to do is develop a product that would be a ketone booster without a lot of these restrictions. Our ultimate ideal would be that, yes, you can still have the cupcake on the birthday, right? You can still have the pancakes on Sunday morning and not have these issues of going back into seizure activity or other issues that are associated with the syndrome. So it is an oral administration. Not sure about the form yet, but again, it's something that you just take by mouth. And it is a source of calories. So like food, it is a source of calories. We hope to see dose-dependent elevation of blood ketones without the dietary restrictions, that this would be rapid and sustained levels of blood ketones, and that all 3 of the blood ketones will be raised: beta-hydroxybutyrate, acetoacetate, and acetone. And these are the 3 naturally occurring ones in your body. So there are a lot of different paths that you can take a product like this. And one of the things that I was asked to provide some education, and this was for myself as well. I come from kind of a pharma background, but to understand, what is the difference between something like this as a dietary supplement, as a nutritional supplement, and what is a medical food, and how does that differ from a drug? And the best explanation I found was at the FDA's own website that was talking about, think of it as a continuum. At one end of the spectrum, you've got broccoli. you've got milk. At the other end of the spectrum, you have drugs. And somewhere in between that, we have a lot of dietary supplements, and we have some medical foods that are on the market as well. And I've circled the medical food because we believe this is the path that will work best for patients with Angelman syndrome for our product as we develop it. As this continuum goes up, you see increased amount of data that is necessary to prove what you think your product does. You see increased costs to bring it to market, increased time to bring it to market, increased oversight by the Food and Drug Administration. And so that's one of the things I want you to consider as you think, well, what are the differences between these? And another key difference is what you can say about what it does. So what a dietary supplement can be marketed as in terms of treatment claims or things like that is very different than with a medical food or with a drug. So dietary supplements are just that. Originally, they were intended for healthy people who just wanted to supplement their diet, right? Vitamins, minerals, amino acids, herbal extracts, things like that. But on the basal level, these are relatively healthy people who just want a supplement, a little bit of a boost. You have to be very careful about, as a manufacturer or a distributor of these materials, what you can say about them. You can make so-called structure function claims, memory aid, but not treatment of dementia. Okay, so there's a distinction between what can be said about these products. The safety criteria for producing these products is just along the lines of enough data to show that there is a reasonable expectation of safety. So this is kind of just moving up the spectrum, but not at the same level as a medical food or a drug. So what is a medical food? A lot of us have never heard of this before. This is a new space that not a lot of people use them, and so not a lot of people have heard of them. As we move up the continuum, the level of safety requirements for these products is higher, so it falls under what's called GRAS, generally recognized as safe, which is a higher level of burden of proof that the material is actually safe for the people who would consume it. In this case, you actually can make treatment claims if you have clinical data to prove it. Okay, so you can't go out there and take animal model data and say we can treat humans. But if you do treat humans and you see a clinical benefit, then you can actually make treatment claims, which is different from a dietary supplement. Drugs, of course, we understand that they're intended to diagnose, cure, mitigate, treat, or prevent disease. So the very, very highest of standards in terms of scientific proof, clinical proof, safety of the material, clinical efficacy of the material, high cost, and high time to market. So again, just think of this as a continuum when you're considering what it is that's being suggested. So for us, with our medical food path, we're talking about nutritional management for patients with Angelman syndrome. It is a medical food. It's for the distinctive medical needs of patients. It's used under a physician's care. Okay, so this is not something that you're going to find on the shelves at GNC. This is not something you're going to find on the shelves at the drugstore or at the grocery store. The child's physician, the patient's physician, will be monitoring their response to make sure that this is appropriate for them, monitoring weight gain, monitoring tolerability, monitoring dosage, monitoring blood ketone levels to make sure that this is appropriate. The product is very calorie dense and will be consumed orally, increasing blood ketone levels, and our hope, our sincere hope, is that this can be used with a standard diet. So here's our path to bringing a product to the market. We are at this step one. We're in the product development stage. We first started talking about this. Mike was talking to me, he'd first heard about Angelman syndrome in May of this year. Okay, so we've come a long way since May, but this is very, very new for us. We have material, we're sourcing it, we're formulating it, we're talking to clinicians, we're talking and working with Dr. Weber, but thankfully it's not a long process, but we're still very early in the process. And like I said, we do work with USF. I am located in Tampa, so I've worked with Dr. Weber and Dr. D'Agostino for many, many years, and it's exciting to be on this side of it, to be able to bring something to you that we hope will work. One of the things I want to point out is at the end stage, when we have a commercial product that's ready. There will be a lot of education that will be necessary because this is a product that is used under physician's supervision. So we'll need to make sure that the families are educated about what this is and that clinicians are educated about what this is to make this the most successful and to reach as many people as possible. So with that, I'd like to introduce our founder, Mike McCandless.
There won't be any science with my my slides, so don't get too excited about that. When you guys probably heard the word startup, it probably creates a little bit of anxiety because I think we all started having flashbacks a couple of months ago to Turing Pharmaceutical, which is the company that took the drug from $13 to $700 immediately. So I think when people see probably someone near my age getting near anything like this, it starts to scare everybody really bad. So I just want to give some quick background. I named the company Disruptive Nutrition on purpose. Disruptive meaning I wanted to cause as much chaos as humanly possible in the pharma world because I'm obviously in the nutraceutical world. And what we're trying to do is take nutraceuticals and be able to give them essentially medical claims, and that's what disruptive nutrition is about, is taking nutraceuticals that we can make medical claims with and be able to go into medical foods. As mentioned, I have over 15 years experience doing everything from funding studies, manufacturing. So when this was brought to me in May, and it has been that short specifically with Angelman's, one of the issues is getting these technologies and be able to manufacture them on a large scale, be able to manufacture them in a compliant facility, have proper testing protocols. These things have been around for a while. This isn't really that new. The problem has been being able to get all this stuff manufactured. I'm happy to say that in the short period of time that we've been involved, we are scaling production, we're building testing standards, all the stuff that I was actually quite shocked had not been done. So taking my resources from my other companies, which is in sports nutrition, and I know that once again can create a little bit of anxiety because we think of big meatheads and all the stuff that you hear negative in the press. Going to the disruptive heritage by funding studies and doing the things that I've done, we have a background in trying to do things the right way, but we got to be careful not to be in a ready, fire, aim situation. We want to get this stuff to you guys, obviously as quick as possible, but also making something that's shelf stable, that meets label claim, that will stay there for a long time. And that's a process. So just understand we're working, as quickly as we can. It's a daily thing. I have hired recently a new CEO for one of my other companies to step away to help manage this project because of how passionate it is for me. I got involved in this because my mom 4 years ago was a cancer patient diagnosed. I went into the chemo ward, saw how everybody had an extreme amount of muscle wasting. And so I'm like, well, one of our best-selling products is built around limiting muscle loss in athletes. I got in touch with Dominic D'Agostino down at USF. I was like, hey, has anybody ever researched using these ingredients before? And he was like, no, nobody's ever really looked at it. It's probably going to have negative outcomes and probably accelerate tumor growth. 4 years later, we have seen exactly the opposite. We've actually spent a lot of money looking at different research, and in that is how, as a side item, I got involved into the ketone technologies, because once people saw that we were authentic and trying to do this stuff the right way, people started coming to me about, well, hey, can you help out in these other areas using your manufacturing expertise and so on. And we've been able to do that. And the thing that I'm probably most proud of is I don't have any investors. I'm not accountable to anybody other than myself. I started as a kid in a nutrition store who thought that's all I was going to be doing, and started an internet business selling products online, and things just continually fed on themselves. And in the past 3 years, almost every major pharmaceutical company has sent a board member either to my warehouse or to find out who my angel investors were, which I don't have any. So my goal is to make these products as safe as possible and as cheap as possible. I have other businesses that take care of what I need to do. This is a personal project for me because the same therapies that we talk about for Angelman's also work in many other cases and other diseases, and one that affects my mom. So, which she went from one type of cancer to another. The doctors told her that, it was a very dim diagnosis, but she's actually still kicking around and doing very well today. So this is a personal passion project for me, and I think that's how all of you sort of get into this, is once you learn and it affects you, the money is irrelevant. It just comes about, you're just trying to help people. we're a new company. You guys don't know anything about us, and this is, I know, sort of a first impression. So I just want you guys to know, at least hearing it from me, that that's our goal. I don't know what the time frame is going to be. Just know that we're working as fast as we can with as many resources as we can to get this done. As soon as I realized some of the impacts, I immediately went out and got Donna to come work with us, and then we're working what I feel like is some of the best team down at USF. I've funded tons of studies and been around a lot of different universities. I've never been more comfortable with a place in my life as far as doing stuff. So I'm super excited. I cannot answer hardly any medical questions whatsoever, so please do not ask those of me. I will default to the women who always know more. But I'll be happy to answer any questions if you guys have anything specific about the business stuff or any of the history and stuff like that. And then I think that keeps us on time and leaves a little time for questions if anybody has any. So thank you.
Okay, so we have some time for some questions. And we have people making their ways to the mics.
Hello, my name's Kathy. And you said that this would be prescribed by a doctor or overseen by a doctor. And we do have nutritionists that manage things for our children currently. Would a nutritionist be qualified to do that?
You know, honestly, I don't know a direct answer to that. I know that when I've worked with some of the clinicians before, what they do is they refer the patient to the nutritionist. So I think it's kind of a collaborative effort, especially in the beginning when you're talking about looking at monitoring blood ketone levels, making sure and looking at weight gain, weight loss, things like that. I think it's going to be a collaboration. I can't imagine that this would be solely run through a nutritionist. I think it much like everything else that you have to do with your children, right? That it's a collaboration.
Would it be a general doctor, a general health doctor, pediatrician, or
I don't think
internal
it matters.
medicine?
I don't think it matters.
You don't think it matters?
No.
Okay. Okay, thank you.
You're welcome.
I will say the government has, when you get into medical foods, it's sort of an area for them that they're not overly clear on the rules. So sometimes when the answers become very vague, understand that's because we haven't been given tremendous amount of guidance yet. So they're still figuring this out. This is a really hot area right now as far as medical foods because it's very expensive to get into. You don't have the pharma upswing with it, but so there's a lot more attention now. We'll probably get a lot more clarity from the FDA because if you ask them outright, the answer you get will be different when you ask them a week later. So I know that shocks everybody, but yeah.
I'm Claire. I've got a question about, can you explain to me the difference, the positive negativity of the ketones as compared to like ketoacidosis, that side?
Well, ketoacidosis also affects the blood pH. So ketoacidosis occurs in diabetics, right, when their glucose and insulin levels are all messed up and then way too many blood ketone levels, but also an acidification of the blood. So this is what we are referring to as therapeutic ketosis. So this occurs naturally during fasting. This occurs naturally with a high-fat diet. So we're not expecting, based on lots of information on the diet side as well as animal data with the supplements, that there would be anything other than this therapeutic ketosis rather than the ketoacidosis. This is an excellent question because it comes up a lot, and people have heard of ketoacidosis and say, "Ooh, this is bad," but this is therapeutic ketosis. So thank you for asking that. Thank you for bringing that up.
And then, do you have information like, is it comparable to the raspberry ketones? Is that what it's called?
Raspberry ketones, do you know anything about raspberry ketones? I know they're not the same.
Yeah, they're, when we say ketones, we're referring to 3 molecules specifically that are called the ketones or ketone bodies. And raspberry ketones it's kind of confusing terminology because it goes back to the organic chemistry nomenclature of the molecules, but they're not at all related. And I wanted to add also, it's all about the dose. So I've heard ketosis, therapeutic ketosis, compared to ketoacidosis as comparing like a fireplace fire to a house fire. And that's exactly the same. You're looking at great higher levels of ketones in your blood during ketoacidosis. So
thank you.
These technologies are not currently available, so anything that you think is a cross-reference to this or whatever, none of this stuff is currently available over the counter or somewhere else, and that's one of the things we're dealing with the FDA right now.
Thank you very much. There's nothing we would love more than to be able to give our daughter normal food. That would be great. So thank you for your interest in this. I think this question may be for Angela. In those mouse studies that you showed, it seemed like in each of the things, the cognition, the epilepsy, the motor function, there were responders and non-responders, if you look at the y-axis. Did you find there were certain mice that responded in all categories and certain mice that responded in none? Or were some got better with motor but not epilepsy, and the other way around? Was it dispersed, or how did you find that data?
You know, that's a very good question. To my knowledge, that particular aspect has not been looked at specifically to see if the same individuals that respond in terms of reducing seizure also were the ones that responded in motor or learning. Dr. Weber, do you have any insight into that I'm unaware of?
Yeah, I don't think that there was any. Yeah, we didn't see any differences between the mice that were significant. So we kind of keep an eye on that to see if one set of mice do better than another, especially if we're doing therapeutic treatment. So, the question is, because all these mice are genetically similar, you don't see those kind of variations. So I've said this before in other talks, all the mice that we use, they're all identical twins. So the genetic variation has been removed out of that mouse model. So what you see in that particular genetic strain is what you're seeing. We saw good response on the group of animals that were treated on all those aspects. So there were none that did well on the motor coordination but didn't do well on the learning and memory. If you look back over the data, and it's important to say that this is all unpublished data. So we're pulling this together for publication, but it's, you guys are seeing this for the first time. So we didn't see anything that was differential in a particular mouse for one versus the other. They were treated as a group.
Great, thank you.
During the mice study, were the mice monitored before and after for medical things such as cholesterol or weight gain, and how did their diet differ when they were on the ketones as to before they started the study?
Things like blood lipids were not measured. Weight was measured, and the animals did not lose a significant amount of body weight. Compared to not treating, they stayed within a healthy weight range. How did their diet differ before? Is that what you're asking? So they were previously eating a standard rodent chow, which is about 50 to 60% carbohydrate, about 20-something% protein. So when you add this supplement, a significant source of their calories then are now going to be coming from ketones, which can kind of be classified as fats. They're derivatives of fats, but they're not one of the macronutrients. So it did alter the macronutrient profile slightly, but it was only 10% of their overall diet that was coming from the supplement. So it wasn't a major shift, really. It was definitely in the range, realm of supplementing the diet. As if a human was taking this, you would have to consider this as a caloric source and consider it in your caloric needs.
So did they gain weight while on it if they were allowed to eat their regular rodent chow?
They didn't abnormally gain weight, no.
Okay, thank you.
Hi, I'm Lauren. I have a son that's almost 4. We've had him on modified Atkins for about 6 months now. And we originally started it for seizures, but we have seen many of the gains you guys have talked about of motor coordination and memory and learning. So it's been really great for us. But my question is the hope with a supplement that you can then work back to just a very standard diet, or would the hope be to still kind of keep them on a somewhat modified but not have to be as strict?
And this is some of the things that we're trying to take into consideration when we're going to design what to do with the children in the clinical study. Mm-hmm. The hope to normal diet with this as a ketone supplement. The reality might be somewhere in between. And we just really don't know until we try. Yeah. But the goal would be a normal, although that sounds bad, right? A normal Western diet. They're like, bad Western diet. But that would be the hope.
Yeah.
That would be the hope.
Okay, great, thank you.
I'm Ann Anderson. I'm part of the Fast Fire team, so I'll talk to you in the afternoon. But I'm also a child neurologist and an epileptologist. And we routinely use ketogenic diet as a therapy for intractable epilepsy. And so we have a lot of experience taking care of those children, both on an outpatient basis and working closely with a nutritionist, but also when they get sick and come in the hospital for non-neurology and epilepsy-related problems. So related to the first person's question about who manages this diet and the children, and it's never the nutritionist alone, it's the nutritionist, and it's one specifically working with your neurology and epilepsy team, at least at most big centers. And I think you probably want to look for this when this becomes a routine therapy, which hopefully it will after the initial human studies. But what happens is these children, as you heard, are ketotic and acidotic, and they have a baseline level of that. When children and adults get sick, and children get sick very fast, as you know, as parents, and what happens then is they get more acidotic. They get dehydrated because they don't feel good and they're not eating, and eventually they end up on a pediatric floor or in the PICU. And the first impulse of those specialists is to run D5 through the IV. And we very often hopefully get consulted, and we have to intervene at that point because that can make their condition even worse, and it can also make them start seizing, so now they go into status epilepticus. So I would encourage you, even thinking about the ketogenic diet, that should be done under the guidance of your neurologist or your epileptologist, who then works really closely with the nutritionist. And I think it's probably with this therapy, it may be a more broader child neurology, not just specifically epilepsy, if we see learning and memory improve and we see motor improvement. And you may also have the therapist, physical therapy, occupational therapy involved, and neuropsychology in assessing improvement and monitoring as time goes on. So I just wanted to make that point since I was back in line with the other parents, but it was related to the first question.
Perfect. Thank you. I hope we can talk after this. That would be great.
My daughter Lila is 6, and for her whole life, she's been supplemented with Pediasure to meet her caloric and nutritional needs, mostly because she doesn't have the desire to eat or the functionality to eat. Is this supplement something that's going to be able to be given through a feeding tube, or is it something that they're going to have to be able to orally take in?
We're actually looking at multiple formats for it. We had been advised that in some cases gel cap would be appropriate because a lot of the children are used to taking those or having those administered. But no, the goal would be that we would also have a formulation for those that are tube fed because there's no reason on our end at this point to limit it.
Cool. Great.
Yeah, I'll say at this point, everything, these ingredients start as a liquid, and it's not the best tasting stuff. I'll just leave it at that. We have already converted it over to a powder, and then we're trying different versions from there. So, yeah, there's not going to be a limit on the number of ways we're going to try. We'll just have to find out what's actually feasible and what really works. But, yeah, by the time we get to the point of getting the study done, I will have as many ways possible as be able to how to take it. So.
Okay, I know we started late, so I don't want to cut this off, but I want this to be the last question because I know you're all going to come back late from lunch too. So, because I will. All right, so
okay.
We'll have you do the last
sorry,
one.
this is opening up a whole other can of worms. My daughter's 27, has had cyclical vomiting problems, like vomiting blood since she was a breastfed baby infant. Not everyone's kid has that, but stomach problems are a big part of this. When she does throw up, you will see food come out in layers from 2 days ago. So she does not have a specific diagnosis of gastroparesis. She has mom's diagnosis. And besides, serious laziness, that's one of the reasons I've never considered a ketogenic diet, because the most easy to process food are simple carbohydrates. And plus she is very well controlled seizures for like 2 decades. Would this be something that would work for someone who you wouldn't consider or has never attempted a ketogenic diet?
Well, it seems from what everybody has been talking about, in addition to what we presented, that there are multiple benefits to the ketogenic diet. And also, when we tested these supplements in the mouse models, we saw benefits beyond the effects on seizures. So motor coordination, learning, and memory. And so I would hope that we would have the opportunity to explore that so that we could see in the spectrum of symptoms that each patient has, where we can have a positive impact. But I honestly just don't know yet, but I hope so.
Okay. Well, so this is the first time ever that I've heard that the ketogenic diet affects anything but seizures. Because I know a lot of other people, you know, her peer group that have been on it and have done, not people with Angelman's, but have had wonderful, like miraculous benefits. And then a lot that had to get off because of cholesterol or all switch victim syndrome, where they, you know, they skinny away to nothing. So that's what I was wondering, could this be used then for people who you wouldn't consider putting on the diet?
I think you also have to keep in mind too that stopping seizures is a pretty miraculous thing in terms of our kids,
I know.
right? So
I mean,
sometimes it's hard to
was-
tease those things
hey, if
out
that's
for
all
sure,
we ever
right?
got our whole life, that
Yeah.
was good enough.
I guess something to that would help her with her question is, like, how quickly is this absorbed and how quickly does it change the levels in the blood?
Within 30 minutes. It's very rapid.
All right, because she's not the only person whose children have this issue with their gut, so
Sure.
that's a really great point. Okay. All right, let's thank the team from Disruptive Nutrition. Okay, and now we will disrupt our own nutrition. Lunch is actually right next door, so go grab your lunch, and then we'll see you guys back here at 1:25. So we're running a little bit late, but we really want to get started with the next part of our presentations. We have some more signs for you this afternoon from the fire team, and they're going to tell you about the work that they've been doing through the fire initiative. And we'll talk more about that in a moment. But first, we're going to bring up one of our major sponsors, and that is Vivint. And we're going to have Holly Marrow come up and tell us a little bit about some of the projects that they're doing and some of the things they're involved in. I think Holly needs no introduction because she's been such an important person in our community for a while. But everyone, please help me welcome Holly.
Good afternoon. So I want to ask just a question and kind of think of some words here. What do you think of when you think of Vivint? For some of you think hope, compassion, dedication, community, innovation, giving, and smart home technology. And you'll see that on the slide in just a couple of minutes. Vivint and FAST have stood together, standing for some of the exact same things for quite some time. We both stand for hope, compassion, dedication, community, and innovation. About 4 years ago, can you get me to my next slide? Thanks. About 4 years ago, we were introduced to each other through Facebook. Some of you remember a Facebook competition Okay, perfect. Vaguely, maybe you vaguely remember. For some of you, there was a lot of voting, a lot of voting, and after that voting, FAST was the winner of the grand prize of the Facebook competition. Just by show of hands, just because I'm curious, how many of you guys did vote? So many. Okay, awesome. It was such a fun time in my life. Got to know Paula really well over the phone, late night calls. It was really great. I want to show just a quick video that a lot of you have seen, but this is a video that really, for me, introduced me and Vivint to FAST. So if we can play that video.
My name is Paula Evans. I am the chairperson of the Foundation for Angelman Syndrome Therapeutics, or FAST for short. Angelman syndrome is a severe neurological disorder. Children with Angelman syndrome cannot speak. Many cannot walk. Most of them have debilitating seizures. Our children are happy, but they're not healthy. The happiness is the one thing that keeps us going and keeps us waking up in the morning. They have the most beautiful smiles and laughs, and that's about the only good thing about Angelman syndrome. We knew that a cure was possible. We knew that treatments were imminent, and we also knew that there was no funding in place for either one. We are preparing for human clinical trials, and the winnings from the Vivint contest would be the exact amount of money we would need to go to a human clinical trial on this first time ever potential treatment.
This is my son Joshua. He is 7 years old and he has Angelman syndrome. FAST has given our family hope.
And it was just amazing how the community came together and made it happen.
I think the Vivint Gives Back project has done something like I've never seen before. It has brought our community together in ways that not only have I not seen, but have never imagined.
For you and me, living out our dreams, we're all right where we should be. With my arms out wide, I open my eyes, and now all I wanna see is a sky full of light.
We're enormously grateful to Vivint for giving us that opportunity, and we're really excited about winning the contest and being able to immediately turn around and start changing children's lives with that.
I've seen that video about 100,000 times, and I cry every single time. So FAST won this competition and kind of came storming into our hearts. This is a picture of our CEO Todd Peterson with Joshua at Vivint when they came to receive the giant check. When I talked to Paula, again 4 years ago, she told me, okay, we're going to immediately turn around and use these funds for a clinical trial. And then I didn't understand what that meant. I didn't understand what an impact it was going to have. When I was here last year, I met, I think, every single one of the parents that was a part of the minocycline trial. And it was amazing to me to know we got the check to you guys in September, and by February, you guys had turned around and used that to make such a huge difference for your children. In 2 years ago, Vivint decided if we focused our efforts, our time, our money, our resources, everything on one cause, that we could make a really big impact. One of the things that we kept coming back to was how passionate this community is. And because of that, all of our efforts now are focused on redefining the home experience for children who have an intellectual disability through simple, intelligent products and services delivered by people who care. While you're working on finding a cure, we want to help keep your kids safe. We understand that there are challenges that come along with having a child that has Angelman syndrome. One of those is financial. Our company, our employees, everybody from executive down are committed to offering our system, home security, home automation, at a discounted rate because of donated time, money, and resources. Next slide. I'll do that. Oh, sorry guys. So this is Jen Kay. She has Vivint in her home, but when she talked to us about what her concerns were, and I'm going to go over some of these concerns so you can you'll probably relate to every single one of them. But one of our biggest fears was that Cole was going to leave our house. He's very independent and strong. Doors don't stop him. He hasn't learned that it's not safe to go outside alone. We live in a fairly quiet neighborhood, but cars still drive fast, and we have a pool off of our deck. It's scary to think what could happen. Next slide. So with Vivint in your home, some of these concerns are taken care of. We put a door sensor. If you're concerned about your child getting out in the middle of the night, we put door sensors on bedroom doors so that you will get a notification in the middle of the night if bedroom door opens. I know the bathroom and water is a concern. You could put a sensor on bathroom doors to let you know when the bathroom doors are open. We've got flood sensors. Another big thing is cameras in the bedroom. We're working on some products right now, a camera that will come out later in 2016 that's a two-way camera, so you can both listen into the room and you can talk into the room, but it's a two-way camera that you can use that also connects to everything else in your home. Another big one is smoke detectors, making sure that your home is safe from fire. I overheard today, I don't even see him, but I overheard today somebody talking about a fire situation. So lots of different scenarios that Vivint can come into play while you're working on everything else in your life, keeping your child safe and kind of giving you that peace of mind. Can we do a quick Q&A? Right now, just really quick, like 3 minutes. If you've got questions, ask me. If not, that's awesome also, okay? So we put cards in front of each spot here. If you want to get more information, if you want us to reach out to you, go ahead and fill those out and get those back to us. We're just outside the door. Come talk to us. We want to get to know you. We love your kids. We love you guys. I was able to attend the gala last year, and coming here is one of the highlights of my year. I feel like I'm here with family, which is which is really fun. So thank you for accepting Vivint into your family. But thank you for letting us take care of your kids. Thank you for letting us protect you. Come see us, come talk to us, and let us get to know you and protect your family. So that's all. Thank you, guys.
Thank you. Does anyone have questions for Holly about Vivint? Move to the microphone. Billy, you have a question? Yeah? Come on up.
I just want to say that we have Vivint, we love it, and you talked about a discount. How do we get the discount? Come talk to us. Okay, I will. Thank you.
So, Holly's not going to say anything, of course, but I know all of us on Facebook know that Vivint did a contest, and they sent a number of parents to the gala this year who would not otherwise have been able to attend. Oh, someone's pointing to someone over here saying it was people who've benefited. So, it's not just the security systems. They really care about us as people, which is amazing. And I think we all also know that one of the hardest things in our community is when we lose a kid, and when it's seizures, it's horrible and it's hard to understand. But when it's a kid that wanders away, that's really tough. And so, sorry. The fact that Holly and Vivint are willing to do this for us, I think, is amazing. So let's thank Holly again.
Thank you.
Ed says he's not ready to start, but we're going to make him start anyway. Okay, so what we're going to do now for the next 2 hours is we're going to have members of the fire team come up and talk to you about the work that they're doing under the fire initiative. And I believe you're going to give a little overview of the fire initiative.
No.
No? Okay, so let me do this instead then. We decided in talking with Ed and some of the other scientists and thinking about some of the programs at the NIH that are very successful. One of the programs at the NIH that I really like is called a program project. And what that is they ask 4 or 5 researchers to come together and put together one single grant that says, the 4 of us are going to work together. We're going to work together on this one single topic. We're going to each bring our expertise to it. And part of that program project is you have to say that you're going to meet regularly and you're going to talk to each other. And we thought, wouldn't this be awesome to do in Angelman syndrome? And Ed was willing to spearhead this for us, and we have an amazing team, and this year we got to add to it, so you're going to hear our new fire investigator. But the point of this is for them to be able to do the basic research that they can do to help us get to the point the pharmaceutical companies can then take these things and run with them. And you have already been hearing that Ed does a lot of preclinical work for some of these groups as well. But we didn't want them to miss the opportunity to hear something that happened, let's say, in Ed's lab on Wednesday that could really affect what David Siegel decides he's going to do on Monday. That kind of close ties, close conversation, that's what makes science go forward very, very rapidly, and that's what we wanted. So now you're going to get to hear each of our fire team members tell you a little bit about what they've been doing. And I, again, feel like we don't really need to introduce Dr. Weber. So I'm just going to say that he is, of course, a superstar in our community. He's also the head of our scientific advisory board, and he helped put together the fire initiative and has run it. And everyone can clap because the Australian police found all of his stuff, and he's able to come here and give you a talk.
What does FIRE stand for again? Could you just say it again? Fast Integrated Research Environment. Thanks.
So back in the old day, and I think that there's probably some people in here that can appreciate it, whenever we give a presentation, we used to do this on carousels with slides. And so you'd have to have your talk done, weeks in advance so that you could get your talk together. All the slides would be in the right orientation, and you would carry these big carousels around. Now with the advent of PowerPoint, I can see all the fire team people working on their talks really early in the morning and on the plane ride down here. So especially for me, yes, I'm sure some of you heard about my adventures in Australia. I had a great time in Australia, and I know there was somebody here that just said they were from Australia. Yeah, it was an unfortunate incident, but I recovered everything. The police there were fantastic. They went after the people that had stolen it out of my the room that day in Cairns, and so I'm here with you today, and I can show you some of the stuff that we're working on currently. Yeah, I tell my students this all the time. It's harder to give like a 10 or 15 minute talk than it is an hour-long talk, because you just don't have time to get into everything. So I'm just going to kind of hit an overview of some of the things that we're doing in the laboratory, some of the things that we're working on, and most of this is are some of the subjects that we're working on that are close to publication or we've already submitted for publication. So so you can see we're moving quite along. So. I have this slide up because just to give everybody somewhat of an overview, and I actually wrote a review article with my graduate student, Stephanie Charlone, that this figure is going to come out with, but it kind of gives an overview of this idea of, where targeted therapeutics can go, and we've talked about this upstream or downstream. And this really kind of shows you that you can target a lot of different areas in the synapse. If we're looking at this at a molecular level, this is a picture of a synaptic connection. We've got, you have the nucleus up here where the gene, the UBE3A gene is. These are synaptic connections. These are inhibitory connections. So when we start talking about upstream or downstream targeting, we're really talking about either targeting the gene where the disruption is, and we know where the gene is, we know what the gene is, or we're talking about trying to overcome the absence of the gene, either through what's being talked about earlier today with Ovid and Agilis and disruptive nutrition. So we can target this in a number of different ways, and this is basically what we're looking at. So this has been done with topotecan to turn on the paternal allele, and that was a great advance in what we know, and as far as a proof of discovery that this can be a viable target. The work that Jen Daly, as a matter of fact, Jen Daly is here in the audience, right over there, raise your hand. So she did the initial AAV work and published that paper that got Agilis so interested in some of the work that we're doing. I think the most important part about that work was we had done this in an adult mouse. So this was a mouse that had Angelman syndrome. We had injected the virus. We waited 5 weeks, and she saw this fantastic recovery. You can also look outside of the nucleus in places like the synapse, and there's been a lot of work done in that area as well. We've published a paper just recently on Reelin application that works on the synaptic connections there. Also work out of Eric Klan's lab, looking at the potassium ATPase, and then some other work with ampakins outside of the gene. So when all these therapeutics that we're talking about and companies, they're all targeting different areas of what we consider to be altered in Angelman syndrome. So one of the things, and Jody kind of touched about this, was the work that we're doing really kind of trying to develop new clinical outcome measures. And we think this is really important. And as Jody talked about earlier, coming up with clear outcome measures that we can use in future clinical trials is going to be very important, maybe even to the success of what we're trying to show. So how you define what you want to do and where you want to target and primary and secondary outcome measures is a big question that we're all trying to deal with, especially when designing new clinical trials. But the overarching question is which ones are going to be best for whatever therapeutic you're looking at. And so we're just trying to develop new outcome measures that are going to be less subjective, more objective, more quantitative, that you don't need somebody in there evaluating and saying, okay, we think we see a difference, or an evaluation of the parents saying, I think we see a difference. Something that we can go in, have the trial tested and say, yes, there's a definite difference there or not. And we really found this from the work that we did in the minocycline clinical trial using the Baileys and the Vineland, which in hindsight are really not very good tools to do an evaluation of Angelman syndrome. And what we found is that if you look at this this distribution, and this is what the average is on whatever you're looking at, and then 2 standard deviations away or 3 standard deviations away. And we use the term normal only because it's a normalization of the data, and that's what they would say this is where a typical child would be on any of those different types of measurements. But what we see with Angelman syndrome is there's a floor effect. So there's more than 2 standard deviations away from that mean. And what we see when we look at them in comparison with some of the measurements that you get from a typical child is that they fall so far outside that even an increase or even a significant increase, you don't really see it. So you may see observations with the child, but when you're trying to measure it and come up with a quantitative measure for this, it disappears. And so we live in science with things like statistics, where you say this is a significant difference using this particular test, and these tests is very difficult to show significance. So what we need to do is we need to develop new outcome measures, and that's what we've started to do. So one of the things that we're looking at is, can these measures be specific to Angelman syndrome? So one of the things we started looking at was the deficit that Angelman children have in verbal communication. Okay, so we saw this when we did the minocycline clinical trial, and we were looking at receptive and expressive types of communication. And we saw, again, this kind of floor effect, especially when you standardize the raw data and you look at that in comparison to typical children. So we started looking at using the LENA system. And the LENA system is actually this really interesting system that uses this microphone here. You just kind of press the button, it starts recording. You have all sorts of different clothing that's got a little pouch that you put it in, so it's non-obtrusive. And then you record over time. You can do this up to 24 hours. And then you plug it into the computer and it downloads everything that it's recorded. It's a sophisticated system that we're finding is trying to get the data out. But what you can do with this is you can isolate all the vocalization that's coming out of the patient, and you can quantify that on the computer. So we've actually done this in a number of patients. And this is one of the things that we came out with. So when you look at and graph these things out as far as things like control of phonation and canonical syllables, these are single syllables that are either vowels or consonants, and you look over a specific period of time, you can see that you get this distribution. And what you should actually see, because this is going from thing is working. I don't know how I'm supposed to point this. There we go. Wow. There's a delay on this. I apologize. What you're seeing is more primitive sounds to more mature sounds, and when you start talking about advanced forms, this is stringing words together. And this isn't just to show that Angelman children are different or your kids are different in how they communicate. But what it does do is it makes a profile that we can compare if we're giving a therapeutic. Does any of those things change? Does any of those different kind of parameters change? And this is a way that we can do it. We can quantify it, and it is completely non-subjective. Okay, so we can get the recordings off. The computer is going to tell us, does this change? Does this profile change to more of what we see with the typical child? See, the old-time slides, actually, I think I like better. There we go. And then it goes 3 ahead. So one of the things that we found, and one of the things that the speech pathologist found when she was doing a lot of these studies, and this is Ruth Barr at the University of South Florida, was that Angelman children, how they express themselves, if they can't do it vocally, is really through gesture. And so the quantification of gesture and looking at these gestures was a really interesting aspect of this. And because of the motor coordination defects, that we see in Angelman syndrome, this becomes problematic as well. So they went through literally hundreds of hours of filming kids with Angelman syndrome to really look to see how that gesturing differs and how it differs from child to child, and if they can actually quantitate that. And so we're actually pulling a lot of this data together to kind of show that there's not only changes in vocalization, but also in other nonverbal ways of communication. And we're bringing this up to publication hopefully in the next month. Wow. Okay, let me just go a little bit forward here. The second thing that we're looking at, and the closest thing that we have to getting the data together for publication, is work that we're doing with the gait analysis. So this here is what's called a gait mat. You can see where he's standing. It's looking at where his footfalls are. It's got pressure sensors in here. And what you can do is you can naturally have the patient walk back and forth on this, and it takes all these different measurements, not only on just the how they're putting their feet down, but also their cadence, how far apart their feet are, if they're pronate. So it takes all these things into consideration, and it's all computerized. So it quantifies all of that data. I can get to the next one. So the nice thing is that this has been used for a lot of different disorders. So for a lot of ataxic disorders, for example. So there's a lot of information about using this gait analysis to kind of quantitate all these different measurements in a person's gait. So we've already done some studies where it shows that one of the first things that we looked at was just width of stance. And we see that there's a significant difference for both left and right foot between Angelman patients and typical age-matched patients as well. But we also saw something interesting when we started looking at everything that had to do with the cadence and spacing and position of the feet when we looked at Angelman patients versus other patients. And this is all actually previously published data. One of the things that we found is that when we look at Angelman patients and we look at all those different parameters, you can actually compare these with children that have other intellectual disorders that are associated with gait disorder as well. And what we found is that when you take all those numbers into consideration, they don't look like those children. What they do look like is people that have ataxia. Okay, so it really kind of categorizes them a little bit differently. But again, we can get really specific numbers from this. This is all computer evaluated. We can supply a therapeutic, put them back on the gait mat, and now you're not trying to evaluate, well, is my child walking better? Are they moving around better? This will actually quantitate it and tell us whether we're seeing a significant difference or not. We have developed somewhat of a gait score on this. If we take all of the data that we get from a typical patient and we put it all together, it should equal basically 0. So we can take all the different parameters from the gait analysis that we do and come up with an overall gait index. And so not only can you see where that child falls within that standard bell curve of changes in gait, but we can also evaluate and say, does a therapeutic change that overall gait index? So we can look at it in a lot of different specific aspects and then in kind of a general gait index aspect as well. The other work that we're doing, and we're actually, this should have been put in for publication before I showed up here, was looking at overall synaptic function using the mouse model. So this has been a recurring theme, I think, with the new models that are coming out. It's going to be important to kind of establish this overall effect of synaptic function, and then we can move forward to do more work on trying to model what's happening in the synapse and synaptic connectivity later on in these other models. Let me look over here. One of the questions that we had was what is happening with synaptic function? So I've come up here and talked to you ad nauseum about things like synaptic plasticity and how connectivity between the neurons and how that increase in connectivity underlines learning and memory. So we've done this in our in vitro model where we can take a slice out of the brain, we can stimulate presynaptic, record postsynaptic, and we can see what that communication looks like. If we give high frequency stimulation, so if we can mimic somewhat like memory formation that's happening at a cellular level, we can see in the AS mouse model there's a deficit there. One of the questions that we had was alterations in proteins like ARC that are involved in receptor trafficking and how the synapses are communicating with each other. What was that underlying the deficit that we see in long-term potentiation? And looking at some of the other receptors and some of the other players in synaptic communication, the conclusion that we came out with was that perhaps what we were seeing was a depressed synapse. And I don't mean depression like they're depressed, but if you give low frequency stimulation, what you can do is you can actually reduce that connectivity, reduce that communication between two synaptic connections. This is important in learning and memory as well, and that function between potentiation and depression, that kind of yin and yang, is very important in aspects of learning and memory. So we were working on a hypothesis that actually what happens when you look at a non-AS mouse and you give high frequency stimulation, you can get enough potentiation to see this long-term effect. If you give saturating amounts, you get a ceiling or as much long-term potentiation as you can get. If you give low frequency stimulation or DHPG, which activates metabotropic glutamate receptors, you can get depression. If you do this multiple times, you can get the maximum amount of depression. What we were thinking was that perhaps what was happening in the Angelman syndrome mouse, that instead of just giving high frequency stimulation and not getting as much long-term potentiation, that what we were actually seeing was a change in the baseline of where you were starting from. So if the synapse is already at a depressed state, you give high frequency stimulation, you don't get as much long-term potentiation. And we've already shown that you can saturate this and get to the same amount of LTP as you can with a typical mouse. What we found, though, is that if we give multiple trains of low frequency stimulation and also DHPG, so make it as depressed as possible, what happens is you can get to the same amount of depression as a typical wild type mouse. Go just a little bit further. And so what we're actually seeing is that the defect in long-term potentiation, or the potentiated state, is the exact same thing as we see the problem that we see with the depressive state. So this does give credence to this model of overall reduction of synaptic connectivity or communication. So we've talked about this before, where we say if you have an alteration in synaptic communication between two neurons, it's not a big deal. If you do that globally throughout the brain, then you start having a syndrome. And this can affect a lot of different areas of the brain, so it's going to come out as a lot of different symptoms: changes in sleep, changes in hunger, changes in seizure ability. And this is kind of where we come up with the idea of a global therapeutic as well. So can we treat all the synaptic connections? So if there is no change in the depressive state or the resting state of this particular neuron, the problem is in communication either on the depressive state or on the excitatory state, then a global therapeutic would make sense. Okay, so you can affect things globally in the brain, and it appears that communication is really where the problem lies. The last thing that I want to talk about is something that we've been working on with Agilis, talking about, or at least looking at UBE3A activity and enzymatic activity. So you've seen these kind of slides before, where you're looking at UBE3A. What UBE3A does, it targets proteins for ubiquination, and then they go through the proteasomic pathway and get degraded. Then the ubiquitins get released and then brought back into this cycle. And this cycle happens at a certain rate, right? So like any enzyme that you look at, the amount of ubiquitins that this UBE3A can put onto this target is regulated. It will change with things like temperature, it'll change with the amount of substrate that you have, or even the amount of target that you have. So this idea of turning on a paternal gene or doing gene therapy, or anything that would have to do with alterations in UBE3A, one of the questions is, well, even if it's there, is it still working at the same effect? Okay? If you're trying to get a Ferrari, yeah, you got a car there, but is it going to be like a Ferrari? And so what we've started to do is develop a test for this and do enzymatic activity tests. Where we have two different ways to assay this. We can see a clear difference between the tissue that we get from Angelman syndrome and then from wild type tissue. We can look at that enzymatic activity, and what we can also do is we can compare this with anything that we do with gene therapy, anything that we do with enzyme that's coming off of the paternal gene. We can say, well, how well is this working? Is it being less active? That means that the curve would shift to the right here, or is it being more active? It could actually shift to the left. Alterations in that activity is going to have a lot to do. Somebody talked about, how much is too much UBE3A? Well, it's not only just expression, but it's how active that enzyme is. So even if you get up to normal levels of UBE3A, the question is it still doing what it's supposed to be doing even at that equal level? Dr. Burdine talked earlier about this regulation of UBE3A and how alterations in what they found is phosphorylation in a specific site can actually change that regulation. It can hang around a little bit longer, but it's kind of less active. So what does that mean for future therapeutics? Well, at least now we have a tool that we can measure it, we can quantify it, and we can see whether specific therapeutics such like gene therapy or protein replacement therapy is actually replacing the protein with something that works as well or better than what's there endogenously. So just very quickly, I know I'm probably going a little bit over, just very quickly I want to acknowledge some of the people that were involved in this. Dr. Barr is the speech pathologist that did all the work with the LENA system. Like I say, we've just submitted that for publication, so hopefully that will get out and you can kind of look at all the results and the conclusions that we've come out with that. Irina Filanova did a lot of the work on the synaptic function in depression. Joe Greco and Stephanie Charlone, which you probably have seen before and met before. Stephanie did all the work that was shown earlier with the ketone ester, and Joe's done a lot of work trying to figure out these new outcome measures. Dr. Lee and Christine Lemens have worked on the UBE3A assay. And then Justin Trotter, I just have in here. I don't even know why his picture's on there. He's an old graduate student that's now working at Princeton. But with that, I will take any quick questions.
Okay, so what we're going to do is while we are miking Scott up for his talk, we're going to take a few questions for Ed, and then at the end we're going to have them all come back up and do a panel discussion about the entire FIRE initiative and all the work you've heard about today. So if anybody has a burning question for Ed right now, we're happy to take it at the microphones. Maybe? Okay, we'll store them up because we're going to have our panel discussion soon. All right, so next up is Dr. Scott Dendo, and he's going to talk to you about the work he's been doing. And just to remind you, he's at Texas A&M, whereas Ed is at University of South Florida. So again, what we're trying to do with the FIRE initiative is put people together to talk frequently that won't see each other in the hallways, for example. So we'll now turn it over and
how do we advance this?
Hear what Scott has to say.
How do we advance this? It's not going. You have to hold it up?
Yeah, but... Fonts? He's not hearing me.
I think the batteries are fine. Well, I guess I could tell a story without any slides while we're up here, but
Yeah, because now your whole presentation's gone. So I would say chalk talk for Scott.
yeah, does anybody have any questions about Dr. Weaver's talk? Am I good to go? Where's the computer at? Is it back there? It had to be me, right? Where's the doggle? Where's the... It's way back there? That's why. Yeah, it's because I'm all the way back. Okay, sorry about that. So first of all, it's a pleasure to be here. It's always a pleasure to be here. I'm honored to be a part of this group. There's some amazing scientists that are working on this, and it's very humbling and very appreciative of this opportunity that the FAST is given me to be involved in this. So I was asked to speak for 20 minutes, and as those of you who know me, that's going to be very difficult, but I'll do my best here. I'm going to try to keep track of my time. What I thought I would do was, if we can, is give you just a brief overview of what we're working on as part of the FIRE project. And what I'm going to do is give a little bit of background in terms of why we're doing the things that we're doing. A little bit of data. A lot of this you'll just have to take my word for it. I'll try not to go into the science too much. And then maybe a little bit about where we hope to go with these experiments and the things that we're doing. Really what we're trying to do here is develop a therapeutic. I mean, along the way, we are interested in learning a lot about UB3A and how the gene is regulated. But as you know, this team was put together to develop therapeutics and, as you can understand, to develop them as quickly as possible. So these are the three areas that I'm going to briefly talk about. So one is our interest in understanding the mechanisms that regulate imprinting of UBE3A in neurons. And so this is a very unusual gene in terms of the way that it's regulated in the brain. And so I've been interested, and my lab's been interested in understanding how this process occurs and also why it occurs. And that's more of a basic science question, but understanding the how and the why will help us develop new strategies to circumvent this process and to understand what we're doing if we do in fact do that. We're also actively involved in the identification of new treatments or therapies for AS, and what we've been doing is developing high throughput screening assays so that we can look at as many drugs and compounds as quickly as we can. It takes a lot of time and a lot of money to do this, and so we've been actively trying to develop new strategies to expedite this process. And then last, I'll mention our work to develop new models of Angelman syndrome. It's been mentioned there's a mouse model of Angelman syndrome that's been extensively used. We're in the process of developing a large animal model of Angelman syndrome, and I'll sort of go over why we think that's important and so forth. Before I get started, I just want to point out the people that are in my lab. Some of them have left. Most of them are still here. We've hosted some students and so forth from other places, but this is really the team that I have. Much of the work that I'll talk about today was done by Dr. Paul Hillman, Dr. Sarah Christian. She was a postdoctoral fellowship through FAST, and then Jade Benjamin, who's currently a graduate student in my lab, as well as Hillary Shaheen. So why we want to understand how UB3A is imprinted, or the mechanism by which UB3A is imprinted in the brain, is so that we can figure out ways to circumvent this process. So as you've heard, one of the approaches that's being used is to develop strategies that reactivate or activate expression of the paternal allele. And I'll talk about that in my second part of this talk. But if we understand how the paternal allele is turned off in neurons, the idea is that we may be able to develop a way to turn it back on. And it's really just as simple as that. I mean, there's a lot of work that has to be done in this area to know whether or not this is an effective treatment. But the reality is that all of us in this room, as far as we know, have our fathers, the allele that we inherited from our father of UB3A, has been turned off. Why that happened, nobody really knows. But nonetheless, that allele is off. It seems to be the natural state. And all we want to do is try to turn it back on as a therapeutic. And the idea is that the expression of that allele will replace what's been lost through a mutation or deletion on the maternal chromosome. And so, it's going to be a problem here. So as you've probably seen in terms of gene regulation, this region in the genome of chromosome 15q11, q13 is perhaps the most complicated region in terms of its allelic expression and the epigenetic factors that regulate expression. There is, without going into a lot of details, what we know about this locus is that on the maternal chromosome, and this is in the central nervous system, UB3A is expressed, whereas all these other genes are not. On the paternal chromosome, these remaining genes are expressed, and UB3A is turned off. The way that UB3A is turned off is through the expression of this long non-coding transcript that involves a number of regulatory RNAs. And so we think that an activation of the paternal allele is actually linked to the expression of these other regulatory RNAs, almost like they're competing with each other in such a way. But the idea is to understand precisely how this long non-coding antisense transcript turns off expression of the paternal allele. And so there's a number of models that exist. We know that the expression of this long non-coding RNA, it's only expressed in neurons, so in all the cells of our body except neurons in the central nervous system. UB3A is expressed from the paternal chromosome, but in neurons, this long non-coding transcript is expressed, it's highly expressed, and by some unknown mechanism, it inhibits transcription of the paternal allele. And it's a very unique mechanism because most imprinted genes that are regulated by an antisense transcript involve repressive histone modifications or these epigenetic modifications that silence transcription of the allele. That's not the case for UB3A. For UB3A, the paternal allele is actively transcribed. It just doesn't complete the process of transcription. So somehow the antisense transcript is stopping the paternal allele from completing a full-length transcript. And so I won't go into any details here, but what we've been trying to do is to understand why this happens. You know, what's the biological relevance of turning off the paternal allele, and then how this happens. And we've focused on one particular area, and I'll sort of quickly go through this. This is going to take forever with this. How about when I hold that up, y'all? Can y'all move it back there? There we go. And so what we've done is we've looked at both the mouse and human UB3A gene, trying to understand why UB3A is imprinted. We find that it doesn't appear to be a dosage regulating mechanism, so the inactivation of the paternal allele doesn't appear to have evolved as a means to reduce the amount of UB3A in the brain. In fact, we see that UB3A levels are higher in neurons than they are most everywhere in the body. We've done sort of evolutionary studies that have shown this to be the case. We've looked at the establishment of the imprint during neurogenesis, and what we see is that the expression levels of UB3 are tightly regulated, even though one allele is being turned off. And so for whatever reason that is, that it's being turned off, some mechanism within the cell, within neurons, is maintaining the level of UB3A, despite the fact that one allele is being turned off. And that's more related to the why than the how. Regarding the how, we've been focusing our attention on the antisense transcript and trying to understand its expression levels, how it's been processed, where it goes, where it stops, and been looking at this in both in human and mouse, and trying to understand exactly how that long non-coding RNA transcript turns off the expression of the paternal allele. And we see that it's very unique. We have a model that we've put together, and this is something that we're actively working on in our lab. Much of this, though, it's very basic in nature, but the idea, again, is that if we understand how the process occurs, then we can somehow perhaps circumvent it. Now we're going to have to get this fixed. So the next part is the identification of new therapies for Angelman syndrome, and this is very much related to the first part of my talk. And so there are a number of efforts that are going on, not just with the FIRE team, but globally, where people are looking for new therapies for AS. And the approach that we took was to speed this process up. And there are a number of groups, pharmaceutical companies, what have you, that perform high throughput screening assays to identify potential candidates for new therapies. And so what we wanted to do is take the knowledge that we had and some of the tools that we had and use that and see if we could develop new ways to rapidly screen drugs as potential therapies for Angelman syndrome. And so I want to point out some of our collaborations that we have at Texas A&M. This particular project it relies heavily on the Texas A&M Institute for Genomic Medicine. Drs. Ben Merpergo, Andre Golovko, and Dr. Jonathan Ballard have been instrumental in helping us set up this particular part of this project. And you'll kind of see how this unfolds here in a second. In addition to that, we work closely with the Texas A&M Institute for Biotechnology that's located in Houston, Texas. And that facility there is a high throughput screening facility that has hundreds of thousands of potential drugs, small molecules and FDA approved drugs that are available to us at essentially no cost. And so we've been working with these two groups to develop a new strategy to screen these libraries for drugs that can reactivate expression of the paternal allele, or that can be used as a treatment for the symptoms. And so there's two approaches that we've been taking. The first is a target-based approach, and the second is a symptom-based approach. And so in a target-based approach, we're looking for a therapy that targets UB3A. And so in these particular assays, they're biased. You know, what we're trying to do is reactivate expression of the paternal allele. Our outcome measure is only one thing, and that's expression of the paternal allele. And it's very focused. The problem with these types of studies is that they are biased. And so if we're only looking at one thing and nothing else, and we don't see anything, well, you know, there are things that we might have missed. The symptom-based approach is an unbiased method. And here what we're attempting to do is to look for compounds or drugs that mitigate the symptoms that are associated with AS. And so in this particular strategy, we're not particularly interested in the mechanism by which this occurs. We simply want to see if something works. This is thought to be a much more powerful approach because, quite frankly, we're not trying to outsmart the biology that's associated with this condition. We throw the kitchen sink, if you will, at the condition, and we see what makes it better. We really don't care what it's doing. We're simply looking to see if the symptoms improve. And so we've taken these two strategies and tried to develop high throughput assays to find a new therapy for AS. So in the first target-based approach, what we're doing is looking for strategies that will reactivate expression of the paternal allele. And so as I mentioned, we know that the expression of this antisense transcript or this long non-coding RNA is necessary and sufficient for inhibiting expression of the paternal allele. And so the approach is quite simple. We're simply looking for things that will inhibit or interfere with this process with the idea that it will reactivate expression of that paternal allele. And this approach has been used. I'm sure we've already mentioned it. There, in some of the earlier talks, and I know that some of y'all are probably familiar with this, the work that Mark Zilka did and Ben Philpott did at UNC, where the topoisomerase inhibitors were found, are shown to be able to reactivate expression of paternal allele, as well as Dr. Baudet's group at Baylor College of Medicine, where they found that these antisense oligonucleotides that targeted the antisense transcript were also capable of reactivating expression of paternal allele. And so we didn't want to reinvent the wheel or redo what they did. We actually wanted to make this more powerful. And so with these types of studies, especially since UB3A is only imprinted in neurons of the central nervous system, they're complicated because you have to have a primary cell line that you isolate from the mouse brain. So neurons are post-mitotic, they don't grow in culture. And so each time one of these experiments are done, we have to sacrifice a mouse, we have to extract its brain, we have to isolate neurons from that mouse, plate it in a dish, and then add the compounds to it. There's only a limited number of neurons in the brain that you can culture. So when we typically use the hippocampus, there's roughly 1.5 million neurons that you can extract from one mouse hippocampus. That gives you, you can translate that into a certain number of compounds that you can screen, which is not that many. So the conventional way of doing this is very labor intensive, largely because of the source of the cells that are used to screen the drugs. So what we decided to do was to use a different approach where we isolated embryonic stem cells from mice that had a YFP reporter allele on the paternal chromosome. And so these mice were developed while I was at Baylor College of Medicine, and it's basically a knock-in mouse model where the gene for the yellow fluorescent protein was targeted to the 3' end or the end of UB3A. And what's nice about these mice is that you can use that fluorescent tag to look at the expression of either the maternal or paternal allele. And so these mice here on the left have inherited this YFP allele from their mother. This is a confocal, or this is a immunofluorescence image of the cerebellum. And so the red here is a nuclear marker, the blue is an astrocyte marker, and the green is UB3A. And so you can see there's very high levels of expression of UB3A in these Purkinje neurons, as you would expect. However, if we look at a mouse that's inherited that YFP allele from its father, we see that it's basically been turned off. And that's what we expect to see. But what's nice about this mouse model is that it's a very nice reporter for looking at the allelic expression of UB3A. So we took mice that had the paternal YFP or a YFP allele on the paternal chromosome, and we isolated embryonic stem cells from these mice. And what we do with this is we go through a process where these embryonic stem cells are expanded in culture. And this is the work that we do with the Texas A&M Institute for Genomic Medicine. We have a system that we've set up where we start on a particular day. A vial of these embryonic stem cells is grown in a dish. Remember, they have a paternal YFP allele that's there. They will grow these until there's roughly 500 million cells. So they're many more than what we would get from one mouse. And then we're not doing this with a live mouse, we're actually doing this in a dish. And then what we do is we treat those embryonic stem cells with a certain cocktail of hormones and reagents that cause them to differentiate into neurons. And so instead of having to isolate a neuron from the mouse brain, we can create one in a dish. And since we can start with 500 million cells, we end up with a lot more material that we can use to screen our drugs with. And so this is what we've spent a tremendous amount of our time on for the past 2 years, is setting up this assay so that we can look at thousands and thousands of drugs. In addition to that, our collaborations with the Institute for Biotechnology in Houston, The high throughput screening facility there it's an automated system, so there are robots and automated imaging machines that will seed these cells into 384 well optical bottom plates. There's very little human interaction here. There's mostly robots that are doing this. The compounds are added by a robot, and then the cells themselves are actually imaged on a machine. So there's actually no person. There's a person that's running this, but it's all an automated process. And then what we do is we take this data back and we mine it to see if we can find things that are capable of reactivating expression of the paternal allele. And so much of this work has been done by Jade Benjamin in my lab. And so she spent quite a bit of time demonstrating that this assay will work. You can see here that on the left, these are embryonic stem cells that have been differentiated in neurons. And so there's the red here reflects the neurons. The cells that don't have red represent other cell types. So this is a mixed cell type that we have in there, but much of them are neurons. And then you can see here that if we know that when these neurons differentiate in culture, that UB3A becomes imprinted like it does in the central nervous system. So these embryonic stem cell derived neurons recapitulate the inactivation of the paternal allele. So she demonstrated that was the case. And then she also used topotecan as a positive control to show that she can reactivate it. So for us, this was just a lot of time with the assay development and getting this and demonstrating that it does in fact work. To fast forward through about a year's worth of work, what we've done is we've screened roughly 16,000 drugs. And again, this would be a very different experiment if we had done it the conventional way, but because we had set this assay up to do this, it actually could go well beyond this. In fact, this many drugs can actually be done in 2, perhaps 3 rounds of screening, which once it's running, it's a very powerful system. We've stopped here, so we've been mining this data to see what we found. We picked up 3 novel hits in the NIH clinical collection. So this is a series of FDA-approved drugs that were available to us, and we found 3 compounds in there that were, at least on the first pass, capable of reactivating expression of the paternal allele. The disclaimer here is that we have to go back and validate all of these. I expect that not most, but some percentage of these are false positives, but nonetheless, this is the process. We picked up 1 hit in the Prestwick Chemical Library, and then we had 31 hits in a Maybridge library, which is a small molecule library. So these are compounds. They're not drugs, or they haven't been tested in any way, but they're thought to represent all of the small molecular space that can be made up with certain combinations of atoms and so forth. So what we're doing is we're going back through this data and validating all of these hits to see which ones we can throw out and which ones we'll pursue further. And here's just kind of an example of what this looks like. So this is one of the drugs that was picked up in the NIH clinical collection. And so this is sort of what the output looks like from the experiment. This is an entire well on a plate, and so there's about 300 of these that will image on one plate. We usually run 12 plates at a time. The blue image here, it's a dye for the nucleus of the cell, so you can tell where the cells are at. This red here represents shows where the neurons are at in the dish, and then the green is the UB3A protein. And so in a control, this would be black. So we know that the paternal allele is almost entirely off. It's a very a robust screen. When it's reactivated, the neurons fluoresce. And so this just gives you an idea of what that looks like. And then here's another one that we picked up in the small molecule library. So again, we have to go back and validate these to show that there's not false positives. Some of these compounds are actually autofluoresce. So they're just by shining light on them, they'll give these colors. And so we want to make sure that's not the case. But nonetheless, to just give you an idea of what we've done with this and what we've found so far. The next experiment that we have is our symptom-based approach. And again, this strategy here is not so much to target a particular pathway or gene or mechanism. This approach is simply to find something that mitigates the symptoms associated with Angelman syndrome. As some of y'all may or may not know, there's a fly model. There's actually a number of fly models for Angelman syndrome. And perhaps not surprisingly, those Angelman syndrome flies recapitulate many of the symptoms seen in Angelman syndrome. So for example, the flies have motor coordination defects. They have learning and memory defects. They have circadian rhythm defects. And we can use that as an outcome measure to screen potential candidates. And you say, well, why do this in a fly? Why not do this in a mouse? Well, mice are very cheap. You can grow lots of mice and have large colonies of mice, but surprisingly, they are very expensive. Their life cycle is, a couple of months. My bills, I know that all of us here, we spend thousands of dollars each month on maintaining our mice. The best labs, and from what I gather even from some of the best pharmaceutical companies, can only screen a few compounds in mouse models, just simply because of the time that's associated with it and the time that's associated with maintaining the mice and so forth. Flies, on the other hand, can literally be grown for pennies. I'm sure all of y'all had fruit flies in your house before, right? They're almost impossible to get rid of. We have, literally, you can have tens of thousands of these animals in a lab and maintain them with very little cost. The life cycle of a fly is about 10 days. Flies start having more flies the day they're born. So it's a very robust, very high throughput assay that you can use that has a phenotype that you're interested in. It's probably the lowest organism on the list of those that actually manifest some symptom that you could do this with. Now there's a lot of biology between a mouse, or between a fly and a mouse, and especially a fly and a human, but this does work, and there are examples of that. Investigators have used the Fragile X syndrome fly to discover new drugs. There have been cancer agents found, or cancer drugs found in fly models. It's very different, and I can understand what it must be like to hear this, but it is a very powerful and very quick way to screen things. And actually what you can do here is you're in the order of thousands of compounds that you can look at. It's not as high throughput as, say, a cell-based assay, but it is very high throughput compared to other organisms. And so I'll just kind of give you an idea of what we're doing here. This is something that we've been setting up the assay for this. We're using three different approaches, different growth chamber formats, if you will. So we can grow these flies in 12 well vials or plates, 24 or 96, and I think there's 24 there, or 12. And then these different 96 well formats. And so each one of these tiny wells can be home to a dozen or so flies. And then in each one of those wells, we can add a particular drug to it. So on these 96 well formats, we can screen almost 100 drugs at one time. And that's pretty amazing when you think about what it takes to do that in a mouse. What we're focusing on right now is larval locomotion, adult locomotion, and circadian rhythm. And again, we're simply looking for things that rescue or mitigate these symptoms, with the idea that it's something that's found will then be validated in a mouse model and then perhaps in another animal model, which leads me to my next topic. So it was actually one of these meetings a few years ago that this idea about generating a large animal model of Angelman syndrome really hit home. And so just a little brief background, my PhD training was in large animal genetics, and my PhD advisor there at Texas A&M was a pioneer in developing transgenic animals, particularly pigs. And the idea was that the pig model would be used to replace the mouse model. And there are a lot of reasons for wanting to have a large animal model for a condition, and being involved with this group really proved that to me that was the case. And the idea behind this is that for those compounds that are found, whether it's through the cell-based assays, the fly assays, the work that Dr. Weber or the others are doing, that has typically ended in a mouse. And that's usually been the gold standard. For preclinical studies, most groups will look at the efficacy in a mouse model, and then they'll test the toxicity and the pharmacokinetics in a large animal model, for example, a beagle or a dog or another breed of dog or a pig. never has anybody had a large animal model of a condition. Now they do exist and they happen naturally, and typically you'll see veterinarians stumble onto them and they identify them and they maintain them, but only recently have people been able to design and generate these large animal models. And so what I mean by that is actually creating an animal that has a mutation in a specific gene. And so what we proposed here was to make a pig model of Angelman syndrome. And so as I mentioned, my background or my training started in this area. My PhD advisor, Dr. Jorge Piedrahita, has left A&M and has been at NC State University for the past 10 or 12 years. He's the director of the Center for Comparative Medicine and Translational Research. It's actually, I believe it's an institute now. And there's a series of events that have led to this, but there's only a few groups in the world that can actually do this, and he happens to be one of them and one of the best of them. This particular project that we have involves a large number of groups. So we're working with NC State to develop the pigs. We're working with veterinarians at Texas A&M who will help us with characterize the model. Dr. Gwen Levine is an expert in gait analysis in animals, and we actually at A&M have a gait analysis system very similar to the one that Dr. Weber showed, that is on par with what you'll see in any hospital in the United States. And it's used entirely for large animals. And so we're working with groups that will help us characterize these pigs once they're made. Also, Dr. Ann Anderson and Dr. Weber will be helping us with the EEGs in these pigs and the learning and memory of these pigs. And then also we'll be collaborating with Dr. Siegel in terms of the design and some of the therapeutics that we're going to test in them. And the idea behind it is fairly straightforward. So as I mentioned, preclinical studies involving new drugs jump from a mouse to a human. And unfortunately, there are examples of many drugs that have failed after this jump. And that can be explained for lots of reasons, but one of them can be that there's just too much biology between a mouse and a person. And so the idea here is to put something in between the two. And so a pig is, physiologically, it's much more similar to a human. It's a large animal model that's been used for decades in biomedical research. The pigs were used extensively for heart transplants and stents. As I mentioned, they've been used to test pharmacokinetics and toxicity of drugs. And so there's a lot known about pigs in terms of their physiology, their anatomy, and so forth. They are a litter-bearing animal. They have a gestation of 3 months, 3 weeks, and 3 days. They're relatively inexpensive to maintain compared to companion animals or to non-human primates. And there aren't the ethical or societal concerns that are associated with using them as a model system. And so we felt like the pig, having our resources at A&M, my interactions with Dr. Piedrahita and my background in this area, to develop a large animal model of Angelman syndrome that would be used solely, if not exclusively, for testing those most promising candidates before they're tested or used in humans. And you can imagine how this would unfold. If there's something that's promising that's found in a mouse and it's tested in a pig and it's also shown to be effective in terms of its treatment, well, then your confidence that it's going to work in a patient is heightened, elevated. If there's a promising treatment found in a mouse and it doesn't work in the pig, well, now you have the opportunity to decide whether or not you want to pursue that. I don't think anybody wants to be testing these things without some degree of success associated with the treatment. And what this, or at least the idea behind this, is that it will ensure what we're using will be effective. It'll also give us a place to work out the dosage. The pigs, commercial pigs that become adults are very large, but there are strains of pigs that, the miniature strains, that as adults are approximately the same weight as humans. And so there's a lot of actually research going on using these as models, and we foresee that this will be the case for us too as well. And so I've sort of mentioned this here. The physiology is very similar. The metabolism is very similar. Brain development is very similar between the pig and the human. And perhaps not surprisingly, cognition. Pigs are all actually thought to be smarter than dogs. They have a very complex social hierarchy that exists. And so there are a number of things that we feel that we can use or test in the pig that we wouldn't be able to do in any other model system. It's been used extensively for other diseases. As far as, to the best of my knowledge, this will be the first project where a pig's being used to study a neurodevelopmental disorder, but nevertheless, this has been used and been very successful for other conditions. Based off where our location at Texas A&M University, we have all the resources and infrastructure to characterize these pigs. A&M is also the home of the Texas A&M Institute for Preclinical Sciences or Preclinical Studies. It's actually a GLP facility that was designed to test pig models for various uses in biomedical research. This is all the work that's being done at NC State. This has to be validated, but there is evidence that we've deleted the UB3A gene, the pig UB3A gene, and now what we'll do is proceed with making the pigs and then characterize them. So hopefully by next year we'll have a lot more to show you in terms of what these animals are like and what we're doing with them. And then with that said, our design, as you can see here, is to use a high throughput assays both in cells and flies. To collaborate with those groups that are using the mouse, we also have mouse models of AS for the most promising candidates, and then the top candidates would then be tested in the pig model, and then those that pass that would then go on for use potentially as a therapy in the patients. And with that, I'd like to thank everybody in my lab, most of them that I've already mentioned, as well as the fire team and FAST. Thank you.
So as we're doing the changeover, we had a question on the live feed. Someone wanted to know if any of the hits that you got in your chemical screen are any of them similar to each other, suggesting they aren't false positives. That was the question. Yes. Okay, and the answer is yes. Okay. Okay, so then our next speaker from the fire team is Dr. Ann Anderson. And she's coming to us from Baylor College of Medicine, and as she mentioned before, she is a neurologist, and she's also an epileptologist, and she runs the epilepsy clinic there. So she will be talking to you today about her work on the fire team, and I'll just turn it over to her.
Thank you. Thank you for the introduction. Can you hear me? No? Let's see. I'll move it closer. Is that better? Is that better? I guess I'll hold it. So thank you for the introduction. And as I pointed out earlier and Becky highlighted, I'm both a clinician and a researcher. My focus clinically is epilepsy. And actually, I run the epilepsy monitoring unit, which is an inpatient unit, and clinical neurophysiology, which is primarily ambulatory EEG, so EEG for outpatients or EEG in the hospital setting. And in that context, both in the EMU as well as doing EEGs, I see a lot of Angelman patients and struggle with their EEG and their epilepsy along with their families and the patient themselves. I was recruited to the Fast Fire team, I think primarily by Ed Weber. Ed and I had overlapped during our postdoctoral period at Baylor College of Medicine in Dave Sweat's lab. And that was at the time when Ed was getting involved in the Angelman research and did a lot of his early work identifying signaling pathway dysregulation in the Angelman mice. At that time, I was learning signaling pathway dysregulation and building an epilepsy research program. But until I got recruited to the Fast Fire team, I had not worked specifically in Angelman syndrome research. So I didn't have the mice up and running in my lab. And so we spent a lot of the early period of our funding with the Fast Fire team actually getting the mice up and running in our lab. And I think this audience, I know you're very sophisticated, and probably many of you know that there's struggles with these animal models, and both the other speakers, Ed and Scott, have alluded to that, which is why the team has been seeking alternative models to the mouse, including the pig model, and we're really excited about that development. Part of the frustration with the mice is that it appears there's some variability in the Angelman phenotype, and it depends on their background strain in part. So that was part of the struggle we dealt with in my lab, and it became such that we ended up evaluating the behavioral phenotype and seizure phenotype in different strains of the mice. And it was really a lot of work for us, but we ended up with some interesting results, and results now that we can move on with in terms of screening these animals. My lab is really, the expertise is in neurophysiology, EEG, epilepsy, and different seizure models, induced seizure models. But we ended up doing behavioral screening, and my lab does some behavior in the context of epilepsy, but we really looked to Ed's group to help guide those studies, but we felt like it was important to do them because that's such an important phenotype in Angelman and also in the mice. So we wanted to make sure that we had mice expressing the deletion that actually had a behavioral phenotype like what's seen in Ed's lab and other labs. So I'll talk to you about that in the beginning of my talk, or most of my talk, and then at the end, once we had phenotyped these animals, then we used them to screen one of the compounds of interest that had been used in several other neurodevelopmental disorders, and then I'll just talk to you a little bit about what our future thoughts are. Next slide. So I don't want to spend a lot of time on this slide, and the other speakers have already discussed this, but I just want to highlight the importance of preclinical studies such as those that are funded by Fast Fire. We really can't translate to the bedside to our human individuals that are affected by a given disorder without these preclinical studies. They're important, one, to identify novel targets, to develop pharmaceuticals against or genetic manipulations against, but also these studies are required to screen compounds that we're interested in part because we need to know they worked in an animal model before we take an agent to then treat a human, especially children with, but also because our regulatory boards, which include the FDA and the institutional review boards at our given institutions, they require that we cite the preclinical studies, the basic science that support what we want to do, what we want to take to the bedside. So this is just one of the early studies that from Art Baudet's lab defining that really characterize the phenotype of these mice, and they're those mice that then other labs, including Dave and Ed, went on to further characterize in terms of signaling pathway dysregulation and further characterizing the phenotype. But they recapitulated a number of the features of Angelman, which I think you know, the motor dysfunction, cognitive deficits, but also there were reports that these animals had startle-induced seizures. And actually, we were just next door to Art's lab when we were postdocing with Dave Sweat, and I went to the animal facility with his postdocs and actually saw those seizures. So this is just an overview of the studies that or an overview of the studies and related to what we see in Angelman syndrome. So we were interested in abnormal EEG activity in the mice. We know that children and adults with Angelman syndrome have abnormal EEG activity, even when they're not having active seizures. So we were interested in evaluating that in the mice. We wanted to look for seizures in epilepsy, both spontaneous seizures, evaluating whether these mice actually had epilepsy, but also doing convulsant-induced seizures, like you heard work from Ed's lab with the kainate induction in the animals. And we were also wanted to look at abnormal behavior that's been reported in the animals previously, and we wanted to make sure that in our hands we saw these deficits. And of course, cognitive impairment as well as abnormal social behavior is often a part of the Angelman syndrome phenotype. And then to use these as markers that we could then evaluate whether therapeutics that we're interested in preclinically had an effect on these abnormalities. So what we did in terms of EEG is that we looked at baseline EEG activity, both just with visual inspection, so that's a qualitative evaluation, and then we use spectral frequency analysis, which gives us a quantitative evaluation of the EEG and allows us to do statistics on the differences between wild type and AS mice. We looked for spontaneous EEG evidence of epileptiform activity, and that's using visual inspection. And then we looked at convulsant-induced seizure threshold. So this is basically the setup we use for the studies I'm going to show you today. We also have a telemetry system up and running now. We're just getting monitoring our first animals with that. But this system is one that involves implanting electrodes, which you would also do with the telemetry system. And basically, we implant electrodes on the left and right side, both on the cortical surface, but also in the depths, in the hippocampal depths. And we get EEG activity. We plug the animal into a thread of electrodes that then is hooked to a commutator. So when the animal moves around, that electrode chain or thread of electrodes moves as well, so it doesn't get tangled up. And they can be monitored continuously for days on end in this system. They have food and water in the cage. So what I put on this slide is human EEG. So what's shown here is an EEG trace from a normal individual. The blue is left and the red is right, and it goes front to back. So these are more frontal, central, and then occipital electrodes left and right. And what you see is this really nice modulated EEG activity. There's an occipital dominant rhythm, which is normal, and then pretty fast frequencies anteriorly as well. And then these are two examples of EEG traces from individuals with Angelman syndrome. And what you see here is this very typical pattern in the frontal regions of the brain, left and right. There's this high amplitude slow activity. And then you can see there's some tiny spikes intermixed. And then the pattern in the EEG trace below just shows a diffuse theta pattern. So it's slow and it's different from what you see normally, but it doesn't show the spike activity that you see here. Both examples of abnormal EEG activity. So what we found in our mice, the wild type traces are here from the cortex and the hippocampus, and the AS mouse tracing is shown here, cortex and hippocampus. And what you can see is that the wild type mouse has this well-modulated background activity. It was similar to what you saw in the human in the posterior regions. This is more typically seen in the mouse in the hippocampal regions. And this corresponds to an awake animal that is involved in exploring and a behaving animal. And then what you see is a disruption of this pattern and a lot of slower frequencies in the hippocampus and in the cortex of the mouse. And what we wanted to do is quantify this. So visually you can see it's different, but we wanted to quantify it and be able to do statistics on it. And we felt this would be one biomarker that we could use to gauge the effects of a therapeutic agent. So what we looked at was total power of all the frequencies combined. We looked at slow activity delta frequencies. We looked at theta, which is 5 to 8 hertz or 5 to 8 cycles per second. Alpha, which is 8 to 13. Beta, which is a bit faster. And then gamma frequencies, which were even faster. And these correspond to various behaviors and abnormalities. An increase in delta is associated with disorders in sleep and developmental disability. Theta and alpha both are involved in learning and memory and attention. Auditory processing, you'll see an increase in beta frequencies. And then, again, attention and object recognition with gamma frequencies. So the spectral analysis can be correlated with behavior, which would be another interesting component of looking at rescue with various agents. So what we found is that the black 6 Angelman mice, had an increase in total power. The Angelman 129 animals did not show a difference, whereas the black 6 did. So an increase in total frequency spectrum. And then we looked at the individual frequencies, and what we found is that there was an increase both in delta, theta, and then the gamma frequencies. So these were abnormalities that then could serve as markers. We looked at the EEG activity for epileptiform activity, and what we found is that the black 6 mice, as well as F1 mice, which were mice generated with the deletion and then a mixed 129 and black 6 background. And both of those animals, we felt that it was more robust in the black 6 animals, showed these bursts of polyspike activity, and they lasted about 2 to 2.5 seconds. The animals didn't demonstrate any tonic-clonic type of seizure activity. However, it's possible that if we were able to test them maybe in a learning paradigm, or in humans, we give them a test word or we give them a command. And this has sort of an absence type pattern, a generalized polyspike pattern, and that can be associated with brief absences or sometimes blinking or myoclonic type seizures that are fairly subtle. So we're not sure if it's long enough to be a seizure, and it's certainly epileptiform. We also looked at evoked seizures, and what I'm showing here is the audiogenic evoked seizure. And what we did with these animals is we put them in a chamber, and after they acclimated to the chamber, we then presented them with 140 decibel tone. So that's the tone. And this is the wild type animal who does not have seizures, but you can see the wild running seizure and tonic-clonic activity in the Angelman mouse. So what's shown here is that when we looked at 129 mice, the black 6 mice did not show this phenotype. Both the young animals had audiogenic seizures. It increased the percentage of them that had them increased with age, and actually one of the wild type animals had an audiogenic seizure when in the older animals, none of the young animals did. So that's an important aspect of their seizure phenotype. We also looked at evoked seizures with kainate and saw an increased threshold to kainate seizures in the 129 animals, similar to what you saw from the Weber lab. So we performed continuous EEG recordings during the kainate stimulation. And I'll show you those EEG traces, partly because it's much more dramatic, the seizures in the Angelman mice. We also did chronic recordings. One of the things that's known about kainate-induced seizures is that while they induce acute status epilepticus, so an hour of continuous seizures or longer, the animals also, a certain percentage of them will go on to develop epilepsy, particularly in rats. In mouse models, it's not as robust. So if we saw the Angelman mice going on to develop epilepsy, that would be quite significant. And I'm not going to show you these data, but we have in those recordings, we have found that a few of our Angelman mice actually do develop chronic epilepsy. But I'll show you the acute data from this 1 hour time point after kainate. So this is an example of the type of seizure they eventually evolve into with the kainate. And these seizures just happen one after another. Usually you have to give them an anticonvulsant to get them to stop seizing. So it's a mixed tonic-clonic generalized seizure. And what you see on EEG, once they go, so their baseline activity is shown here, and you can see the Angelman pre-kainate induction. So this is just how they are at rest, is abnormal, higher in amplitude than the wild type. This baseline is markedly compressed. That's why it looks different than the earlier EEG I showed you. With the first seizure they have after kainate, already the Angelman mice have a much higher amplitude seizure activity in their EEG trace. And then once they go into status epilepticus, that activity is much higher in amplitude, suggesting there's less inhibition and there's possibly recruitment of more cortical neurons, excitatory neurons. We really don't know the basis of this, but it would, I think, be interesting to pursue this on a molecular cellular level. What we found is that, similar to what Ed showed you, and like I said at the beginning of this section, that the Angelman mice, the 129 mice, had a decreased latency to both the first seizure and what's shown here, status epilepticus. So they were more prone to seizures, earlier seizures, and a decreased, earlier seizures, earlier status epilepticus. So again, supporting that they're more seizure prone compared to wild type animals. So just to summarize, we looked at 3 backgrounds: the F1, which is the cross of 129 black 6 with the AS mutation, then the mutation on a black 6 background and a 129 background. And in terms of just the EEG trace itself and spectral power, it seemed that the black 6 had abnormalities that potentially would correlate with their behavioral deficits that are known, and I'll show you a summary of that in the next couple of slides. And they also have the generalized polyspikes, possibly representing seizures. We're not sure at this point. Whereas the 129s are valuable in that they have audiogenic seizures that in the mutant animals, as well as an increased susceptibility to kainate. So it seems with EEG and epilepsy studies that both strains would be valuable expressing the mutation. We characterize these animals behaviorally, and because of time, I'm not going to go into all of the individual results. I'll show you a summary slide, but we had a series of studies over 10 days, and we performed the studies in each of these backgrounds in order to figure out what the optimal strain would be for Black 6. Going into these studies, previous data had suggested it would be the Black 6, and indeed the most robust behavioral phenotype, as expected, was the Black 6, and they had both decreased locomotor activity in open field. Marble bearing is a task that looks at repetitive behavior. That was abnormal in these animals, as well as looking at motor coordination and motor activity on wire hang and rotor rod. So next, we felt like we were ready to screen therapeutics, and I think we've already discussed that the Fast Fire team interacts weekly and sometimes more if needed, and there's a lot of interaction and guidance from the entire team as well as the board on our weekly calls. And it was felt that based on this neuron compound, NNZ-256, based on what had promising results in Fragile X and Rett syndrome, there was a push to look at this compound in the animal model. So it's an interesting compound. It's critical. The compound is an analog of this insulin-like growth factor, and it's naturally occurring in neurons and the brain, and it's part of normal development. It's expressed in normal development. But it also seems to play a role in injury and stress responses. It seems to mediate inflammation, and it's seen in neuronal dendritic dysfunction, microglial dysfunction. So basically, it's involved in inflammation or modulates inflammation. And like I said, there were both preclinical as well as clinical studies suggesting it was promising in 2 other neurodevelopmental disorders. So what we did is we used a paradigm of treatment that had been used in preclinical studies with Fragile X. We treated the animals for 10 days, and we did behavioral analyses, and then at the end of these studies, we did seizure stimulation. We did studies in all 3 backgrounds, but I think moving forward, we're probably not going to use all of the backgrounds, probably just the Black 6 and 129, Black 6 for behavior and 129, and Black 6 for seizures in EEG studies. But just to summarize what we saw, this just is an overview of the series of tests that we performed. I'll show you the results of a few of these. Like I said, we got negative data in open field. There was no rescue of the hypoactive locomotor activity in the AS mice treated with vehicle versus the neuron compound. We also found that the changes in the marble bearing task, there was no rescue in the vehicle versus NNZ treated animals, and the drug had no effect on behavior in wild type. We also found that similar to what the Weber lab had shown is that the AS mice have a decreased time on the rotor rod, and there was no rescue with the NNZ compound. We looked at audiogenic and kainate-induced seizures. What's shown here are the results with audiogenic seizures. So these are the AS mice. The 2 treatment groups, vehicle versus NNZ, had similar seizures in the audiogenic induction, and none of the wild type had seizures. and there was no change in the time to tonic-clonic, as well as wild running seizures. So basically, we found there was no behavioral rescue or rescue in the seizure phenotypes of the AS mice in treatment with this agent. There potentially are other things we can look at in considering this compound, but we're also ready to move on to screening other compounds. We heard and other treatments. We heard about some of these this morning, and whether or not the Fast Fire group is, it depends on how we want to move forward, but we certainly can do additional EEG studies with the dietary ketone ester compound, but also move on to other agents. I'm really excited about being involved in characterizing seizures and epilepsy in other models, such as the pig model. I think that could be very promising. And for EEG and neurophysiology studies, having a larger animal and more cortex to record from is a lot easier in terms of performing EEG. So I think those can potentially be very promising in terms of screening for the epilepsy phenotype. Some of the other studies that we're interested in doing in just characterizing the mice and then potentially using as biomarkers would be scoring sleep. And if we see a sleep phenotype in the mutant animals, we can potentially screen agents and even look at NNZ effects on sleep. And we can hopefully potentially do that with EEG tracings that we already have. We're interested in looking at inflammation in the animal model. There's data already published suggesting that this is one candidate mechanism to target in Angelman, and we know that agents such as minocycline that have proven useful in some of the Angelman patients targets inflammation, so it seems worth looking at that, especially at the dendrites and in areas critical for learning and memory like hippocampus, and that's the last point here. And then to use all of these as biomarkers for screening novel therapeutics. And I think many of these aspects of the phenotype that I've talked about here and that Ed's talked about as well would be valuable to screen in a higher mammal such as the pig. So that brings me to my acknowledgement slide, and I couldn't have done this work without the Fast Fire funding. Like I said at the beginning of the talk, I was not a lab set up and running with Angelman mice already in my lab, so we had to rederive the mice and get them in our animal facility, learn how to genotype and then phenotype them. And it's been a really exciting and interesting road doing this. My collaborators are amazing. Every time we talk, there's always interesting discussions and debates, and really the research is very dynamic, and there's interaction with the board, and it moves forward at a quick pace, and it's really driven by the Fast Fire team and the board and all of you with your input. And of course, our children and adults with Angelman and their amazing families, and really worldwide. I mean, you in the case here, physically hold hands, but I think you share your stories and studies that are ongoing or in the works with each other internationally, and it's really very remarkable through your website, through social media. And I got to experience part of this international connection through a trip this fall with part of the Fast Fire team going to Australia to the Fast Australia meeting. And one of the highlights was really getting to spend time with those families and those investigators and doctors taking care of the patients. And Scott and I got invited to go to a kangaroo koala bear petting zoo with one of the developmental pediatricians and her patients' siblings with Angelman syndrome and their parents. And they had annual passes to the park, and so we actually got to pet one of the kangaroos. Of course, Dr. Weber was invited, but he was busy reviewing grants. I think he had study section coming up when he got home. So I want you to know that you motivate us, you inspire us as the Fast Fire team. You inspire me in my clinical work, and as a mother, as a parent, you inspire me. Of course, I want to acknowledge my lab members. Two of the main players in generating the data I showed you today are Heather Bourne and Ann Dow. And they came into the study with some Angelman background, but also with background in behavior and EEG. And there are some other lab members that help with some of the surgeries and implantations, and then my institution. So thank you. I'll take questions.
Okay, so as we switch over our speakers, if anyone has a question for Anne about her presentation, you can do it now, or we can save it for the end when we do the panel discussion. So, okay, everyone's thinking really hard about their questions. So, as we're changing over, I want to just make two quick announcements. I know there are a lot of people here whose tickets, you need to get them directly from Paula, and lunch was a little bit faster than we wanted it to be because that time always goes by when you're with friends. Paula's in the back of the room, so after the talks today, or at some point if you're walking back there, stop by and get your tickets. Take your pads and pens away with you today because they are going to clean this room out, throw everything away, and they will not be here for you tomorrow at the educational seminar unless you take them and bring them back. So please just remember to do that. Okay, so now our next speaker member of the fire team is David Siegel. He comes to us from UC Davis, and he will be talking about reactivation of UBE3A.
Okay, thank you. Can you all hear me? So we'll see if I could use this, or else I may just have to say next slide. Oh, I need to point it that way. Oh, look, it works. Okay. So what I wanted to talk to you about today was just a few short stories about some work that's in progress in our lab today, and give you an overview of how things are going. So as many of you know, we've been trying to develop a kind of transcription factor therapy for Angelman syndrome. And the basis of this therapy is thinking about how nature works. So we know that we have this situation in Angelman syndrome where there's a silenced paternal allele that's intact, but it's silenced. And so, we started to ask the question of how we could use what we know about biology to try to address this issue. And one of the ways that our cells regulate which genes are turned on or turned off is through the use of transcription factors. So we have transcription factors like this that will, it's a protein that will bind to a piece of DNA near a gene. And it can either activate that gene or turn that gene off. And so we are trying to use the same kind of tools that nature is already using in the case of Angelman syndrome. But we're able to do that by designing the DNA binding domain so we can direct them to a specific part on the DNA. And so in our case, we're going to make a factor that we're going to put in, and in what I'm going to show you today, it's going to land just about there and shut off this antisense transcript somewhat, allowing expression of UBE3A. So I've talked about this a few times before, and I mentioned that we were able to build a protein. This is our protein production, and that we can inject this artificial transcription factor into UB3A deficient mice, an Angelman mouse model. And in this case, I'm just showing you, I'm just cutting right to the end here to show this data that I think I've showed several times before, where we can inject this into the mouse, not directly into the brain, but into the kind of body of the mouse. It's able to cross the blood-brain barrier, enter the neurons in the brain, and here I'm showing UB3A expression is in green here, so this is hippocampus and cerebellum sections from a wild-type mouse that expresses UB3A. This is the Angelman syndrome mouse not expressing UB3A here. And then when we put in our therapeutic protein, we can see that the levels are turned on, kind of more like wild type. But if we put in a protein that's just a little bit different in its DNA binding domain, you don't see the UB3A coming on. And then we can quantitate that. We can show the protein levels with the so-called Western blot. And we could see that when we treat them, we also see an increase in the UB3A protein by that method as well. So we know that we have the ability to turn this gene on in the brains of mice, and that's very exciting. We also know that it has a fairly widespread distribution in the brain. And I think this is really an important benefit of our process, that we were able to successfully not only introduce this, that it crosses the blood-brain barrier, but it also distributes very widely in the brain. So at the time that I was starting this work, it looked like other kinds of vectors, like viral vectors, had a somewhat more limited distribution. But I think maybe Kevin in the next talk will offer his insight on that at the current state. But let's say in this case, we were getting some very nice distribution that you could see this intense red signal in brains that were treated compared to this kind of duller in brains that were not treated. But we were also able to measure the kinetics of how the protein came in. Because there was a fluorescent protein as part of our protein, we were able to do live animal imaging, and we could actually see the fluorescence through the skulls of these mice that have shaved heads. So the mice are alive, but we just shave the head, the hair, so that it doesn't interfere with this fluorescence signal. And then we have a machine that can actually read when the protein is there in the brain by measuring that fluorescence signal. And so we're able to measure how soon it gets in and how soon it gets out. And basically what we found is that it has a peak of after we inject it, it gets into the brain fairly quickly, but then after 24 hours or so, it's almost all out. And so, we know that it has activity, but it doesn't have a very long activity. And so this has kind of set up an important challenge in our research that we're trying to address this year. So the concern is that, if there's a relatively short duration, we would inject, maybe we would get some level of UB3A reactivation, but then it would go down. And so to show that the picture that I showed before with all the brain tissue lighting up like that, what we did is we were injecting 3 times a week for 4 weeks. So that's a lot of injections, and that's a lot of protein as well. So it became very problematic, to think about trying to move that kind of a therapy towards clinical trial. So what we would really like is to have a more persistent effect, to have something where you inject it and it has a longer duration of action. Ideally, it would be great if we could just inject something once, and then everything all the UB3A levels would come up, and we could just walk away and not have to do retreatments. So how can we do something like that? So this is story number 1. Story number 1 is about epigenetics. And again, our goal here is to increase the persistence of this therapy. So in all the cells of our body, nature has also provided us some insight on how to achieve persistent changes in gene regulation. And we know that just by studying life. So if we think about this so-called central dogma of biology where DNA makes RNA and then makes proteins, we could think of the genome as a kind of library. So it has all the genes that we need in all cells of our body. But not every cell needs all those proteins. So for example, the difference between a nerve cell and a muscle cell are the proteins that are expressed. And so if we think of the genome as all possible genes, any particular cell type might only express some of those genes. And the other genes, it kind of puts in long-term storage. So if you're a neuron, you don't need to express liver enzymes. So the cell will turn off those liver enzyme genes so that those cells are not expressed ever in neurons. So the mechanism that the cell keeps these genes repressed has to do with this field of epigenetics. So the DNA in our cells is always complexed with some other types of proteins. These proteins, we could call them histone proteins or nucleosomes. These proteins are always wrapped around the DNA, and they have little tails that come out from them. And these tails are chemically modified by other enzymes that are in the cell. And depending on what modification, what chemical group is attached to these proteins, that constitutes a kind of epigenetic code. So we call that epigenetics because it's kind of wrapped around the DNA. This information is not encoded in the DNA, but it's surrounding the DNA. So we call it epigenetic. And it's basically a chemical code, like I say. So genes that are active have certain types of chemical modifications on those proteins. And genes that are silenced have a different kind of chemical modification on their proteins that are wrapping around the DNA. So this constitutes the so-called epigenetic code or epigenetic regulation. Now, through many studies, the scientific community has identified the proteins that are responsible for writing this information or erasing this epigenetic information. And so now we can make artificial transcription factors that take advantage of this information. And so in looking at it from a cartoon, it looks a lot like what I showed you before, but I can only tell you that now this is not going to just be affecting the expression of the gene in a transient kind of way. What we're hoping to achieve here is doing the same thing that nature does when it tries to shut down genes in a persistent way. We're trying to use that same machinery now so that we can shut down this antisense transcript in a more persistent way. And so again, we're going to make some artificial transcription factors that now contain some of these epigenetic modifying enzymes. And we have good reason to suspect that this will work, because this is actually already happening at the Angelman locus. So on these genes on the maternal allele that are shut off, they're epigenetically silenced. We know that they have DNA methylation, which is a type of epigenetic information, in this imprinting control center. And in fact, that forms the basis for one of the main diagnostic tests for Angelman syndrome. In addition to the DNA methylation that we know a lot about, we also know that there's some chemical changes to the histone proteins that wrap around that DNA. And we should be able to kind of recreate what's going on over here, and all we want to do is be able to get that to happen right over there. Now, nature plays a very elegant game, and most of it we don't understand. But we're trying to do something that we think is much more focused. We just want to change the epigenetic information just right there. And we think that we can do this with this targeting technology. So here I'm showing you some new data that came from my lab, where we took some of these epigenetic enzymes and attached them to our artificial transcription factor. And what this is showing is, so these are cells, mouse cells. And in these cells, if this is the normal expression of this gene, this is actually the SNRPN gene, where kind of near where that antisense transcript is originating. If this is the level that we see in an untreated cell, when we put in that same repressor that I showed you in the earlier studies, we see maybe half of the UB3A is well, half of the transcription of this gene has gone down. And when we use these epigenetic repressors, this group out here at the end, we also see a decrease in gene expression, so that's good. And particularly this one that we're calling FOG1. It seems like the repression is as good or better than the thing that I showed you before that was giving that great expression of UBE3A in the brains of the mice. Now, what we're not showing here is if this is persistent. So I just got these results a week or so ago, and now we're going to test to see if this is going to give a persistent effect that we could maybe just treat this area once. Hopefully, we've deposited some epigenetic information in that area, and now when our factor goes away, the gene expression levels will just be set the way that we've set them. Now, this data is in cells, and we're going to look at persistence in cells. But of course, we also want to look at persistence in the mice. Actually, that's all I wanted to say. So, we're going from like a cell environment, which is, very removed from the real situation. And of course, we have to, then go back to our tested in our preclinical tool, the mouse. So story number 2 is a different way of addressing the problem. Well, let's not call it a problem. Say it's a challenge. This would have to do with in situ production. And in situ production is just a fancy way of saying that we're going to make it where it's being used. So one advantage that trying to use a protein as a therapeutic, we could call that a biologic. One advantage that this biologic should have over, say, drug therapy is that our bodies make proteins. So, we don't make drugs. Drugs have to be synthesized, and then they have to be introduced. Now, we're using our protein as a drug. We're making it someplace, and then we're introducing it. But in principle, we could engineer our body or our mouse to make this compound, this protein, and then it should just be made where it's going to be used. So we should be able to use that to our advantage too. And I think you're going to hear a little bit about making UBE3A that way in the next talk. But for our transcription factor, we've been looking into several ways of how we could get the brain to make this protein so that it doesn't have to be made and injected into the mouse on a regular interval, but it's just going to be made right there and then used right there. So one of the ways that I can share with you a little bit about today is a cell-based delivery. So the idea of a cell-based delivery is we introduce this into some cells, put those cells into the brain, and now those cells will excrete that protein into the brain, and then will be taken up by cells around it, or taken up by the neurons. So in this case, we're using a cell type called a mesenchymal stem cell or mesenchymal stem cell because this is being used already therapeutically for some treatments. Particularly, we've collaborated with Dr. Jan Nolta at UC Davis, who's a recognized stem cell expert and with expertise in these mesenchymal stem cells. And they can put them into brains, and the cells will get in. They will migrate around within the brain. They will secrete whatever they're designed to secrete and affect the neurons there. And so we've now engineered some of these mesenchymal stem cells using a viral vector to contain our protein. And what I'm going to show you is going to be our TAD-S1 protein, the same protein that activated UBE3A in the brains of the mice. And now we're going to have these cells make it, and we're going to put them into the brain. So I'm not showing you what's them in the brain yet, but these are just these cells in a culture dish. And what I want to show you in this movie is that the cells are moving around. So hopefully you can see that. So the red color here is the red fluorescent protein that's part of our therapeutic protein. And so you can see that these cells are making a lot of that protein. And you can see how they migrate around. They really crawl. So this is on a dish, but you can see them crawling around over this time-lapse photography. And so the idea is that they're supposed to give us that same kind of widespread distribution throughout the brain that we think is going to be important, since we know that UBE3A expression throughout the brain is affected. If you look at this long enough, you can actually see cells balling up, dividing, and then settling back out. So that's story number 2. Now, story number 3 is getting back to animal models. So, as you know, the experiments that I've talked about today have all been in cell culture, and there's certainly a lot of advantages of working with cells for kind of learning about things and trying to try different things. But after that, we really need to move into some kind of a live animal. So we could try to move into this live animal, but we probably have to work with some kind of an animal model first. And so you've heard a lot about the mouse studies now, and a lot of progress being made there. And up until now, the mouse has really been the preeminent model on this pathway between cells and human, apart from things like flies and other kinds of model organisms like Dr. Dindo had just talked about. But we had also said, as the FIRE team, that we were going to make a Angelman syndrome rat model and an Angelman syndrome pig model. So Dr. Dindo just told you the update on the pig model, and I'm proud to announce today that we have the rat model now. So we have the first rat model of Angelman syndrome. So the initial parts of this project were actually started a lot earlier this year in my lab, designing the strategy for excising this UBE3A gene. So we're using some targetable nucleases to do this, and we're going to make cuts on either side of the gene and just take the whole UBE3A gene out on this chromosome. And so we designed these parts, and then we gave them to this company, Transposogen, to inject into into rat embryos. So the way these experiments are done is, these things are designed, and then they're injected into a one-celled embryo. So it's the one-celled stage of the animal. And it goes in and it cuts out the UBE3A gene. And then that cell can be grown up, continued its development into a mouse. And so out of that, we're able to get animals, and some of those animals will contain the deletion that we're interested in. So the injections were done in June. And the first animals were born in July. And this gave us the so-called founder animals. So the founder animals, some of these animals will contain the deletion, and then some don't, so they need to be genotyped when they get a little bit older so that we can actually see if they have the deletion or not. So from some large number of embryo injections that they did, then some fewer were born as the founder animals. But then there can be, there's always a question of if this, even if we see that the mice have the deletion, if they're going to be able to transmit that deletion to their offspring. And so, this deletion will be continued through the mice. So they don't really consider the project successful until we get to the next generation, the so-called F1 generation, which are the descendants of this founder animals. And so the first F1s were born just in November, or that's October, I guess. And then they had to grow a little bit before they could be genotyped, but now we know for sure that we have F1s that contain this deletion, which means that now we're ready to start studying them. So I think the company did a great job for us in creating these rats, and now it's our turn to take over and start doing all this kind of phenotypic characterization that you heard about from Dr. Weber and Dr. Anderson. We're going to need to measure the behavioral phenotypes as well as the neurologic phenotypes. And what we really need to determine early on is, how much better this model will be than the mouse model. Because, of course, a lot of work has already gone on into the mouse model. So it's the thing that we know. But our hope, of course, as we have said all along, is that the rats should be a much more better cognitive model and behavioral model, and should allow us to advance our research beyond what we've been able to do up to now. And of course, we want to make this resource as widely available as possible so that other investigators in the field can take advantage of this new tool. So with that, I just want to point out the people in my lab who have done a lot of this work. So in particular, the people circled in green have worked on the Angelman, our artificial transcription factor therapy, particularly Barbara Bayless, and Ben Piles in my lab. And these are also some people now that are working on Angelman syndrome research in Australia. From the time that I was in Australia on sabbatical before, we worked with FAST Australia to actually set up their first funded preclinical research study in Australia. So I like to think now that the sun never sets on my research program. I'm in touch with Ingrid McIndoe every week by Skype. And so we have research programs going on both sides of the Pacific. And I'd also like to thank all the funding, especially from FAST and the FIRE team. And finally, I just want to say, if you ever decide to come visit my lab, we can show you the Jamie Berkeley imaging facility that we've dedicated due to a grateful donation from that family. Thank you.
Okay, same process as before. If anybody has questions for David now, we can have them now as we're getting our last fire team member and our newest fire team member wired up to give you a talk. So any questions for David, or are we saving them for the panel?
All right. Well.
Oh, Ann has one.
How old are your rat pups?
Well, they were born in October, so I guess they're a couple of months now.
Any seizures? Like clinical, just behavioral seizures?
So we don't have any information about that yet.
I mean, if they're having frequent seizures, the animal caretakers will let you know. So
yeah, so it's also important to consider. So from the founders, we had a male and a female, and we were concerned about the female because she might have pups with the Angelman phenotype. However, this wasn't a female that inherited the deletion from her mother. This was made in the embryo, and so we don't actually know which chromosome on that female was affected. And so we don't have that information for the F1s yet.
All right, let's thank David. Okay, so one of the things we've always wanted to do with the FIRE team is make sure that we could expand it to include other researchers that we think could add something to what we're working on and the work that's going on. And again, this is one of those things where we thank everyone in the audience who's been helping us raise funds and keeping our coffers filled so we can do things like this. Because of you, we've been able to add a fifth member to our FIRE team. And so today you're going to get to hear from Dr. Kevin Nash. He is also at the University of Florida, so he and Ed can work together. And you heard a little bit today from
Florida.
South Florida? University of South Florida, sorry. Sorry to football fans in the area. And you heard today also about some of the work that they're already doing with Agilis. So I'm not going to take any more time, and we're going to turn it over to Kevin Nash.
Okay. Can everyone hear me? I'd also like to thank the FAST team for actually inviting me to join the FIRE team. And I'm really looking forward to working on the project that I have, and I'm really looking forward to working with the rest of the FIRE team as well. Since I haven't been here before, and most of you wouldn't know me, I thought I would do an introduction of where I come from. I graduated at the University of Queensland, so I am Australian. Go Australia, people. And then from there, after I graduated with my PhD, I moved on to the University of Florida, where I worked for a while. And there I worked on adeno-associated virus. And what I was particularly interested in there was actually the replication of this virus. So I was looking at the biology of the virus. But while I was looking at the biology of the virus, I actually became interested in the virus as a tool for gene therapy. And in particular, I became interested in the tool for neurological diseases. And I actually started collaborating with other researchers at the University of South Florida, looking at Alzheimer's disease and Parkinson's disease. And then from there, I actually moved down to the University of South Florida to continue my collaborations. And since then, since I've been at the University of South Florida, I've continued my work on Alzheimer's and Parkinson's disease, but I also started collaborating with Dr. Weber, looking at Angelman syndrome. So I just wanted to point out some of the advantages of using this viral vector adeno-associated virus. Now, it's particularly important virus because it is non-pathogenic. So this virus, the wild-type virus that occurs in nature, does not cause any disease in humans. So you're not going to cause any problems by injecting this particular virus, even if it was a wild-type virus. You don't get a huge immune response, which is particularly important because some of the viral vectors that have been used have caused an immune response. And some of the immune responses have actually caused death in some of the studies. You can infect non-dividing cells and dividing cells with this virus, which is particularly important because we're interested in infecting neurons. We have what we call episomal maintenance, and Greg talked about this earlier. The virus does not integrate into the genome. So it remains episomal, so it remains outside of the genome, so you're less likely to integrate your DNA into cells and then maybe cause cancer to develop. You get long-term expression. So a lot of studies have looked at how long you can actually produce the protein from the gene that you're injecting. And there's a lot of studies now that have shown very long-term expression. If we look at mice or rats, you'll have expression for the entire life of the mouse. Some other studies in dogs have seen up to 6 years without any change in the level of expression. We don't have any of the viral genes present. So this is important because if you have viral genes present, you may get an immune response to those particular genes. And because they're no longer present, we're unlikely we're going to cause an immune response to the virus that we're injecting. And of course, there's the virus itself, and the production methods for the virus is well characterized. And OK, here we go. So if we take another look at the virus here, it's a very simple virus. It's what's called a dependent-virus, in that it actually doesn't replicate by itself. It needs other viruses to infect a cell in order for it to replicate. So it's a very basic virus. You can see here, it's a very simple genome. It only has essentially 2 proteins present. And we can take those particular proteins and we can remove them. So like I said, we don't have any of those proteins present in the vector that we're injecting into the animals. And then we replace them with the gene of interest. In this particular case, we're replacing it with the UB3A gene. We can also change what we call the promoter. And that's what's driving the expression of the gene. So we can actually replace that with different promoters depending on where we want to target the gene of interest. And in this case, I'm just talking about a tag. Sometimes we tag the proteins in order to be able to see them easily. So when we inject our virus, we can specifically target the protein that we're making in the cell because it has the small tag on it. So if you can imagine, here's a picture of the virus. If you can imagine, the AAV is like a soccer ball. And if you normally would see the viral DNA inside that soccer ball, okay? But we essentially remove that DNA and we're replacing it with the DNA that we're interested in. So now we have a way to inject that DNA into the cells we're interested in. I like the long pauses you get when you push the button. OK, so here's an example of an injection of the AAV virus. This is actually AAV9. So Greg was talking earlier how there's different serotypes of this virus. Essentially what that means is the protein that makes up the outside of the virus is slightly different. So there's small mutations within the protein sequence. So they actually become immunologically different. So they can, in fact, infect different cells differently. But here I just have an example of how well we can infect the hippocampus of a mouse. So this was a single injection on one side, and you can see clearly, looking at sections throughout the entire brain, we can target pretty much the whole hippocampus. And this was important for the first study we did, and a lot of people have talked about this, Jen Daly's work. We used this method to inject the UB3A gene, and in this case it was the mouse UB3A gene, into the AS mice. And we got nice expression of the UB3A gene in the hippocampus. And then we also saw restoration of some of the behavioral deficits and also rescue of LTP. So here you can see a wild type animal. When you stimulate, it maintains the stimulation. In the green down here is the AS mouse, where it doesn't have the UB3A gene, so it can't maintain the stimulation. Oh, sorry about that. And then here where we treated with the virus, you can see that we're maintaining that level of LTP stimulation. But one of the problems with the virus, of course, is it is limited to the site of injection. And if you remember when I injected in the hippocampus, you could clearly see that I was only in the hippocampus. I wasn't throughout the entire brain. So AS is not limited to one part of the brain. So we need to find ways to achieve more global distribution. So we want to get this protein therapy to the entire brain. So some of the things that I'm interested in is looking for alternative methods to distribute the virus or distribute the protein throughout the entire brain. So one of those methods that I'm looking at is using the ventricular system. So the ventricular system makes the spinal fluid essentially within your brain. And so you have this spinal fluid system within your brain, and it pretty much, essentially you can imagine that it coats your brain. So you have these ventricles here, and the system actually floats around and it goes down into the spinal cord as well. So one of the serotypes that we have is an AAV4. And it's interesting because AAV4 can actually infect the cells that line this system. So what we can do is inject the virus into these ventricles, and then we can use these ventricles to express the protein we're interested in, and then try to deliver that protein to the rest of the brain. So we can use these cells as like a small factory to produce protein, to try and deliver that protein to the cells that need it. And I'm not sure how clear you can see this, but here we have an AS mouse, and hopefully you can see that there's not a lot of staining along the edge here, which is the cells that line these ventricles. And then here you can see this dark staining here, where I've injected an AAV4 virus that makes this UB3A protein. And so what we're going to be looking at is whether we can use these cells to produce the protein and then restore function within the mice. Another serotype that we're looking at, this is actually from another group. They used serotype AAV9, and then they essentially injected it into the ventricles as well, but using a targeting down here, and it's called intrathecal injection. So you still end up in this spinal fluid, but this virus has the ability to actually pass out of the spinal fluid and then infect cells within the brain. So you can see here they show that there's expression throughout the brain, and they're getting neurons and other cells targeted throughout the brain. So we may be able to use this system to have these particular hotspots, we could call them, or factories to produce the protein again and deliver it to all the other cells within the brain. So we don't necessarily have to target all of the brains with all of the cells in the brain with the virus. We can target some of them and then have those produce enough protein for the rest of the cells. And then one of the last thing that I'm looking at is looking at pathways within the brain. So we know that the brain is not just different regions that don't talk to each other, they don't interconnect. Of course they interconnect. And so there's particular pathways that make different connections within the brain. And so I want to target some of these interconnecting pathways to see if I can make protein. I can infect a cell in this region here, it'll make protein and deliver it to another part of the brain. And I hope you can see here where I targeted this region of the brain here, what it's showing here is actually a green fluorescent protein and not the UB3A protein. So we typically use this as a control to set up and see how well it works. But you can see when I inject in this region here, I'm getting expression in many other regions of the brain. And so I'm getting spread from one particular region where the neurons branch out into other regions of the brain. So hopefully I can use this technique to infect these cells with UB3A. Then those cells will project, they'll deliver the protein to the other regions of the brain, and then hopefully those cells will take up the protein and then restore their normal function. And I didn't have much time to make my acknowledgement slide, but since I was a little busy this morning working on a grant, but I'd like to thank Ed Weber, Jen Daly, and a couple of members of my lab who are help working on this project at the moment, Christian and Mindy. Thank you for your time.
Okay, what we're going to do... It's on. What we had planned was like a 10-minute break, and then we were going to come back for the panel. I'm going to make an executive decision not to have a 10-minute break. We're just going to start with the panel because we're a little bit late anyway, and we're going to run out of time. And if we get done with all of our questions early, then, you know, more drinks at the bar. So if I could ask the rest of the fire team to come up, and then if you guys have questions that you would like to ask the fire team, we can get started on that. And I do have one for Kevin already from online. So, yeah, so you had mentioned that you were going to make the UBE3A in factories and then get it out to the rest of the brain. Someone online said, well, then how is it going to get into the cells to actually do its job from the factories where it's being produced?
Well, I don't want to get into all the details, but it's very similar to what Dave is doing, actually. And we put these tags on the protein, and the tag will not only tell the UB3A, oh, I need to get outside the cell, but there'll be a second tag that says, oh, I should go back into another cell. So essentially, we're tricking the system using its own mechanisms in order to make the protein for us and then engineer it so that it gets taken up by other cells.
And we had another online question for Dave Siegel. And the question there was, can you explain how your approach is different than the antisense approach that's being taken by ISIS? ISIS, the company, not anything else. Yeah, I think they're working on it.
Can I? Oh, I can. I can just talk into this. Right. So ultimately, there are different ways to reduce the antisense from silencing the UB3A gene. So the antisense is one method, and we're trying this transcription factor approach as a different method. The antisense method is an anti-RNA approach, in that the antisense goes in and what we believe is happening, we being the scientific community, I think, is that it's actually cutting off the end of that RNA, that antisense RNA, and not allowing it to somehow interfere with the UB3A. Ours is to try to reduce transcription of that antisense from the point where it's actually made. And you know, there might be pros and cons of either method, but theirs a little bit further along, and that's very encouraging. So I would say that ultimately It's another method to inhibit that antisense RNA and to reactivate UB3A in the brain.
Thank you, Becky. So I have a hypothetical question, which I'd like each one of you to answer if possible. So let's assume you each have a child with Angelman, and you each have $10 million in a bank, has to be earmarked for Angelman research and development. So you have a child, you have the money, where would you be spending it right now?
And I guess you're not allowed to say on your own work, or?
You certainly could. I mean,
Oh, okay.
it's open, so it's your money, it's your child.
Well, this will be fun.
Do we start?
Go, Scott.
Is this good?
Yeah.
So I think, Sharon, you asked this question, didn't you? We've already been asked this question. And this is actually where, for me at least, this is where the FLY project came from. I felt that would be, now $10 million wasn't on the table, but in terms of identifying something that, or a method or an approach to finding a new therapy, that's one that I felt that would be the best opportunity to maximize your chances to identify something. And then those that are found there then move into the other models. But that was my answer at the time, and that's really where that project came from.
I'd probably give it to FAST, actually.
Of course. Your check's in the mail.
Yeah, I mean, it's a difficult question because there's a lot of horses in the race, right? So, it's funny how, at least in my experience, you're looking at one line of research, and then from that single line of research, there are several different things that come off of that. I think that this is one of the, as you well know, the kind of organic parts of science. And so it's really difficult to say, what you'd want to put all your money into. It's probably better, as was mentioned earlier, that what we're going to probably be seeing in the future is multiple therapeutics that are going to be targeted at different areas. So I think it's almost better not to put all your money onto that one single horse. That would be my answer. But FAST is the number one.
Yes.
I have this there.
I agree with Ed. I wouldn't.
Sorry about that. I agree with Ed. I wouldn't put all my eggs in one basket either. But I certainly would fund my own research. I believe that gene therapy is definitely an up-and-coming tool that could be very useful. I mean, not in the immediate future, but maybe 10, 15 years from now, once we get things perfected. But I think that other avenues of research is also important because you may have to target more than one thing in order to get a global effect. You might not get that with one treatment.
So without trying to sound like I'm saying the same thing, I would think that, the question kind of is asking, if we weren't resource limited, is there something else that we would be doing? And it's hard for me to imagine, that what else we could be doing at this point as a community. Of course, having more money always makes it go faster, I suppose. But, we have a lot of very interesting basic, kind of preclinical research going on here, investigating things in a couple of ways. Even the last question that was asked, what's the difference between the antisense therapy and what I'm trying to do? I mean, you see multiple different ways being applied here so that in the end, that it's not just my way or, Kevin's way or, one way that we're just going to put a big bet on that and say, that's probably the one that's going to work. Let's try that. I mean, at the end, you're going to know that we're having the best therapies or therapies that can apply to as many people as it can because we have many different kinds of efforts going on. So I guess something that might be nice to see is if we had even more people involved in doing the research, if we had even more companies involved. But, the number of researchers that are working on this, sitting here and then also around the world is, I think, very exciting now. With all the advances that have just been made in the past couple of years, and seeing all these companies at this meeting now is also really very exciting. I mean, just in the short time that I've been involved here, I think this is a tremendous development, to have people that can really move things to market, coming to this and starting to make a difference. So, could we apply that money and make things maybe go faster, maybe get more people involved or something like that? But I think that already we're seeing a lot of different approaches being tried and explored, a lot of different ideas, and then a lot of dedicated people, especially the families, right, that are supporting all of this research, because that's where a lot of the money has been coming from now, and a lot of the energy to do this work as well. And so, everybody has a role to play in this. Like I said in the past, you feed off of us, we feed off of you. So I don't know what I would do with the $10 million, except maybe try to give it out and see that we can do more of what we're doing.
Yeah, I agree. Diversifying the investment, trying to get more people involved, but that's basically what's already been said.
So can I add one thing to that? I think one thing that I wish we could do, I don't know there's a way to do it because it's not very directed, is I wish we had enough money and enough resources to start going through all kinds of either FDA approved drugs or things like OV101 that have been through a certain amount of work and maybe could go further. I think right now we're having to do a little bit of picking and choosing as to which of those compounds we look at, and sometimes we get lucky and sometimes we don't. But it would be great if we could do that a little bit more unbiasedly and just try everything. It's not realistic, but that would be one thing I think we're not really doing. Allison. Tina?
Hi, my name is Tina Thompson. I actually have a question about maybe more directed toward the Ovid panel this morning. Is that kosher to ask now? So I heard two things during the presentation this morning. One was a reference to animal models and how OV101 had worked on the animal models, and then I'm not sure if I picked up right, but at some point there was a dosage question and there was a reference to using 1/10 of the dosage of Alzheimer's patients. So I'm not aware of either OV101 being used either in animals or on Alzheimer's patients, so I wanted to just hear a little bit more about what had been done there and what the results were.
Okay. Yeah, so sorry to the panel. Yes, I was happy to take that question. When the drug was first discovered, it looked like a GABA molecule, and it was a time in the history of neuroscience where we didn't have the full understanding we have today, approximately 20 years ago. And at the time, we did know that certain diseases of the brain had deficiency of GABA neurons, Huntington's being one, Alzheimer's being another, where there's a loss of GABA neurons in certain parts of the brain. And so the simple, naive idea at that time had been, this drug looks like a GABA molecule, let's just give it to these patients and hope and use as big a dose as we can. So they started with doses 10, 20 milligrams 4 times a day, escalated up to 120, 160 milligrams a day. And the patients were still walking around for the most part and still okay. So the drug was safe, but they did very short studies. These were open label. They were in very severely affected individuals, and so they really weren't pursued. And in retrospect, they weren't well-designed studies. It was used in many other indications. It was used in pain. It was used in one trial in epilepsy. It is an analgesic. It does have anti-epileptic activity, but none of those really stuck, and it really didn't really pursue from a commercial point of view, from a drug development point of view. None of those indications really looked ideal. And it really wasn't till this concept that it acts on the selective extrasynaptic pathway, which is a much more recent finding, that all of a sudden there was a sort of crystallization of two events. One, understanding what we call the molecular pharmacology of the drug, so we knew exactly where in the brain the drug was working, not just like a GABA molecule. And secondly, an increased understanding of the biology of this disease and biology of Angelman, and those two bits coming together. And really, the reality of the drug really wasn't used in the animal model specifically as a therapeutic. It was really to prove that tonic inhibition was important, and restoring tonic inhibition could improve some of the function of that animal. So really it was that basis, and seeing that biology and seeing parallel studies occurring in many organ systems, both flies. There's some very recent papers now showing that if you can actually use Drosophila, not Angelman Drosophila with other cognitive deficits, you give OV101, you improve the cognitive phenotype. If you give the drug to Fragile X mice, you also improve them. If you give it to Rett syndrome mice, you also improve Rett syndrome. So all this data sort of accumulated to a point that we felt sufficiently comfortable with the drug, with the pathway, that we felt it was appropriate for us to move towards the clinic. So I hope that sort of helps a little bit.
Yeah, thank you. Okay, Allison.
I'm going to first thank Dr. During and Ovid for donating $10 million to the FIRE team at FAST, and we'll all be proud to take that. But along the same lines, actually, my question does go back to that. Knowing, and I asked Scott this question yesterday, but I actually want to ask all of you the same question that I asked Scott yesterday. You know, the title of our organization is FAST, and obviously things are moving very quickly with that title, and it's, for us parents with children with Angelman syndrome, it's not fast enough. And even though it's quicker than you've ever seen before, what is it that could be done, or what is the rate limiting step to make this faster? If that's 3 months faster, 6 months faster, 2 years faster, is it money? Is it time? Is it personnel? Is it the science? Is the rate limiting step things that cannot be moved any faster, or are there things we can do? Because I think financially, the iceberg hasn't been touched with what we can do and what we can raise. And I think if we knew what we needed to make this move faster, I think we could. And I think we need to know what that is.
Yeah, as far as rate limiting steps go, taking something to clinic, I think that that Dr. During addressed that earlier today. I mean, you can only go so fast through making sure that something is safe, making sure that you get approval through the FDA, going through, you know, all of those steps. You know, what can you do to make things go quicker? You know, I think for now it's some of what Jody talked about, the registry, making sure that everybody is registered so that when the clinical trials come on board, it's going to be easier to find those patients. You know, coming out with good outcome measures so that it's not you don't have to replicate a clinical trial over because you didn't do the right outcomes. You know, I think that being proactive in that way is going to save us time in the future as well. But I think we're at a point now where things are changed. I mean, you can see there's companies up here that are talking about going forward and how fast they want to go. But there are limiting steps. Sometimes it's not the science; it's just how those things work to get to clinical trial. So, but I think we can be proactive now to save time in the future.
But what about like with the FIRE team? What does the FIRE team need to be moving some of this stuff from just getting started or just getting good results to being able to pass it off to an Ovid or an Agilis?
Yeah, well, you know, I think that just, you know, Scott and I are both doing drug discovery. I mean, if you had a whole team of people doing drug discovery, it would go much quicker. You know, there's subtleties here too. So one of the things that Scott and I talk about when you're doing drug discovery, it really is kind of a fishing expedition. You're looking at, you know, thousands of different drugs. Some of you don't even know what they are. Some of them are soluble, some of them are not. Some of them are yellow and green, and you don't really even know what you're putting them on cells, and you're hoping to see a result. You're trying to do this as quickly as possible, but this isn't hypothesis-driven science. So in order to get that science to get moved forward, it's difficult to give somebody with a lot of training that kind of a task, because this does not promote their career. This isn't something that they can publish. It is just grinding work that takes a lot of time and energy and effort. And a lot of times you have to do that with volunteers or technicians, somebody who's not at that higher level. So, you know, that's what throws that into a much slower process. And Scott would agree with this.
But we also have this whole idea in science with the brain drain, right? There are plenty of people who get through with their postdocs and there are no jobs for them, right? I mean, we know this. So if you had the money to pay somebody a decent salary to come in your lab and be an expert, technician to screen drugs.
Yes, most certainly. Yeah.
Okay, well then let's do that.
You'd have to do that.
That's what we need.
More money you could definitely throw more money at that and more personnel at doing something like the drug discovery work.
Yeah, so what one of the things Ed's talking about, for those of you who aren't thinking about academic research, is that we get graduate students and postdocs into our labs, and it's being an apprentice, like a journeyman. And so we give them projects for them to work on and work their skills out and use their own intellect to move them forward, and then that's supposed to help them get their own job. And so you can't give them something like, go look at 10 things and see if something works, because if it doesn't work, you've kind of killed their career prospects. So, in that way, probably money for people who are experienced and want a job but aren't going to be hampered by this kind of project would be helpful.
And it's also not something that would be funded by NIH because it's not
Correct.
hypothesis driven. They don't want to fund a fishing expedition, look at 10 or 20 or 50 things and see if something works. They just won't fund that.
So
right or wrong, it doesn't happen.
Yeah,
that's
a mistake.
That's exactly the second thing I was going to say, is that this is where foundation support is just invaluable, and you can take that money and do things that are high risk but potentially have a high payoff. And so the more money that you have to do those kinds of experimentation and research, the more likely you are to get that one, big, huge hit. When you're writing grants to the NIH, it has to be bulletproof, and funding right now is very, very difficult. So it almost has to you almost have to propose things that are going to work, and they know are going to work. This isn't how science should be done. We should be taking bigger chances. The foundation money allows us to do that, so we can come up with really innovative ideas that are potentially high risk, but could have a huge payoff. And you never know what that next identification of a therapeutic may be in order to move that forward and attract another pharmaceutical company or another biotech company. The work that Jen Daly did was not on an NIH grant. That was actually a foundation grant that we got. And now that science really kind of drove things forward for Agilis to come and talk to me and get interested in the research. So that kind of money, it's hard to say, well, this is exactly where I would put it, but those kind of ideas that get funded really can drive the science quick.
I think what slows down a lot of, especially the research that I do, is the animals. I mean, they are animals. You have to breed them, you have to grow them, you have to wait for them to mature in order to use them. And you also have to screen them and make sure that they're the correct animal. I mean, we have to make sure they have the mutation. We don't want to use animals that don't have the mutation. So there's a lot of time and effort and money that goes into maintaining the animals and making sure they're healthy, making sure they're growing, making sure we're getting more of them. And that's also a big expense that we have to also consider. And it takes a lot of time. Because even the studies when I do the injection, I don't do an injection and then the next day I analyze the mice. I have to wait for them to produce the protein to see if there's an effect. And sometimes some of the studies we do, we wait months and months, 6 months, waiting for that effect to come through. And so each day we have those mice, that's more money that it costs for us to maintain them within the facility.
Dave or Ann, either of you want to add to this, or should we move on to the next question?
Just to say that I think that, something that you could do with the money is just involve more people. So more people in the lab work, more people coming up with ideas, more people. Yeah, you could use the money for more people.
Yeah, it takes an army to do things the correct way, and you don't want bad data. You want it done right. Behavioral studies like what Ed and my lab do, you have a large sample size, and I mean that's just what's required, and it takes a whole lot of time.
So personnel, and so this is why we were saying this morning, we still need you to fundraise for FAST. We still need money. There's places for that money to go that's still going to be important for us.
I want to know as a parent how we can help, and if you guys, gather what kind of information, testing that you can help quantitate. Eventually, what kind of testing would you like to have our children for baseline testing? So if we go in yearly, we have the new AS clinic in Mayo. We'd love to have that voice output or the gait monitoring data that you were explaining earlier, what kind of things would you like for us to start, that we can maybe start collecting baseline data?
We'd like to have a symposia. Jody is kind of spearheading this whole thing with Agilis, and what I think we're trying to get is a consensus from the clinicians, from other people, to say these are the things that we can start looking at and establishing baselines now for the next upcoming clinical trial, and that we can use. And it's going to be a whole kind of menu of different things that we want to establish, be able to look at, to refine, get people's input on how to do it and how to do it correctly. And then those things can be chosen for a particular clinical trial depending on what they're looking at or depending on what's being targeted. I think what's important now is really the first thing is the registry. So the registry is going to be huge, and it's not just a U.S. or an Australian thing. The registry is going to be something that is going to be, people from all over the world are going to be able to register, have all that information put in, so that when clinical trials come up and they go outside of the U.S. boundaries, people know what's going on and can be part of that clinical trial. So I think that right now we will be asking the community, this is what we need you to do. We need you to come in and help us establish those baselines. But for now, we just really have to come up with some kind of a consensus on what those baselines are. Okay. We're all of the idea that new outcome measures are needed. Yeah. So now we need to really work on what they're going to be, what they're going to look like, and what can be FDA approved for clinical trial later on.
Okay, thank you.
So just to follow up on that, as a clinical provider, I fight daily. Even here at this meeting, I'm fighting with insurance companies for reimbursement, for approving, pre-authorizing a test. And I think the reality of this is that it's going to take time to do each one of these studies, to do the gait analysis. And the hospital and our academic institutions won't let us do anything for free. If it's research, there has to be a research dollar that covers our time, that covers technician times, that buys the space to do the test. So I think with our $10 million, part of what would need to happen is to sponsor once a group has met and there's a consensus on what's needed in terms of additional phenotypic characterization, then and even genotypic characterization, then we're going to have it funded. There may be some cases where insurance will cover it, but they're only going to cover it if, as the provider, I can say I need this test because I'm going to do X, Y, and Z with the results. And they get stricter and stricter with what they will authorize and cover. So, and we can't have our community of families stuck with huge bills for the characterization.
Is the pig ready now? Oink, oink.
It's like, there's so many jokes that I can make of it. No, we're in the first process of it. So, as I mentioned, they have some data suggesting that it's been deleted. The technique that was used, very similar to what Dr. Siegel described. And so from there, then the animals are cloned, and we just wait for that to happen. So we hope, there are no guarantees on any of this. He is one of the best, if not the best, in the country or the world. But that sometime in the spring, we'll start seeing pigs.
Do you think
spring pig?
Mm-hmm. Would that be before it's even needed? It kind of sounds like it is.
That would be good.
Yeah.
Yeah, you want it before you actually have to have it.
Yeah. Anyway, I have a question for the last person. I'm sorry, I don't remember your name. But
Yes.
If the patient has an issue with their brain, like an intraventricular hemorrhage, or if they have some other brain malformation, would a medicine delivery that goes into the brain, would that not work on certain people maybe? I don't know if that makes sense, but.
Yeah, you're saying if they have some sort of defect, maybe in the ventricular system or something like that.
Yeah.
That is difficult to say. It depends. I would assume if it's just a structural thing, it may not be a problem because you would still have the cells lining the ventricular system, and those are the cells we're interested in affecting. So they still may be functional, and we still may be able to produce the protein, but without knowing exactly what the problem is, it might be difficult to say. But that's why we're trying different approaches. And so maybe that particular approach may not be very useful for that patient. We may be able to try one of these other approaches in order to achieve something similar. And then that way we can circumvent that problem.
Thank you. Matthew?
Sorry, well, I don't want to, this is really the forum more for the family, so I don't want to take up too much time. But I guess just to go back to your point, which I think, when I first moved into the Angelman area, I could say, and look online and go to PubMed and look, there's a lot of great science in terms of animals on UB3A, but there's a paucity of good clinical studies. And I'm not just talking about intervention, but we really don't have a good understanding of the clinic. We know a lot more about the mice, far more about the mice than we do about the patients. And I guess what I'd like to ask again, each of you, is to think about, again, what would you really want to know? What is missing from the clinical data out there that would really help shape and advance your research? Because I think there's some huge gaps out there. I'd really like to know your thoughts in terms of what you think is missing, not just in terms of patient registries and what you're doing, but what would you really like to understand about the disease and about the patients as opposed to a pig or a mouse or a rat at this stage?
I think one of the for me, it's why there's such a variation in Angelman syndrome if it is monogenic. If it's just one gene, why are all these kids so different? So that understanding of gene-gene interaction, what makes one child be able to learn to walk when they're 2 and another child not until they're 11. There's such a wide variation in the symptoms of Angelman syndrome. There's got to be other interactions in there. I find that it's got to be very complex, but a very fascinating area that really has not been touched.
Yeah, we talk about this a lot online, right? There's 20,000 other genes that go into making up who you are, and they have to be influencing this on some way, just the way that Dr. Weaver was saying. So,
I think for me, there's 2 questions that I'd like answered in terms of like a gene therapy approach. The first, I'm just making sure this was on. The first question is, do we need to target the whole brain, or is there particular structures in the brain that are most critical? And if we can target those only, would that be enough to affect the quality of life of the patient? And the second question is, do we need the entire protein? So UB3A gene is actually quite big, and the protein is a fairly large protein, but it has different domains. And the question is, do we need the entire protein? Because sometimes if we can make something smaller, it might be much easier in order to generate the therapeutic that I'd like. So if I can reduce the size of the protein that I'm making, it may be much easier for me to get the therapeutic benefit that I need. But right now we just don't know, do we need the entire protein, or is it just some of these domains within the protein that is critical?
Well, on a research level, I would like to know how loss of a ubiquitin ligase leads to the symptoms that we see in kids. I think we have a description of what Angelman syndrome kids are like, and we know this gene defect and the gene that's involved, but actually going from that gene defect to the things that we actually see is not a clear pathway to me. We know that UB3A has a lot of targets. We don't know what all of them are. We don't know what are the ones that are most critical for causing the disease. And so I'm often struck by the fact that there seems to be this kind of phenomenological level, kind of like Dr. Anderson here, measuring the EEGs and things. And this kind of genetic level where we know what the defect is. And then there's a whole region in between where we don't really have a good connection between how the loss of this ubiquitin ligase is causing the things that Dr. Anderson sees. So if we knew all the parts of that pathway completely, that may provide other therapeutic targets, or it might provide a much richer understanding to start, thinking about to develop therapeutics in. But that's on the research level. On the clinical level, I imagine the kinds of things that we would need are the kinds of things that were brought up this morning. We need good outcome markers. Like all the studies that I show where you could see UBE3A coming back onto the brain, obviously that's not something that you can do in a person. You can't see the UBE3A come back on in a person because you're not going to take the brain tissue out. So, what are those clinical markers that we need? What are the biomarkers that could tell us how well the therapy is doing, or if someone is going to be more severe or not? Those would be nice things to have.
I agree. I mean, along the same lines as what others have discussed. I mean, my big question is related to epilepsy. Why do some children have severe epilepsy and they go into the subclinical or subtle clinical status epilepticus? And what's different about those AS children or adults compared to the ones that maybe have a few seizures or pretty well-controlled seizures, or that have no known seizures at all? Is it related to their mutation? I think we have enough data, even though it's not comprehensive, to suggest that, well, those that have the GABA receptor included in their mutation, yes, those children often have, or AS individuals often have worse epilepsy, but we also know just the UB3A mutation itself can be associated with severe epilepsy. So we really don't understand the basis of that part of their phenotype. And if you're continuously seizing, that likely affects your cognitive phenotype. And you as parents, I think, know that. You probably know when they start having subclinical seizures because you lose the interaction with your child. So if we understood that, I think we could direct therapies better and maybe come up with a cure.
Okay, thanks. I actually want to ask a question about the outcomes, and forgive me if I'm misunderstanding. So when you're submitting for approval, you want to submit certain outcomes to the FDA so that we can approve the trial of the drug. Is that correct? Yeah.
So yes and no. So you can, for your primary outcome, you have to get approval for that. So you can't just come up with any outcome that you want. For secondary outcomes, you can change that. So you can look at a lot of different things. I think that the key here is, I think there's a lot of confusion on, even from us and clinicians, on what you need to do and how you need to get that approved so that you can have that as a primary outcome measure. So, there are defined primary outcome measures that are FDA approved, like the Bailey's, like the Vineland, the same ones that I used in the minocycline clinical trial. I think the key here is that those are not specific to Angelman syndrome, and the NIH has even come out with potential grants that you can apply for to come up with new outcome measures specific to different cognitive disorders, Angelman being one of them. So I think they understand the need, and they're trying to actually come up with ways to standardize outcome measures so that clinical trials can be assessed across the board. They can be compared a little bit easier. But I think the problem that I found in the clinical trial that I was involved in is that those outcome measures are not geared and not specific to Angelman syndrome, and I think that's what we need to do. So how we do that, how the best way to do that, having FDA input into this once we come up with these ideas, I think is critical. But from what I showed you earlier was strictly to show that there are ways that you can look at different outcomes, and you can do that in a way that's not subjective, and I think that's really what's needed.
Sorry, this is probably more a comment than a question, because isn't it that we're trying to get a therapeutic out there specifically for Angelman syndrome that is going to improve the motor skills, the fine motor skills, the hopefully speech, that kind of thing, no epilepsy or reduce the epilepsy levels. So how would you, I mean, can't even format the question, how would you put that to the FDA and say, this is the outcome we want, but this is only, I mean, you know, like, this is across the board. Is that making sense? No?
Matt, do you want to answer that?
Sorry.
The problem, and Ed and I have discussed, and I think Ed's done really some pioneering work that he presented some of the data here, which is really a great step forward. There's multiple issues here, because remember, if you're looking at within the Angelman community, there are patients who can't walk, there are patients in wheelchairs, there are patients who need sidearm assistance, and so you've got this incredible variability from the first place. So if you say, well, let's look at the gait, the other point is that only certain subjects will be able to go on the gate. There's lots of endpoints that have been used to approve other drugs, but they're not really relevant to this population, as Ed has stressed. And you know, for us, the issue is really one of, you also want to say, what is the change in that endpoint? You can measure someone's along the gait, but does that really reflect clinical significance at home in terms of lack of falls, in terms of independence, in terms of mobility? So whatever endpoint you choose has to be relevant to the real world. Is it really something that clinically stands and is meaningful? So these are really difficult questions. And I can tell you that one of the most advanced companies in the rare orphan space, a company called Ultragenics, has developed a whole team, and that team is just entitled endpoints. That's all they do, because that is how important this question is. So I take my hat off to Agilis to work on this. We clearly at Ovid are taking this issue very, very seriously. And as Jeremy said, this is something we do in partnership with the FDA. Ultimately, the key is if you believe your drug works and if you can show it's safe and effective, many of these questions won't get answered until much later in development. You really want to design a trial that you hit certain endpoints, and if you believe the drug is good, then move that forward. We're taking this extremely carefully. It's one of the things we're spending more time on than anything else. And we think we have a handle of how to move forward, but again, it's early. We need some more refining of that, and we're doing this in partnership with FDA. I don't know if you want to discuss.
Your question is absolutely pertinent. For example, in a cancer trial, there are really two measures. Question number one, does the tumor shrink? Question number two, does the patient live longer? That's kind of it. In somebody who has, and that's simple, and there's a huge long track record of that. In congestive heart failure, which is just as fatal as cancer, you have a walking test. You have certain biometrics that you can actually easily measure. What is the oxygen in the blood of the patient? You have clear measures that have been around for a long time. Here, just as Matt says and as Ed has said, we are actually broaching a new field. You have patients, as I understand it, as old as 70 years old, and as young as we heard this morning, months old, days old even. Each one showing different types of symptom. So somewhere in that, and no track record of any substantive major clinical trial through the FDA. Very important to understand that. So we have to educate the FDA. Very important to educate them. Very important to ourselves understand what it is exactly that is important and for which age group and how we're going to approach that. And then as we do that, to then think about real metrics, and we heard a lot about metrics, which I really loved that discussion. I thought it was a great discussion. What do you measure? What do you actually measure? When a child can't get out of a wheelchair, well, you can't measure motility. This is really a tough one. So I think as we look at this, the work that Agilis and others are now doing, and the NIH and ourselves, hopefully we will craft the right approach for the beginning. I can assure you that as the therapies that you've heard about here evolve, and they're very exciting to me, incredibly exciting to hear this actually, you will have to start developing, or we will, not you, we, sorry, get this right. And Matthew, you're giving me $10 million? Tomorrow, thank you, because I know what I want to do. The question is, how will we together craft the right endpoints for the right age and for the right therapy, and to make sure that they don't negate other therapies. Very important that, because once the FDA gets into its head that there's only one measure, there's only one measure. It's very simple for them. So we're asking them to be quite sophisticated, and I think they'll be a very good partner, actually.
Thank you. Thank you.
Yeah, you also want to keep in mind that, you know, we talk about the FDA as this big barrier to some of the stuff that we're doing, but they're ultimately tasked with making sure that nothing dangerous happens, especially to people in clinical trials, especially to children. So, you know, it's good to partner with them, and they will hold you to a very high standard, and I think every parent and grandparent and caregiver in this room and sibling wants a very high standard.
Okay, I actually have two questions. My first is, we had a question earlier about what still needs to be done, because as parents, we want things to be done as quick as possible to fix our children, or not even really fix them. They're perfect how they are. But how much time do you think that doing collaborative research has saved our community from not having an answer? And how much time do you propose it will take? Sorry, writing a dissertation on this title.
No, these are great questions.
The second question is difficult. I mean, how long it'll take, you know, you always think it's going to happen much quicker than what it does. Science is a really, really slow process. It really is. I gave a talk one time about a science experiment of dripping tar that's in a museum in England that's been going on for 100 and some years. You know which one I'm talking about. So, you know, science it's not quite that slow, but it's a slow process. But the collaborative nature, I mean, what you're looking at up here, you know, this whole thing with the AAV and the virus, that never would have happened if Kevin wasn't there to help me. He's the AAV guy. You know, I've got an idea. He has the expertise. This is where the collaboration comes together and really moves forward. We wouldn't dream about doing another large animal. I don't have that expertise. You know, I don't have the expertise to make a rat that I can do some of the more complex experiments that I have in mind. Dr. Siegel does. One of the things that we were looking at, and I'll tell you, the disruptive nutrition and the ketone ester, that was a random thing. Dom D'Agostino was actually sitting on my student's dissertation committee and said, "Oh, you ought to try this. This is, you know, this new material that we have." We saw the potential in doing that, but I have no expertise in seizure whatsoever. And does. So, you know, that kind of thing drives the science much faster than me learning all those techniques, understanding that type of a field and doing it all by myself. I mean, nobody's an island, and those kind of collaborations moves the science much quicker. It's hard to quantitate and say, yeah, it's increased the field so much, but I think the exponential increase in publications and how fast the science is going in the different directions is a direct result of the collaborations. And, you know, that's hard to kind of put your thumb on and say, you know, this is how much time we've saved. But if you think about 30 years ago or 50 years ago, when not even that long, before the internet, when, you know, the way that information, scientific information was disseminated was through a journal, that you had to go to the library and go, let's see what, you know, Journal of Neurochemistry has this month, you know, and you'd flip through and go, oh God, look what they're done. You know, that research was done 2 years ago. Now with conferences, the internet, and PubMed, that information gets disseminated very quickly, and it can influence your research quite a bit.
Can I just say, the old adage, you know, 2 heads are better than 1. And so, you know, when you have 5 heads, it's much better as well. And because sometimes when you're looking at a project, you're seeing it from this perspective. But then when you collaborate with someone, they see it from this perspective. And they see something that you don't see, and then they can find things that you're missing that you may be doing wrong. The other advantage of collaborating, in my opinion, is you hear about negative data. So when you're a researcher, you never publish anything that doesn't work. So I'm sure there has been experiments that have been repeated many times in many labs just because no one reports the negative data. But at least if we're talking with each other, we're not going to repeat the same experiments that may fail. And so we can save time by not repeating things and then working on things that are working.
Can I just share a quick story? When my daughter was diagnosed, she was about 10 months, 11 months old. And I talked to Art Bodette like 3 days later and said, I thought he was going to tell me that, it's too bad, it's a horrible thing, and here's the science. And what he said to me was, do you have her in any of the natural history studies? Have you thought about doing the betaine folate trials? We will have clear roads to therapeutics in 10 years. And I wasn't expecting to hear that because that's not what I was seeing on the internet. My daughter just turned 10. So I think he was right about that. There are people in this room who have been diagnosed more recently, and they are being told by people in sort of a general way, we think we'll have therapeutics for your kids in 5 years or even 2 years. Things are changing, and they're changing pretty rapidly.
I found that in my own research. But my second question actually is more directed to Dr. Anderson, and may not actually fit right here, but it's the only time I have to ask it. So tell me how an EEG would change over a period of time. Like, it was a typical EEG for a kid with Angelman syndrome to it's perfectly normal with a different doctor and a different EEG.
It's hard to say without having the same doctor reading it.
Right.
People have different skill levels. It happens within our group itself. The more experienced EEGers have seen a lot more children with Angelman and can spot an Angelman, an EEG consistent with Angelman syndrome very quickly. The variations, and our less experienced readers are getting educated on it because we do see a lot of EEGs from children with Angelman. So I would pull both of them and have one person read them.
That'd be great, but neither one of them are here anymore. So it's just a question because we don't even have a neurologist where we live anymore. So we have to travel. And
where do you live?
Central Illinois.
So
Talk to Paula.
We also know, that slow spike and wave that's sort of more frontally, that can suppress. It could suppress with medication, or, it could be much more evident if your child just got vaccinated or has a cold and is febrile. And then when they're feeling better and they're very alert and not having seizures, the EEG might look much more, normal.
Okay,
thank you. We know there's a lot of variability from EEG to it's
Right.
sampling error. You're not doing it continuous on your child like we are with the animals.
Right. Thank you so much.
Okay, so in the interest of time, these can be our last questions. Anna?
Yes. Gene therapy still sounds like science fiction to me, and I know there's a lot of concerns about genetically modified food. What happens in terms of measuring side effects for gene therapy? Is there like a lot of science behind this already, or is this a new area?
It would depend on the gene therapy approach. There's with AAV, there's hundreds of clinical trials right now, I think. It would depend on what the clinical trial was for and what sort of side effects you'd be looking for. I think one of the things that we would have to look for is, maybe immune responses, inflammation in the brain, things like that. But you would have to have some sort of outcome measures again that were just measuring, neurological function. You might be looking at, EEGs or something like that to see if there's any changes in that sort of thing, so you're not generating a problem. And one of the problems might be if we make too much of the protein, we don't know what effect that would have. But we would think it would have an adverse neurological effect, so we would be looking for something like that.
You mentioned there's hundreds of clinical trials. Is there anything in market which is a virally...
That is probably better to answer that question than me. Matt's been in this field for like decades.
The only approved gene therapy in the Western world is an AAV for a sort of a cholesterol metabolism, a rare disease, a lipoprotein lipase type AAV for Glybera, it's called, and that's a company called Unicure. So there's nothing ever really got through the approval process here in the US. we have we've run trials in Parkinson's disease with a lot of work, and there's some overall the safety record of AAV. We used to always talk, and I've worked on AAV now for over 20 years, and we used to always go up and say from the stage, well, gene therapy hasn't worked yet, but we haven't killed anyone. And in fact, that for a long time was true. Then there was one case at University of Pennsylvania where a child had adenovirus and had an overwhelming immune response and a total sort of organ failure, and that was back in now 99. Since that time, a few cases using retroviruses where it's got into the bloodstream, and we heard today a lot of discussion about the question of integration versus non-integration because of the vectors that Kevin's using and Ed are using and non-integrating. And I don't know if any of you in the audience, everyone knows what that means, but the bottom line is that because the viral DNA doesn't get inserted into your own chromosomes, it stands apart from that, it's not interfering and not taking any change, and that was a huge safety component to that. In some diseases we have to use, because if you have a dividing cell population, that doesn't work, that DNA gets spit out, so you have to have a gene or a vector that gets integrated. But in the context of the brain, I think, again, as Kevin had emphasized, in primates now we have data out 8 years. We treated patients back in 2000 in the brain, and those patients are still alive. So we have enormous safety data on gene therapy lasting, as well as not having any major adverse events. So I think the gene therapy approach can be very, very safe compared to other strategies. The biggest problem, again, as Kevin emphasized, is just typically getting into the brain and having to do stereotactic surgery, as an example, is one of the biggest risks associated with that. But as he said, he's making a lot of advances in terms of ventricular and CSF administration. I think it's really exciting stuff.
And I think if you, even though there's not really clinical trials that are finished, if you look at the number of clinical trials, in the past few years, there's a lot more that are making it onto phase 3. So the number that are getting further in the process is actually increasing. So I think, in 5-10 years, you will definitely start to see some of these that will probably be used as a gene therapy for certain diseases. I know one of them would be there's a retinopathy that's actually looking quite promising, and there's a gene, anti-alpha chymotrypsin, which has been shown good results as well.
Thank you.
Anna?
My question is actually for Dr. Weber. Are there any updates available for the future of minocycline?
Short answer, no. We're actually doing a little bit more work on the minocycline, trying to identify what the potential molecular changes are. It's a little bit putting the cart in front of the horse now that the clinical trial results have been published, but we did have some interesting preliminary results on minocycline changes in the AS mouse brain. So we're continuing to work on that. So probably coming up with a molecular target may spur some more interest in minocycline, but as far as my research program goes, that'll probably be it.
Thank you.
Jody?
Okay, real quick. Thank you all. Those were great presentations on a summary of your research, and it was nice to sit back and just listen to you all talk about it one by one. I think that for the FAST board and the funders that have raised the money to that, it's great outcomes, and it's nice to hear that you're collaborating, but you're all kind of coming at it differently, which I think will ultimately advance the science more. My question specifically for Dr. Anderson and then for the rest of the panel, biomarkers would be great to have specific markers, and thinking of the EEG, and I heard you answer her question before, is it in the way you collect the EEG that you could interpret it differently, or is it in the interpretation? And then could we just get a bunch of EEGs from all over the place, put them together, and have an expert panel read them? And might that be a way as a marker, or is there a way to somehow computerize it and have a computer read them?
I think getting raw data, and I mean, most centers, I think big centers, save the raw data, so it's in a specific file. And then that is fed into a computer program, a MATLAB program, and you need to understand what you're doing and what sections you're taking out to analyze. But I think it would be really nice to have that as part of potentially what the group that does this consensus of what we need data we need to compile, and that could potentially be one. It's time consuming though, and requires some expertise, but it seems like at least what we're seeing with the animals, and especially if we screen additional agents and therapies and see that if we rescue behavior, we also rescue that spectral frequency change, then that could potentially be a really nice biomarker that's non-invasive. And almost all of these children and adults too have had an EEG. So as long as you can get the raw data, it's an .edf file, and you plug it into the program. I did have, there was one online comment related sort of to epilepsy at least, and I wanted, just for the online person that made this comment, they wanted to make sure that the group, especially families with children with epilepsy, were mindful of anti-epileptic medications that are contraindicated for children with and adults with Angelman syndrome and epilepsy. And I guess it's not, we don't think of them clinically as an absolute contraindication and not an allergy, really. But there is a body of data that suggests some medications can cause the epilepsy to worsen and seizures to worsen, and vigabatrin is one, or Sabril. Additionally, drugs that target focal epilepsies like trileptal or Tegretol. So those are, there is a list of them, but basically I guess if you think of the epilepsy with that frontal spike and wave, it's bilateral, and myoclonic seizures and the atypical absence, those are more generalized type epilepsies, although you could see them with a focal epilepsy. But then we know generalized epilepsies can worsen when you use a therapy that really targets a focal epilepsy. So it's important to be mindful of that, and talk to your neurologist about it or epileptologist about it if they don't seem to be recognizing that.
One quick point on that before Chick gives us our last question. If you have a neurologist that you feel like is incredibly open and willing to talk to other neurologists and doesn't seem to have a big ego problem, let me know, because I would really like to put together a email listserv with, say, Dr. Tebert and some of the other really fantastic neurologists who will actually consult with each other, so that other neurologists, when they get their first AS patient, could go to that listserv and ask for advice. Because, I mean, we all know on Facebook the parents are pretty good at telling you what drugs work and what don't and what's contraindicated, but nobody wants to hear a Facebook parent tell a neurologist with lots of education what they should be doing. But if we could get our neurologists all together with Dr. Anderson and some of the other neurologists where they could ask questions in a very secure MD area, I think we could help a lot of kids. So if you have a neurologist that will do that, please let me know and get that name to me.
And I would emphasize, you know your child better than any neurologist knows your child. And if you don't think that your child is performing the way they should, I would press ahead. And it may mean you need a second opinion, and press for that. You have the right to that. And a physician should never be offended because you want a second opinion if you're not getting the response you want. It's your child, and it's your right to that. So I always say, I tell my patients, if your doctor has a problem with that, then something's wrong with that physician. That's not an appropriate response to a request for a second opinion.
Okay, last question, Chick.
Thank you. So this was a question about, I guess, gene therapy, viral vectors, or maybe even the biologicals that Dr. Siegel mentioned. And just a question further about the blood-brain barrier. It sounded like, Dr. Siegel, unless I misunderstood, is that you were almost a little surprised about the uptake of the drug you had injected throughout the CNS, how it had crossed the blood-brain barrier. And just to follow up on that and some of the viral vector things and the concerns about intrathecal injections, there was some news in the mainstream media this year about some techniques using like high-intensity focused ultrasound and things to disrupt temporarily and reversibly the blood-brain barrier. So you could inject drugs that would pass the blood-brain barrier and then it would repair itself. And I suspect people in this room are familiar with this. This was mainstream media stuff, not medical science journals. So I would like to know, you all in the field, is this done in one place that hasn't been repeated? Is this the real deal? Is this going to happen in the next couple of years? Is this going to drastically change the approach to a lot of these things? If you could just comment on that.
You want me to go? I know which study you're talking about, and I saw the mainstream media. To my knowledge, it hasn't been replicated yet. And it's difficult to say whether this will be, a useful technique. And I think in certain neurological disorders, it may be actually detrimental, because in some instances you already have a weakened blood-brain barrier. So for example, Alzheimer's disease. And I don't know what the situation is in Angelman syndrome yet. I don't think anyone knows. So to disrupt it may be more detrimental, because you're already damaging something that's damaged. So, and how that would affect the efficiency of the virus uptake, I don't know. Because a lot of the viruses, they use protein receptors in order to actually move through. They attach to something and then they move into the cell, or they move between the cells. And so it's difficult to say if that would actually help with that method of movement. And it may be great for maybe small molecules or things like that, which have a problem getting across the blood-brain barrier, but maybe not so much the virus.
But I mean, maybe an important lesson to take from that study is not even whether it works or it doesn't work, but again, it's just people trying different kinds of approaches, to try to address this problem, because it is a significant barrier for trying to get therapeutics into the brain. There are other types of delivery methods too, some of which Dr. Nash talked about in his talk, that are more or less effective. There's intrathecal kind of delivery as well, intracranial kinds of injection. But of course, people would like to be able to get things across the blood-brain barrier easily, and sometimes that's very hard. So, I mean, maybe this approach is something that may work. Maybe it'll be replicated. Maybe this is not the one that's going to work. But people are trying to make this kind of work. So, I'm encouraged just that people are still pushing on in this area, and if this guy doesn't get it, someone else may be.
And how did yours get across, or were you surprised, or no? Did I misinterpret that?
No, I was surprised. I'm always surprised when the stuff works. But I'm happy. I mean, it was our intention to get it across the blood-brain barrier, but I'm still very happy that it worked.
So check out, since we spent a lot of time in this area, my colleague Mike Kaplan has been working on ultrasound delivery and is a practicing neurosurgeon at Cornell. The problem that you're faced with is that the blood-brain barrier, as we've heard, is there for a very good reason. The moment you open it up, and it's been done for years with gliomas, because we use hyperosmolar mannitol, for example, to open up the blood-brain barrier, get chemotherapeutic drugs ahead. The problem is you immediately allow all sorts of foreign proteins to get in, and get a lot of inflammation, get a lot of problems with that. So even though we think about invasive neurosurgery being risky in the context of how many strokes you have and how many complications you have by opening up the blood-brain barrier, stereotactic neurosurgery is far safer as a general rule. The other problem that you're faced with when you give peripheral injection of large amounts of virus, which you really need to do periphery, you think it's less invasive, but to the immune system, it's highly invasive, and so you get some massive immunological response. And remember, only a small fraction of what you're delivering gets across the blood barrier. Most of it seeds out to the rest of the body. It's a problem. So I think the strategy, and we've thought about this a long time, so there's very safe ways now of injecting things into the CSF, into the brain, using stereotactic process. So I think the energy, even though it's interesting that people are doing it, and I think for gliomas it's promising, I think the future in terms of CNS gene therapy is still going to be standard neurosurgical approaches, which are relatively safe.
And it's possible, I mean, we do this clinically now for the neurosurgeons to place a reservoir that then you just tap into. And yes, it seems invasive, and I know it's a hard decision to make, especially for a young child, for a parent to make. But it's possible you could place a reservoir and then tap into that to deliver.
Okay, quick announcements before we thank our panel. Remember, if you are one of the people that needs to pick your tickets up from Paula, she's in the back of the room. You should probably go back there and get them. Take your pads and pencils, because the room's getting cleared tonight and they won't be back here tomorrow. Enjoy yourselves tonight, and please join me in thanking our panel again for all this wonderful discussion.